Hi and welcome. My name's Michael, and this is the introduction to my Linux networking and troubleshooting deep dive. I've built this course using both suggestions from the community as well as my own experience. I'm really excited about what I've put together in this deep dive course. Over the next few minutes, I'd like to give you a preview of the content. Let's get started. This course is comprised of 4 primary sections. We have network concepts, the machine level configuration, administrator services and tools, and advanced use cases. Beginning with network concepts, we'll cover the network interface. So we're going to discuss what information is important when looking at the information around the network interface. After that, we'll move on to network topology, where we'll cover the differences between switching and routing, and we'll look at the OSI layers in some detail with both real and conceptual examples, and then take a close look at the anatomy of an IP. Moving on to network flow, we'll look at routing and cover the routing table, followed by ARP, what it is, why it's used, and the sequence in which it occurs. Likewise with DNS. We'll take a close look at the TCP three-way handshake and why it's so reliable, and then put all of these lessons together when we look at how packets travel through the network using live examples and packet captures. Lastly, in this section, we'll take a conceptual look at VPN. This takes us out of the conceptual and into the hands-on with machine-level configuration, where we'll start with the network interface. We'll discuss static versus DHCP addressing, multiple IPs on the same NIC, multiple NICs using the same IP, etc. We'll circle back to routing and add some static routes and do a little routing troubleshooting, and then we'll wrap up the section with DNS, where we'll look at local resolution as well as name servers and DNS troubleshooting. As we get into the second half with the admin services and tools, we discuss firewalls, what they are conceptually, the framework behind them, and we'll dig into both IP tables and firewall D, as well as troubleshooting them. Next, we'll cover connection testing. Is it the firewall? Is it a layer 3 issue? We'll cover that and what tools we can use for testing at each network layer. And as an extension of that, we'll create some packet captures and perform some analysis on them. And finally, we come to our advanced use cases. I took some community suggestions and threw in some things I thought would be helpful to have a better understanding of. We'll cover port forwarding and redirecting with the firewall, and that's with both IP tables and firewall D. And if you don't have root access, no problem, because then we can create all 3 kinds of SSH tunnel, right up to a SOCKS proxy, which gives us a nice segue to proxy servers. And I use Squid as an example. We talk about whitelists, blacklists, and delay pools. Next, we cover load balancing, where I cover both HA proxy and Nginx as load balancers. And after that, we'll implement a VPN, OpenVPN in particular. We build a skeleton of a VPN and then use what we've learned about routing to leverage it. And lastly, IDS, where we'll set up Snort, and all of these sections are very, very hands-on, lots of learning activities that closely match the lessons in terms of their use cases and configurations. Just to pluck some examples from the course, we'll look closely at how IP addresses are mapped to MAC addresses, as well as how domain names are mapped to IP addresses. And we'll look closely at the TCP handshake through packet captures with Wireshark, and we'll get into how each table in IP tables has multiple chains and how those chains are processed. And these are just a few small examples of what we'll be covering. And finally, by the end of this course, you're going to be familiar with an architectural map like this. You'll recognize the different subnets, you'll probably even recognize the IPs, and you'll have a really good understanding of what's needed to implement a VPN on server 1 there in the middle, and you'll do so to grant client 1 on the left access to the web server at node 1 on the right. You'll also be familiar with the manner in which node 1 has firewalled off all web requests outside of the VPN subnet. I hope this video has given you some appetite for the course. There are a lot of learning activities provided, almost 20 of them in fact, so you'll really be learning by doing. Thanks for watching. Hi, my name's Michael. I'm a training architect here at Linux Academy. I've been a Red Hat certified engineer since 2005 and a production engineer and architect ever since. Outside of Linux, I enjoy hanging out with my family, playing games, fly fishing, and playing the guitar. I'm really excited to be here at Linux Academy to help you achieve your goals. Hi and welcome. My name's Michael, and in this lesson we're going to take a look at the network information available on the host so that we have some context to build on as we cover networking concepts later in the course. We're going to start small and build up. Some of this should be familiar to you as a Linux administrator, but I'm going to walk through the information to fill in any knowledge gaps that you might have. I'd expect you to have functional knowledge of what a MAC address, an IP, a gateway, and a DNS host is, but I'll cover them briefly just the same. Before we get started, Let me clarify what the important information is that we'll be looking at. The MAC address. This is the unique fingerprint of your network interface and is used to make sure that the data sent gets to your unique device as a final destination. The IP address is a unique address to your network and is the address of your device. The net mask or subnet is a piece of information that applies context to your IP address as well as defining the size of the network. It separates your IP into a network and a host address. The gateway is the host's connection to outside of the immediate local area network. The DNS server answers questions our host has with respect to what IP address a host name resolves to. It translates host names into IP addresses. And lastly, the DNS domain is the lookup domain, permitting us to not have to type the fully qualified domain name instead of a host name, as well as defining what domain our host name is in. So over the next few minutes, we'll look at how to pull this information from the host. The commands I'm going to be using are ifconfig, IP, nmcli, and routeL. The environment I'm using is a Linux Academy cloud server running CentOS 7. This is the same environment you have access to as a student, and I'm using the standard user account. So let's start with ifconfig. Before I get too far into ifconfig, I do want to point out that ifconfig is an obsolete program, as shown here in the man page. However, this release of CentOS 7 does include it, so I'll include it in the lesson. I'm going to run ifconfig without any switches, and I see that we have two interfaces. We have an ETH0 and we have our loopback interface. The loopback interface is a special virtual interface that the host uses to communicate to itself. It'll always be there, it'll always be up. So important information here for ETH0 is our IP address here, 172.31.110.91, our net mask, 255.255.240.0, as well as our MAC address here. Now our IP6 information is here. Here's our IP6 address. Here's our IP6 subnet. And then here's the scope. There's also some information around packets received and transmitted, and that can be useful for troubleshooting. So a newer utility to pull this information is IP, and I'm going to use IP adder, which is short for address, show. And we see a lot of the same information. We have our two interfaces, our loopback and ETH0. It's in a slightly different order, but it's all there. Here's our MAC address here. Here's our IPv4 address here, as well as the subnet. In this case, we're using the solder notation of /20 instead of 255.255.240.0. And we have the same for our IPv6. So lastly, since this is CentOS 7, and I know that it's running Network Manager, I'm going to use nmcli. I see again that we have two interfaces, ETH0 and our loopback, but I also see our DNS configuration information. Our DNS lookup server is 172.31.02. So anytime we go to find out what IP address a host name has, we're going to ask 172.31.02. And our domain is mylabserver.com, and this is over the interface ETH0. So in addition to seeing the MAC address, as well as the IP and subnet, we also see our default route here using nmcli. Lastly, down at the bottom, I see that we can use nmcli device show. So I'm going to abbreviate device with D, and we're going to pull that information. So we get a little more information. But again, the important information is here's the MAC address, here's the IP address and the subnet, and here's the gateway. Here's our DNS lookup host and our DNS lookup domain. We also see some routing information here, so let's go ahead and look at the route table. I'm going to use IP route show, and I see that our default route is 172.31.96.1. This is also the same IP as our gateway, because remember, we need to use the gateway to connect to anything outside of our local area network. For a little more granular information on routing, I can use routeL to list the entire routing table, and we get a 7-column output showing our default route over our gateway as provided by DHCP for the device ETH0. So to wrap it up, we've used ifconfig, IP, and nmcli to locate and identify the host IP address and subnet, the gateway, as well as the DNS lookup information. We also used IP and routeL to view the routing table. This information and how to find it gives us the context to build on for the next lesson. This lesson is now complete. Thanks for watching. Hi and welcome. Now that we know how to find the important network information, we're going to review some basics around network topology and connectivity. I'm covering a pretty big topic in a short amount of time, so I'm going to be glazing over a fair amount of detail, which I'll get to in upcoming lessons. For now, I want to give you an illustration of a simple network topology and discuss how switching and routing facilitate interconnectivity. I'm going to start with switching. Let's assume we have a client computer, and this computer is connected to a network over an Ethernet connection. We'll call this connection ETH0, and the wire connected to ETH0 is running to a switch. A switch is a network device used for local area network traffic. The switch is also connected to a router, and the router is connected to the internet. The router is connected to the upstream network, in this case the internet. It is the gateway to networks outside of the clients, so we designate it as such. Let me stop here for a minute. If our client wants to download something from the internet, the request will need to traverse the internal network through the switch to the router, then go through the router to the internet. This is an important distinction to make. This path from the client to the gateway is the default route. This is the route to everything outside of the local area network. We don't need the router to send and receive data to other clients within our network. Regardless of how big it grows, our requests would only traverse the router when we need to connect outside of our local network. Let's talk about routers for a minute. Our client has sent a request for some piece of data from the internet. The request will traverse the default route to connect to the internet. Once it hits the internet, it's going to need to traverse a number of additional routers and networks before it reaches its final destination. You can see these hops by using the trace path or trace route command. Eventually, it will reach the edge of the destination network, pass through some number of switches or perhaps none at all, reach its final destination, and request the data. A quick recap of that. Switches facilitate internal network traffic and routers facilitate traffic between networks. Here we have a couple of networks. We'll call the bottom one network 1, we'll call the top one network 2. In these networks, if the hosts within want to be able to communicate outside of their respective network, they need to be connected to routers, subsequently connected to upstream networks. Let's say in this example, the routers are connected to each other. We could pretend that the internet and some number of hops were between, or perhaps they're two discrete private networks, such as an office network and a server network, and each router has the proper routing table to be aware of the other. If host A wants to communicate to host F, it's going to create a network message. This message is going to contain the network request, or the payload, the destination address for the request, as well as the return address to make sure that it gets to the final destination. It's also going to contain the address of its own network card, as well as the address of the default gateway's network card, since its routing table designates the address of host F as outside of network 1. I know I'm glossing over this, but stick with me. We're going to be getting pretty deep into what's happening in upcoming lessons. The request will traverse the network and arrive at its destination. At this point, the message has been delivered, and depending on the protocol, acknowledgments would take place. Our Linux Academy Cloud server has a different topology. After however many hops are necessary, the request will hit the destination network edge, which in this case will be an AWS data center. From here, the request is routed to the VPC, which is the virtual private cloud, where it passes through a number of public network access control lists before finally reaching the destination. Cloud architecture abstracts a lot of the routing into what is referred to as software-defined networking. It is a simulation of a traditional physical network. One of the big benefits of doing it this way is there are a number of security constraints and access control lists that permit very granular accessibility programmatically. So let's wrap up. We reviewed the basic purpose of a switch. It facilitates internal network and basically forwards packets within the internal network. We reviewed the basic purpose of a router. It facilitates network-to-network traffic. We looked at traversing the network internal to external, and we reviewed a cloud network as a simulation of a traditional network. I've distilled a lot of information into a few slides here, and in upcoming lessons we're going to dive into addressing as well as the nuts and bolts of routing and how data moves through the network. This lesson is now complete. Thanks for watching. Hi and welcome. In this lesson, we're going to review the OSI model, and I'm going to talk a little bit about why it's important to understand it. The last lesson was around developing an elementary understanding of network topology. Beginning with this lesson, we're going to start getting deeper into our understanding of networking, and knowing the OSI layers is fundamental to that depth. So what is OSI and what is the OSI model? Let's start with the Wikipedia definition. The Open Systems Interconnection Model is a conceptual model that characterizes and standardizes the communication functions of a telecommunication or computing system without regard to its underlying internal structure and technology. Its goal is the interoperability of diverse communication systems with standard protocols. The model partitions a communication system into abstraction layers. The original version of the model defined 7 layers. That second to last sentence summarizes the OSI model pretty well. The model partitions a communication system into abstract layers. Let's dig into these layers. Let's start with layer 7. This is the application layer. The application layer is the interface permitting the user to send and receive data through clients and applications. Layer 6 is the presentation layer. The presentation layer converts the request from the application into a universal format. Layer 5 is the session layer. The session layer permits the ability to open, close, and manage a session between the process and response. Layer 4 is the transport layer. The transport layer defines how data will be sent, providing validation and security. Layer 3 is the network layer. The network layer looks for the best path to reach the destination. So I want you to think about IP addresses in the network layer. The data link layer, layer 2, handles communication between adjacent nodes. So I want you to think of MAC addresses when you think of layer 2. Layer 1 is the physical layer, and the physical layer handles the bit level transmission between network nodes. So connections begin with the source in the application layer, move down through all 7 layers to the physical layer, travel across the network medium, and then move from the physical layer back up through all 7 to the application layer at the receiving end. Let me break these down a little more with conceptual examples as well as actual examples for each one. The application layer is the interface permitting the user to send and receive data through clients and applications. A conceptual example is an individual using a telephone to place an order for an item to be delivered. The telephone is the interface used by the user to place the order. An actual example is a user clicking on a link within a web browser. The browser application provides the interface for the user to interact with the content provided by the remote web server. The application handles the details of finding the web server, requesting the web page, and loading the requisite assets to render the page. The presentation layer converts the request from the application into a universal format. In a conceptual example, the individual using the telephone needs to be speaking a language the person on the other end can understand. In our actual example, the web browser renders the page by converting the files stored on the remote server into formats that permit displaying the content. In the case of the web browser, this includes image formats such as JPEG and GIF being converted into actual images on the screen. The session layer permits the ability to open, close, and manage a session between the process and response. For our conceptual example, when the user dialed the telephone to place the order, someone on the other end needed to pick up so that that conversation could begin. In our actual example, when a user clicks a link in a web browser, the browser will initiate a TCP connection to the web server. The web server will send a response and close the connection. The browser will manage the additional TCP connections necessary to load externally referenced assets by the web server. The transport layer defines how data will be sent, providing validation and security. In our conceptual example, our user has placed the order and is waiting on delivery. Quality control has mechanisms in place to ensure the user is only sent what they requested and nothing else. In our actual example, the web browser breaks up the TCP requests into manageable portions, applies a label to protect the ordering, and then transports those pieces across the requisite sessions. The network layer looks for the best path to reach the destination. So remember, think IP addresses. In our conceptual example, the order has been fulfilled and shipped, and the shipping provider uses GPS to determine the most efficient and direct route to deliver the package. In our actual example, the web browser computer uses the IP address to determine if the web page is local or remote and how to reach the remote IP via the default gateway. The computer creates a message, which is a packet, and addresses it to the web server with its own return address. The data link layer handles communication between adjacent nodes, so remember MAC addresses. Conceptually, the shipping company needs to know the full delivery address to successfully deliver the order. In our actual example, the packets are structured into messages called frames to be sent to the default gateway. These frames contain the source and destination IP addresses, as well as the source and local destination MAC address. What I mean by local destination is it will have the MAC address of the default gateway if the destination is outside of the local network. If the destination is inside the local network, it will have the MAC address of the destination. The physical layer handles bit-level transmission between network nodes. So in our conceptual example, the shipping company's truck navigates a network of roads and interstates to deliver the order to the delivery address. In our actual example, this layer is hardware specific and is the actual physical connection between the computer and the network. The raw bits are transmitted as pulses of electricity or lights, that's the ones and zeros, over the network medium. So let's take a look at some example protocols for each layer. Starting with layer 7, HTTP, POP3, SMTP, DNS, and SOAP. So in our example, we were using HTTP. In the presentation layer, we have TLS, SSL, MIME, JPEG, and GIF. So in our example, we may have been using SSL or JPEG and GIF. At the session layer, we have LDAP, NetBIOS, PPTP, RPC, SMB, and SSL. SSL is on here twice. It initiates at one layer and then is processed at the other layer. It's technically a layer 5 protocol, but it's sort of in a gray area. At the transport layer, you have TCP, UDP, SPX, and iSCSI. In our example, we were using TCP for our web connection. At the network layer, you have IP, IPsec, ICMP, and RIP. In our example, we were using IP. At the data link layer, you have Ethernet, frame relay, Wi-Fi, PPP, VLAN, and MAC. We were using Ethernet and MAC. At the physical layer, you have Ethernet physical, FireWire, infrared. We were using Ethernet physical. So troubleshooting. The OSI layers are really helpful for troubleshooting. And so I'll run through a few verifications that you would do for each layer. So at the application layer, you basically want to verify that the application is functional and that your DNS settings are correct. The presentation and session layers are rarely issues if the application is performing normally. The transport layer is the layer where a lot of people get tripped up. You want to verify blocked or damaged ports. You want to look at your firewalls and make sure that QoS isn't affecting your connectivity. At the network layer, you want to verify addressing and routing configuration, your bandwidth, and authentication. At the data link layer, you want to verify switch and VLAN configurations, as well as MAC addressing and IP conflicts. And at the physical layer, you want to verify physical connections. Make sure your SFPs are plugged in all the way, make sure you're getting link lights on your Ethernet connection, that kind of thing. So that wraps up this lesson on our OSI layers. This lesson is now complete. Thanks for watching. Hi and welcome. In this lesson, we're going to take an in-depth look at the anatomy of an IP address. I'll be covering IPv4 as well as IPv6. Now that we're familiar with the OSI layers and basic network topology, for communication to take place, the source and the destination need to be addressable on the network. This is where IP addresses come in. We've got a lot to cover, so let's get started. What is an IP address? Simply put, it is the address of your device on its network. Think of it like a house number on a street. Your house may be number 101, but there may be many streets with house numbers 101. It's the same with an IP. It is the address of your device on its local network or street in the example of a house. These IP addresses allow the host to communicate on the network and each address must be unique to its network. You can't have two house numbers 101 on the same street. So here's an IP, 192.168.101.100. It's a pretty typical IP, and you may have seen one similar in your travels. Let's break it down. It's a 32-bit number divided into 4 8-bit sections. These 8-bit sections are called octets. 4 of them comprise the whole IP number. Here's the address in binary, and we can see that each octet is an 8-bit binary number. The upper limit of an 8-bit binary number is 255. That would be all ones, 8 ones in a row. As such, each octet can only be a number between 0, which is 8 zeros in a row, and 255, which would be all ones in a row. So 0 to 255. Let's examine IPv6. IPv4 was the 4th iteration of the IP protocol, and IPv6 is the 6th. Given its improvements over the traditional IPv4 space, it's being rolled out with some frequency. Here's an IPv6 address. A couple things should stand out immediately. For starters, it's a lot longer, but it's also a hexadecimal number, meaning that it's base 16, so it's not a 0 or a 1, it's a 0 to 9, and then A, B, C, D, E, F. Some of the letters represent the numbers higher than 9. In terms of length, it's a 128-bit address. This gives it a significantly larger range than IPv4, about 37 orders of magnitude to be specific. This 128-bit address is broken up into 8 16-bit sections, each separated by a colon. Each bit has a range from 0 to 15, 16 in all, starting from 0 to 9, and then A through F for the higher numbers. The IPv6 address looks a little intimidating at first. There is a technique we can sometimes use to make it more manageable. Let's take this address for example. It's kind of long, it's kind of ungainly, but you notice how we don't write out the leading zeros for an IPv4 address? Here's what it would look like if we did. So look at all the leading zeros in this IPv6 address, and this example has a lot of them to kind of prove this point. We can remove these zeros and compress the address. We can compress complete blocks of zeros, leading zeros, which can then be denoted with a double colon. Obviously, we can only use the double colon once per address, or we wouldn't be able to reliably rebuild it. We've looked at the anatomy of an IPv4 and IPv6 address, so let's go back to IPv4 for a couple minutes and talk about classful networking. There are 5 classes of traditional classful networking. These are referred to as Class A, B, C, D, and E. Remember that IPv4 addresses are comprised of 4 octets, and these have binary representation. A Class A network is represented as an address containing a 0 in the first bit of the first octet. The first octet could be anything from all zeros to all ones, but for Class A, that first bit is always going to be a 0. This means the address range of a Class A network is from 0000 to 127.255.255.255. So 0000 is special. It means undetermined. The 127 address space is also special. I'll get to that in a couple minutes. So really anything between those. A Class B network is any address having a 1 in the first bit and a non-1 in the second bit, or a 10. The resulting address space is 128.0.0.0 to 191.255.255.255. A Class C network represents all addresses having 1 for the first 2 bits and a non-1 for the third. You should start seeing a pattern here. The resulting addresses are 192.0.0.0 to 223.255.255.255. Likewise, Class D is represented by 1 in the first 3 bits, but not in the fourth, spanning 224.0.0.0 to 239.255.255.255. And lastly, Class E is represented by the first 4 bits being all ones. This would span 240.0.0 to 255.255.255.255. A couple of these classes are reserved for special use cases, such as Class D for multicasting networks, and Class E for experimental and future use. Classes A through C traditionally use a part of their 32-bit address to accommodate different sized networks. So let's talk about classful networks and subnets. In terms of using a portion of the address to accommodate different sized networks, Class A uses the remainder of the first octet to define the network, and the rest to define the hosts, represented as the delineating line here. The first octet is masked off, leaving the remaining octets for host numbering. The resulting network is a little over 2 million host IPs available. Class B uses the first 2 octets, so that's the remainder of the first and the whole second, to define the network, and the third and fourth octets for hosts, again represented by the line. The net result is over 65,000 IPs available. Continuing this pattern, Class C networks use the first 3 octets to define the network and the last octet for the hosts. The first 3 octets are masked off. The last octet represents the host, permitting 254 host IPs. 0 to 255 is 256 numbers. However, the first number 0 and last 255 are always reserved. So Class A has lots of room for hosts, but very few networks, and Class C has little room for hosts, but lots of networks. So let me pose a hypothetical question to you. If you wanted to build a network for 500 hosts, how would you do it? Would you use a Class A network and waste potentially 2.1 million IPs? Would you use a Class B network and waste around 60,000 potential IPs? Would you use 2 Class C networks and have scaling problems? How would you do it? We'll get back to that. Within a classful network, some ranges are designated as for private use. So for Class A, this range is 10.000 to 10.255.255.255. For Class B, it's 172.16.00 to 172.31.255.255. And for Class C, it's 192.168.00 to 192.168.255.255. There are some additional reserved ranges for specific use cases. There's also a reserved range for IPv4 addresses. This should look somewhat familiar to you. This is the loopback range. Normally, the loopback is represented by the first host IP in this range, which is always 127.0.0.1. With that out of the way, let's revisit subnetting and dig into that a little more. Here's our garden variety IP again. We now know that it's a Class C IP within the private range. In a typical classful network, the first 3 octets of a Class C address represent the network, so 192.168.101. And then the last octet is the host, which is host number 100. Here's the address in binary. We need to mask off the first 3 octets to define the size of our network, so we're masking them off with all ones. The resulting net mask computes to 255.255.255.0, because remember, all ones, 8 ones in a row in binary, is 255, leaving us just the 0 for the host space. So we can have 1 to 254. That's our 254 limit of a Class C network. Nowadays, the use of classful networks for large portions of IP space is kind of a legacy concept. You have your choice between a couple million IPs, 65,000-ish IPs, or 254 IPs. So what if you did want to design that network for 500 IPs? You could use 2 Class C networks, but that doesn't scale well. This is where CIDR comes in. CIDR stands for Classless Interdomain Routing. Let's look at our Class C private address again, so we're going to keep it a little classy. Here is how the subnets work out for each of the classes. Our Class C address allocates 24 bits for the net mask, so if we wanted to write out our network in CIDR notation, we would use a /24. That 24 represents those first 24 bits being masked off. So let's look at another example. Here is our friendly address, and let's drop the notion of a classful network. In the 192.168.101 space, we can use IPs from 1 to 254, because remember 0 and 255 are reserved. Here is the binary representation of that net mask again. But what if we wanted to just use those first 23 bits, like I've got the line here? For starters, we designate the subnet as a /23 in CIDR notation, and with a little binary calculation, we would see that that comes out to 255.255.254.0. So we've masked off the first 23 bits. And the resulting IP range is 192.168.100, so 1 to 254, and then 192.168.101, 1 to 254, which is going to give us 510 hosts. This would be perfect for a 500 host network. So let's look at subnetting in IPv6. It's similar. Here's our IPv6 address again. It's a 128-bit hexadecimal number separated into 8 16-bit sections separated by a colon. The first half, that first 64 bits, are designated as the network section and is used for routing. Second half is designated as the node and is derived from the MAC address of the interface. This was one of those aha moments for me. Knowing that the node section is derived from the MAC address, for me, made it make a whole lot more sense. Within the network section, the first 48 bits are designated as global and used for routing over the internet, and the remaining 16 bits are the subnet ID for use on an internal network. So pretty simple. You have two halves. The back half is the node, front half is the network. The first 3 sections of the network are for global use, and the last network section is for your internal net mask. So pretty simple stuff. There are 3 types of IPv6 address: global unicast, unique local, and link local. Global unicast are internet routable. They always start with a 2001 colon, and blocks of these addresses are allocated by ISPs. Unique local is non-routable from the internet and is usable for internal networks, similar to our IPv4 private ranges. And link local is non-routable from the internet as well, but is restricted only to a network link. It always starts with FE80 colon. So before I wrap up, let me mention NATing, or Network Address Translation. Network address translation is a method of remapping one IP address space into another by modifying network address information in the IP header of packets while they are in transit across the traffic routing device. So a simple use case would be, we have our web server running on our internal network on 192.168.101.100. This is connected to the internet via router. This is our default gateway. If we wanted to make our website available from the internet, we would need to use the public IP address that our router uses for its internet connection. We would then map that to our internal IP using network address translation, translating the traffic from one IP to the other. For this specific use case, port forwarding would be a more apropos fit, as we'd only need port 80 and port 443 traffic being passed instead of all the IP traffic, but you get the idea. So let's wrap up. IP addresses are necessary for layer 3 addressing on the network. An IPv4 address is a 32-bit number separated into 4 8-bit octets by periods. An IPv6 address is a 128-bit number separated into 8 16-bit sections by colons. A subnet is a subsection of the network. It determines the IP range and size. A classful network uses a portion of the IP address as the network address. And CIDR permits more flexibility in terms of network size over the traditional classful design. This lesson is now complete. Thanks for watching. Hi and welcome. In this lesson, we're going to talk about routing and routing tables and how they facilitate network communication. Let's get started. We'll start with the basics. A router is a layer 3 device functioning at the IP level. So remember, layer 3 is the network layer, layer 2 is the data link layer, so think MAC addresses, and layer 4 is the transport layer, think protocols like TCP, UDP, as well as firewalls. And a router forwards packets between networks. The routing table is a static table mapping of the best path to a network destination. The routing table lists destination and gateways for networks the host belongs to. If it's a member of a single network, there'll be a single gateway entry. If it's a member of multiple networks, there may be multiple gateway entries. So here's an example routing table. Let's walk through it. We have 8 columns and 2 rows. Looking at the columns, we have a destination where the traffic is bound, the gateway to use for that traffic, the net mask for the destination. The default gateway is always going to be 0000, and the flags. In this case, U for up, meaning the route is up, and G for gateway. Metric isn't used by recent kernels, but it stands for destination in hops to the target. Ref is the number of references to the route, also not used. and use is the count of lookups for the route. iFace is the interface. So let's look at the entries. If the destination is outside of the local network, inside the local network would be known, right, and not a 0000, then use the gateway. If the destination is inside the local network, in this case 172.31.69.0, then don't use the gateway. You've probably heard the term static route before. Let's talk about those for a minute. These are manually configured routes. They are used for traffic that should not or must not go through the default gateway. Here's our routing table again. Let's say that 172.31.96.0/20 is the server network and the office network is 10.0.0.0/8. The office network is accessible via a local IP of 172.31.96.2. So to be able to communicate on that network, a route would need to be added to permit this host to communicate with the office network through that router. This is, of course, assuming that the default gateway will not permit communication to that network. And once the route's added, it is, of course, ordered in an if-then style. So if the destination is unknown, write quad zeros, then we use the gateway 172.31.96.1. If the destination is the 10.0.0.0/8 network, then we use 172.31.96.2. And if it's on our local network, we don't use the gateway. So I'm going to talk about BGP for a minute. This is a really big subject, and I am really glazing over it, but just to give you a little bit of awareness as to what BGP is. BGP stands for Border Gateway Protocol. It is the routing protocol used to route traffic across the internet. This is the protocol that enables the internet to work. BGP is a layer 4 protocol sitting on top of TCP. This makes it much simpler than OSFP as it does not have to manage what TCP handles. There is no discovery. Peers are manually configured to exchange routing information and form a TCP connection. And organizations can use BGP for true multi-homing of their corporate network. An ASN, an autonomous system number, is required to implement BGP peering. This is a special number assigned by IANA for use primarily with BGP that identifies each network on the internet. Two routers that have established a connection and exchanged BGP information become BGP peers, exchanging routing information between them via BGP sessions over TCP. Again, I know I'm glazing over this. This is only tangentially related to Linux networking and troubleshooting, but you should have some awareness of it. This subject is more than capable of being a deep dive in and amongst itself. So in conclusion, routers connect different networks. Routing information is contained in a routing table. Static routes can be used for connections that can't or shouldn't use the default gateway. And BGP is the routing protocol that enables the internet to work. This lesson is now complete. Thanks for watching. Hi and welcome. In this lesson, we're going to define and understand ARP requests. Let's get started. ARP is short for Address Resolution Protocol. ARP is a communication protocol used for discovering the MAC address associated with a given network layer address, an IP address. Put simply, ARP is used for mapping an IP address to a MAC address on the network. To understand why ARP is needed and used, we need to understand the sequence to moving data through the network. When we send requests through the network, we are sending some bit of data. The data may be the question. It may be, hey, send me this picture. Or it may be the answer, hey, here is the picture. This is what we refer to as the payload. The point of the network is to be able to send and receive this data. But the data needs to know where it should be delivered and to who to send it. A layer 3 header is created containing the source IP and the destination IP. This facilitates network-to-network delivery. A layer 2 header is also created. The layer 2 header contains the sender's MAC address as well as the receiver's. This ensures end-to-end delivery. For instance, if the host is sending data or a request to somewhere outside of the network, the receiving MAC address will be that of the primary gateway. Upon receipt, the gateway will strip the layer 2 header, add a new one for the next hop, per the router's job getting that data from hop to hop. If the MAC address to the delivery IP is unknown, an ARP request must be sent to the network. This information is needed before the data can be sent. Lastly, with all of the needed addressing available, the data is sent. The ARP request takes the form of a network broadcast. So here's an example. We have a 2-node network. Host A has the interface ETH0 with MAC address AAAA, which I've abbreviated to keep simple, and IP 11.11.11.10. Host B has an interface ETH0 with MAC BBBB, again abbreviated, and IP 11.11.11.20. Without an entry in the ARP table, neither of these hosts has the MAC address for the other and as such would not be able to communicate. The ARP information is kept inside of the ARP table. Host A is going to create a message. Who has IP 11.11.11.20? I need your MAC address, and here's mine. It's then going to send the message to the entire network in what's called a broadcast, meaning every connection on the network is going to receive it. Host B is going to receive this message, and upon doing so, updates its ARP table with the IP and MAC address of host A. It will then formulate a response saying, I have IP 11.11.11.20, and here's my MAC address. This is then sent unicast back to host A, so only host A will receive it. Host A will then update its ARP table and be able to create the layer 2 header necessary for communication. So let's take a look at the ARP table on a couple of network devices. I have 2 VMs here. I have one CentOS VM with IP 146, and I have one Ubuntu VM with IP 182. They're both on the same subnet. They're both using the same gateway. Right now, neither one is aware of the other on the network, and I know this because I can use IPN, N standing for neighbor, to take a look at the ARP table. I can see that our gateway is represented here, and I can see that the machine I'm using to log into these via SSH is also here. And on the Ubuntu side, I see the same thing with the exception of one more host on the network, which may be making some kind of a connection. So right now, neither of these hosts is aware of the other on the network. So if I were to issue a ping from the CentOS server, before that ICMP payload can be delivered, it needs to create the layer 2 header, and it would need a MAC address to do this. So it's going to send an ARP request out to everyone on the network, and it's going to say, hey, who has this IP? I need your MAC address, and here's my MAC address so you know where to send it. So let's grab the IP of our Ubuntu server, and let's go ahead and ping it from our CentOS server. So we have, and if we look at the ARP table, it now contains our CentOS server. And if we look at the ARP table on CentOS, we now see that it contains our Ubuntu server, the IP, as well as the MAC address, so they are now aware of each other on the network. So in conclusion, ARP is necessary to map layer 3 IP addresses to layer 2 MAC addresses. This is used for local area network connections. Connections outside of the local area network go through the gateway, so the ARP request is for the gateway MAC address. The ARP table is dynamically updated and can be viewed using the IPN command, N being short for neighbor. This lesson is now complete. Thanks for watching. Hi and welcome. In this lesson, we're going to look at DNS in the context of the service that it provides and how we use it. Let's get started. What does DNS stand for? It stands for Domain Name Service. This is a pretty apt name as it is the service that permits us to use domain names instead of IPs for addressing at the application level. DNS is a Layer 7 communication protocol used for discovering the IP address associated with a given domain name. Put simply, DNS is used for mapping a domain name to an IP address on the network. So how does DNS work? DNS is a pretty big topic, particularly when we're talking about implementing and managing a DNS infrastructure. We're interested in the network side of things, so we're going to be looking at it from that perspective, and it all starts with the query. A fully qualified domain name is the complete domain name for a specific host on the network. When a computer wants to initiate a connection to a fully qualified domain name, such as www.example.com, it needs to know where that host is on the network. The computer will send a query to the DNS server asking it to resolve the FQDN to an IP address, and then it looks at the routing table to determine where to send that request. So how does it work? Using www.example.com, there is an implied period after the .com. The query is going to start at the far right with that implied period. This part of the query will be resolved by the root servers and then forwarded to the top-level domain servers. The TLD servers then resolve the .com portion of the address. Root servers are available to answer domain queries regarding TLDs such as .com, .gov, .edu. You get the idea. The query is then forwarded to the name servers for the domain, in this case, example.com. The name servers resolve the domain portion of the query, in our case, example.com, and the name servers may also be able to resolve the www portion. Or they may need to forward that query to additional authoritative DNS servers managing the zones within that domain. So let's walk through the DNS resolution sequence. First, we have to resolve the dot. That's going to be handled by the root servers. Then we have to resolve the TLD, the .com, the .gov, the .edu, .net. That's going to be resolved by our TLD servers. Then we have to resolve the domain, example.com. That's going to be resolved by the domain's name servers. And then we have to resolve the www. That's probably going to be handled by the domain's name servers, but if it's a large domain with multiple subdomains under it, then it could be handled by other authoritative DNS servers within that zone. Finally, we get the IP address and we can make our connection. All right, so let's look at an example of this from the command line. The command I'll be using for this is dig, and this command is part of the bind utils package for CentOS. So let's run a dig, and we're going to use -4 because I'm only interested in IPv4 against www.linuxacademy.com. And what we see is, here is the question section. Give me www.linuxacademy.com. I want the internet record. I want the A record. And our answer is www.com has these 3 A records. So 3 IP addresses. So that's pretty succinct. Let's look at the path it follows for the query. Let's say we want to see the complete path it follows for this query. I'm going to run the same command, only I'm going to add a plus trace because I want to trace all of it. Now I'm going to get back some lines that are really, really long here, and I don't want to see those. I don't have a whole lot of window space to work with. So I'm going to cut them out. So any lines greater than 50, I don't want to see them. Let's run it. Okay. Here is the dot that we resolved. Here are the root servers. Here is the .com that we resolved, and there are the TLD servers, and then here is the www Linux Academy, the domain part that was resolved. So let's wrap it up. DNS is necessary to map fully qualified domain name addresses to layer 3 addresses. We need those IPs. This is used for internal and external connections. Resolution begins with the TLD and progresses through the name server for the domain. Once the domain name has been resolved to an IP, the connection can then begin. This lesson is now complete. Thanks for watching. Hi and welcome. We've looked at the basic network topology, routing and switching. We know our OSI layers. We're familiar with routing and DNS. In this lesson, we're going to look at the TCP handshake. Let's get started. So what is TCP? TCP is Transmission Control Protocol. TCP exists at layer 4 along with UDP. It is a highly reliable connection protocol through positive acknowledgement with retransmission, PAR. Data is resent if an acknowledgement is not received. The layer 4 data is referred to as segments. Each segment contains a checksum for verification upon receipt. So segments go inside of packets, packets go inside of frames. If verification succeeds, the acknowledgement is sent. If verification fails, the receiver discards that segment and waits for retransmission. Remember, data is resent if an acknowledgement isn't received. So let's look at the TCP handshake in action. We have two hosts, host A on the left, host B on the right. Host A wants to communicate with host B. It already is aware of the IP address. It already has an entry in the ARP table. So we're good to go. To make that TCP connection, it's going to start with a SYN request. It's going to send that across the wire unicast to host B. Host B is going to receive it and create a SYN-ACK request. So I am acknowledging your SYN request. It's going to send that back unicast, at which point host A is going to create the ACK request for the SYN-ACK, and it's going to start sending some data. That is the basic three-way handshake. So let's look at it in a little more detail. So we have two hosts, 10.0.1.154, and we have 162.221.202.8. We're going to send the SYN request from the host on the left to the host on the right. And this is what that's going to look like if you were to look at it in Wireshark. So you see the top line there, line number 3. The source is 10.0.1.154. The destination is 162.221.202.8. The protocol is TCP. And if you look in the info column, you'll see that that is a SYN request. If you then look down under the flags, you'll see that the SYN set is 1. So those flags are going to be zeros or ones, and SYN set is 1. So 162.221.202.8 needs to respond SYN-ACK. So it does. So now we're on line 4 here. So source is 162.221.202.8. Destination is 10.0.1.154. Protocol TCP. And you can see in the info section, it is a SYN-ACK. So if we look under the flags, SYN is set. Acknowledgement is also set. And then lastly, our host on the left, 10.0.1.154, has to send the ACK request to the SYN-ACK. So it has to say, yes, I received your SYN-ACK. Here's the ACK for that, the acknowledgement, to 162.221.202.8. And you can see that now on line 5, source 10.0.1.154, destination 162.221.202.8, protocol TCP is the ACK, and then in line 6 you can see client hello. That's where the data starts sending. If you look at the flags, we have acknowledgement set, and you'll see that SYN at the bottom is not set. So to wrap it up, I'm going to reuse the definition slide. TCP exists in layer 4 along with UDP. It's a highly reliable connection protocol through that positive acknowledgement with retransmission. So we saw the positive acknowledgement. We didn't see any retransmission, but we'll look at examples of that as we come up and we look at packet flow. Data is resent if an acknowledgement isn't received. The layer 4 data is referred to as segments. Each segment contains a checksum for verification upon receipt. Remember, segments go inside of packets. Packets go inside of frames. If verification succeeds, an acknowledgement is sent. If verification fails, the receiver discards that segment and waits for retransmission. This lesson is now complete. Thanks for watching. Hi and welcome. In this lesson, we're going to begin putting together everything that we've learned so far in terms of how data moves through the network. This is going to be a lot of fun, so let's get started. So the first thing to keep in mind is the connection sequence. So if you wanted to make a connection and you're using a host name, the first thing that's going to happen is the client is going to reach out and say, hey, I need the IP address for this host name. It's then going to look in the ARP table, and it may say, hey, I need to send out an ARP request to get that MAC address if it's on my local connection or if I don't have the MAC for my gateway. So before I go on, it is possible that we don't need to issue a DNS query, for instance, if we're connecting to an IP address, and we don't need to issue the ARP request if we already have that information in our ARP table. And since we're using TCP, the three-way handshake will initiate We could be using UDP, but UDP is a lot less fun to dig into because it's basically just a unverified stream of data. So you would use that for video or gaming or something like that, where you don't need the checks and balances of acknowledgement of receipt. And then finally, we make our connection. So I have some packet captures ready to go. Let's take a look at those and dive into some actual examples. So the first one I have here is just a standard DNS query. So I just ran dig on my host while running a packet cap, and then this is what I got back. So we can see our source is 10.0.1.1.5.4 and our DNS server is 10.0.1.1. I send a standard query, hey, I need the A record for linuxacademy.com. Here is the request, standard query. And my query here is for the A record for linuxacademy.com, the internet. Here is the response. There's my query. And my answer is linuxacademy.com has 3 A records, 34.230, 144, 134, this one, and this one. And you can go in, you can actually see the time to live and that sort of information. So that is a basic DNS query. Let's take a look at the three-way handshake. And here we have a three-way handshake. So we have source is 192.168.1.104, and our destination is 216.18.166.136. We send the SYN, and we look down here, and we look at our flags, and we can see the SYN flag is set. It responds with acknowledgement of the SYN. We see that our SYN flag is set and our acknowledgement flag is set. And then we respond with, okay, got it. Acknowledgement set, but SYN is not set. So that is the basic three-way handshake at this point. Source 192.168.1.104 would say, hey, here is my request for data, or hey, here is some data. And then 216.18.166.136 would say, okay, got it, and then formulate some kind of response. This is a good one because this works through pretty much all of it. On our source side, we have 192.161.51.182. And on our destination side, we have linuxacademy.com. So this is from my computer to linuxacademy.com. This is what happens when I try to load the web page in a browser. Okay, so here's what's going on. I've tried to load the web page, but I don't have my ARP table populated with the gateway, and I need to do a DNS lookup. So the first thing we're going to see is a broadcast sent from my computer. It says, who has 192.168.51.2 on this network? Tell 192.168.51.182. I am 182, so I'm sending that request. And so if we look down here, we see that the sender's MAC address is this one, and our sender's IP address is my IP address. This is my VMware MAC address that it has assigned me, and this is my IP address. My target MAC address is unknown, but my target IP address is 192.168.51.2. This is my gateway. The gateway will respond and say, hey, 192.168.51.2 is at this MAC address. So if we look down here, we have a sender MAC address, we have the sender IP address, and we also have the target MAC and target IP. Now the ARP tables are up to date, and we can proceed with our connection. My computer sends the query, hey, I need the IP address for this linuxacademy.com. So I request for the A, so a request goes out for the A record. A request also goes out for the quad A record. The quad A record response comes back. It is empty. The A record response comes back, and it is populated with the 3 linuxacademy.com IPs. At this point, my computer, 192.168.51.182, to the destination, which is one of the IPs from above. In this case, we used 52.86.212.143. It came back first. We send the SYN request. So here it is, 192.168.51.182, 252.86.212.143. Here is the SYN request. The Linux Academy web server sends back the SYN ACK, so it acknowledges the SYN request. My computer then sends back an acknowledgement, so I've acknowledged your SYN ACK. Here comes some data. And so then I send the request for linuxacademy.com. And in this case, I'm using curl. The web server responds back with an acknowledgement of the request. It then sends the 302 redirect down here at the bottom that says this document has moved and my browser knows to now use HTTPS instead of regular old HTTP. I send the acknowledgement for having received that. Here we have an SSH connection from my machine, again 192.168.51.182, and I'm trying to SSH into my Linux Academy cloud server, which is mchristian1.mylabserver.com. So the first thing that's happening is my machine needs to resolve mchristian1.mylabserver.com, so it sends out the standard query. In this case, my DNS host is 192.168.51.2, so the query goes there for the A record as well as the quad A record. Now, before my DNS host can respond to that, because it's on the same network, it needs to know my MAC address. So it sends out the query, who has 192.168.51.182? Tell me 192.168.51.2. And this is a broadcast request. My computer will respond, hey, I have 192.168.51.182, and here is my VMware generated MAC address. At this point, my DNS host can respond to the query. It responds to the quad A with nothing, and it responds to the A record with this IP here, 18.212.195.175. So now the TCP handshake can begin. My computer at 182 sends to the Linux Academy cloud server IP 175 the SYN request. It responds with the SYN ACK. My computer responds with the ACK, as well as some data. Hey, here we go. We've got protocol SSH, and here's what I've got. Let's connect. The Linux Academy cloud server will respond, acknowledged, I got that, and here's some responding data. Protocol, the same. I will then respond, I got that, and then key exchange initiates, some other stuff goes on to make sure that the connection is encrypted and we are connected. I received a prompt to log in, and we're good to go. And you can see some of that here if I were to scroll down. In this example, I've simply tried to load example.com. So I'm back to my computer with 10.0.1.154. So the first thing my computer does is it initiates a DNS query for example.org to 10.0.1.1, which happens to be my DNS server. 10.0.1.1 replies, here is the IP for www.example.com. A SYN is sent from my machine. SYN ACK is replied from www.example.com. An ACK is sent back from my machine. And then the request. That request is acknowledged, and the response, in this case, is a 200. I then send an acknowledgement saying I received that. I then receive a duplicate acknowledgement. So I've sent two acknowledgements. So this was an extra acknowledgement that I sent that it probably just didn't receive quickly enough. And it is a duplicate of this one here. So it simply retransmitted it because it didn't receive the reply in time. So that wraps up some Wireshark examples, and looking at the segments, packets, frames, all travel through the network. We're going to be diving into Wireshark a little more when we start talking about packet captures. But for now, I hope that this has added a lot of context to what we've been looking at up till now and starts putting it all together. This lesson is now complete. Thanks for watching. Hi and welcome. In this lesson, we're going to talk about VPNs. This is a very big subject, and we're not going to cover the full width and breadth of VPN at all here. I just want to give you a conceptual example of what a VPN is and what the purpose is. So VPN stands for Virtual Private Network, and so let's talk about some use cases. A VPN connection is an extension of a private network using the IP connectivity of the internet to connect remote clients to remote sites in an encrypted private connection. So why would you want to do that? Maybe you want to secure your private network traffic over an insecure public network. So you're at a coffee shop and you are working on something and you don't want the coffee shop's wireless or network guy or ISP to see all of the traffic that you're passing back and forth. Maybe you want to permit connections to an internal corporate resource from a remote location. So you have someone in HR and they are working from home one day. They still need to be able to log in and access all of their services that permit them to perform their job function. So they would use a VPN connection from their house to the corporate office. Or perhaps you want to connect two separated private networks together. So this is more of an extension of the WAN. You have two corporate offices, or you have a corporate office and a branch location, and you want them to be able to pass traffic back internally. The routing table lists the destinations and gateways for all the networks that a host belongs to. So for each of these networks, you would need an entry in your routing table. So here we have an example of a site-to-site VPN. We have two private networks, the network on the left and the network on the right. Both of these are connected to their own ISP, which is connected to the own internet. If they wanted to talk back and forth, we would have to use network address translation or port forwarding or public IPs with DMZs, something of that nature for them to be able to communicate. However, they would not have access to each other's internal resources without implementing VPN routers on both ends and establishing the VPN tunnel in between them. At that point, they would be an extension of each other's network. The VPN router on each end would have to have the requisite routing table entries to know where to forward the packets. So a site-to-site VPN connects two parts of a private network or two private networks, and this allows an organization to have routed connections between separate offices or with other organizations over the internet. And here we have an example of a remote access VPN. This is probably the one you're going to be the most familiar with. Your company has issued you a VPN client and credentials, and you use that to connect with your corporate office, and then you can access internal network assets. So a remote access VPN connection is made by a remote access client. A remote access client is a single computer connecting to a private network from a remote location. The VPN server provides access to the network resources where the VPN server is connected. The packets sent across the VPN connection originate at the VPN client. So let's talk about what makes VPN connectivity secure. That is the VPN tunnel. Tunneling permits the encapsulation of one type of protocol packing within the datagram of a different protocol. For instance, sending TCP/IP traffic over the internet. For PPTP and Layer 2 tunneling, L2TP, a tunnel is similar to a session. Each end of the tunnel must agree to the tunnel connection and will negotiate configuration variables such as the address assignment, encryption, and compression parameters. The mechanism used to create, maintain, and end the tunnel is the tunnel management protocol. Only after the tunnel is established can data be sent. When the tunnel client sends network data to the tunnel server, the tunnel client appends a tunnel data transfer protocol header to the payload. The client then sends the encapsulated and usually encrypted data to the tunnel server. The tunnel server accepts the data, removes the tunnel data, and forwards the payload to the destination network within the VPN. So in conclusion, a VPN can be used to securely connect a client to a private network. A VPN can be used to securely connect two private networks. A VPN works by encapsulating and encrypting the network data at the client end and decrypting it at the destination end. There is a whole lot more to VPNs than I've covered in these few slides, and you may see a learning activity later in the course that has you working with VPNs on a more intimate level. For now, this lesson is complete. Thanks for watching. Hi and welcome. In this lesson, we're going to review the difference between dynamically allocated IP addresses through DHCP and setting a static IP. Let's get started. We'll start with the differences between them. Static IPs are dedicated, unchanging IP addresses assigned to the device. Dynamic addresses are assigned from a pool of IP addresses from within the DHCP scope. So the DHCP server will have a block of IP addresses, or a range or a couple of ranges, that it can allocate network devices IPs from. Upon setting a static IP, you also need to specify the subnet, the gateway, and the DNS host information. DHCP will almost always provide subnet, gateway, and DNS information upon assigning an IP. Static IPs are not dependent on DHCP for anything, and dynamic IPs are dependent upon DHCP for lease renewal upon expiration. Static IPs are typically used for important network devices and hosts that require absolute connectivity. DHCP is typically used for hosts and clients requiring transient connections. I've got an asterisk here. DHCP is used for managing lots and lots of IP addresses on a large number of hosts. So unless you have an army of admins that you can assign to babysit, thousands of IPs across a large infrastructure, you're probably going to be using DHCP with reservations. So let's look at some considerations of using DHCP. Using DHCP creates 3 potential points of failure in network connectivity: the DHCP host itself, a rogue DHCP host, and DNS. The DHCP host becomes an issue if it is misconfigured, especially if you are dependent upon reservations for static-like IP assignment. And what I mean by that is if you have a junior or mid-level administrator who has gone in and starts making configuration changes in the DHCP host, and those configurations are applying as leases are expiring and renewing, and all of a sudden things can't talk to each other because they're not at their typical IP assignments. The potential exists for a rogue DHCP host to present network configurations that could route traffic to a different router for nefarious purposes, or you could have somebody standing up a DHCP host because they don't even know any better on your network. That can be a problem. If the host IPs are transient and changing, you'll need to rely on fully qualified domain names for the host-to-host communication. This places a dependency on DNS for FQDN to IP resolution. Again, DHCP makes managing thousands of host IPs in a virtual or automated infrastructure on a secure network much, much easier. Let's talk about DHCP leases. The DHCP server will grant a lease on an IP address, assigning it to the host for a period of time. The DHCP request and offer are layer 2 broadcasts similar to ARP requests and require a running DHCP client. The DHCP server uses UDP port 67, the client uses UDP port 68, and you can use reservations to make sure that the same hosts get new leases on the same IPs upon expiration. So to view the lease information on the host, this is going to be a little bit different between Ubuntu and CentOS and Debian, etc. But if you cat out var lib dhc, you can generally find it. In this case, I'm referencing varlib dhclient, dhclient.leases, and you can always grep through varlog messages for DHCP offer. You might have to use varlog star if your log rotate is rotating your messages more frequently than your lease is updating. So let's look at the DHCP sequence. The first thing that's going to happen is the client broadcasts a request on the network for a host that can assign it an IP address. So I'm a brand new device, I'm on this fresh network, I have to send out a request, hey, somebody give me an IP address. The DHCP offer comes in from the DHCP server. It will respond with an offer of an IP address, and then I will request that IP address officially. I'll say, okay, you're offering me 192.168.101.100. I'll take it. That is my request. The DHCP server will then acknowledge that request and say, all right, it's yours. So the DHCP server acknowledges the IP address has been assigned. So enough of the conceptual. Let's take a look at what this looks like in real life. I have an Ubuntu VM running here. In this tab, I've started Wireshark, and in this tab, I just have my console. So the first thing I want to do is take a look at my DHCP lease information. This path is going to be a little different on CentOS, but if you use tab complete, you'll still find it. So I'm going to cat out varlib dhcp dhclient.leases. And I can see my lease information for interface ENS33. I have this IP 192.168.51.187. My subnet's 255.255.255.0. My gateway is 192.168.51.2. Here's my lease time. Here's my DNS host. And then there's some additional DHCP information here in addition to our renew, rebind, and expire times. So the next thing I'm going to do is take a look and make sure that my DHCP client is running. And so for that, I'm going to use SS, listening on UDP, and I want the number of the ports, and I'm going to grep for DH client. And of course, I have to use sudo for this. And I can see that it's running on port 68, or rather listening on port 68 UDP. So the next thing I'm going to do is jump down here and start a packet capture. And we're capturing. So I need to release my IP address. I'm going to use DH client TACR for that. And then I'm going to restart my DH client. And so if I look at my packet captures, I have lots of information here. I'm going to stop it. And now I'm going to filter for boot P. And I can see here is where I released it. Here is the discover, the broadcast. So if we look down here, source port is 68. Destination port is 67. Here is the offer. And if I scroll down here, I can see that it's offering 192.168.51.187. Here is the request where my client sends back, yes, I'll take that IP address. Requested IP address 192.168.51.187. And here is where the DHCP server acknowledges that request, and I now have that address. Let's talk about static IPs for a couple minutes. You need to provide the following information to set a static IP: the IP address, the net mask, the gateway IP, the DNS host, which is optional, and the DNS domain, which is also optional. So let's take a look at that. So let's look at how we can set a static IP when we already have a DHCP IP. So I'm back on my Ubuntu VM, and you can see I've got 192.168.51.185. And we know from earlier that this is running DHCP. So if I wanted to set this as a static IP, I would use nmcli connection modify, and I would modify the wired connection 1. That is this connection name up here at the top. And I would set the IPv4.method, and you can tab complete here, to manual. I would set the IPv4 address to something like 192.168.51.191, so something different from 185. And I'd go ahead and use the CIDR notation for the subnet. Now I'll also have to provide the gateway. So IPv4.gateway, and I already know that the gateway is 192.168.51.2. So I'll reuse that. And I'm not going to add any DNS information. So I'll hit enter. That has applied the change. It hasn't taken effect yet. So if I use an nmcli, I'll see that I still have 185. So I'll need to drop the connection and pick it back up. For that, I'll use nmcli con down, and I'll use wired connection 1. And then I'll do the same thing with con up. And you can now see I have IP 191. So if I try to ping 1.1.1.1, I get some information back. However, if I try to ping something like google.com, I'm not going to get anything back because I haven't added a DNS server. So let's go ahead and do that. nmcli con mod wired IPv4 DNS, and I'm going to use 192.168.51.1. I've got to drop the connection again. Take a look. We now have some DNS information down there. Let's try pinging Google. Still not going to work because I put the wrong IP address in. So let's fix that. Let's go back and put IP address 2 in. Take our connection down. Bring our connection up. Look at it. We now have the right IP address in there. And we'll ping google.com and everything's fine. So there's a little bit of troubleshooting in that, and that's how you set this. If you wanted to set it back to DHCP, I would use an MCLI connection modify, and we're working with wired connection 1 here, because remember, that's the name of our connection. And I'm going to set IPv4.method to auto. I'm going to set IPv4.address to nothing, IPv4.DNS to nothing, and IPv4.gateway to nothing. I've got to drop the connection and bring it back up. Take a look at NMCLI. We are back to IP 192.168.51.185. We can ping 1.1.1.1 again. Everything's good. And we can try to ping Google. And everything's good. So we've restored our connectivity. So we switched from DHCP to static, and then we switched back to DHCP. So in conclusion, the DHCP host provisions IP addresses to network devices upon request. We looked at a command line example of lease information. The DHCP request is a layer 2 broadcast. The sequence is discover, offer, request, acknowledge. We looked at a Wireshark example of the DHCP request sequence. To use a static IP, you must provide all of the network information. And we looked at a command line example of going from DHCP to static and back to DHCP. This lesson is now complete. Thanks for watching. Hi and welcome. In this lesson, we're going to look at having multiple IP addresses per host. There are a number of reasons you might want to do this, from IP segregation of services to fault tolerance. Let's get started. Here we have one IP address allocated to one interface on a single host. This is the most common configuration you'll find, but what are some others? Well, you can have multiple IPs on the same network on a single interface, and that's what we're looking closer at in this lesson. It could be that you're consolidating multiple services into a single host, or you just want discrete IP address space for each service. But let's look at some other configurations as well. You could have the same IP across two different interfaces, and this would be useful for additional throughput, but more likely for fault tolerance and balancing across two diverse paths if an interface fails. You can also have multiple interfaces with multiple IPs. This is something we're going to look at more closely when we discuss setting up a Linux router. In this manner, the host can belong to two separate physical networks and then pass the traffic between them. But back to the multiple IPs for the same interface. All right, let's look at adding an extra IP on the same NIC. So I'm back on my Ubuntu VM here. And if I use an MCLI, you can see I have 192.168.51.185 in the /24 subnet. I'm also logged into a CentOS server over here that we'll use to verify the new IP. So the first thing I'm going to do is I'm going to use NMCLI connection modify, and I want to modify the wired connection 1. That's the name of my connection right here. And remember, you can use tab complete to see every single option you could possibly use. Install the bash completion script just to make sure you pick all of that up. But in this case, I'm going to use IPv4.address, and I'm going to give it 192.168.51.190 in the same /24 subnet. So right now, it hasn't taken effect. For that, I'm going to need to bounce the interface. So I'm going to use NMCLI con down wired. Now, a quick note, make sure you're not using a remote session to do something like this, because I'm about to bring the interface down. So the interface is deactivated, and I'm going to bring it back up. So if I use an MCLI again, I see that I have the 192.168.51.190 /24 IP address. So let's ping it from over here on the CentOS server. So I'm going to ping a count of 1 to 192.168.51.190. And it is successful. Everything looks good. So right now, I've not changed from DHCP to static. I have merely added a static IP, which is only going to work so long as I have my information from my DHCP, right? It's pulling in the gateway and the subnet and things like that. All I have done is added a single 192.168.51.190 IP and subnet to my configuration. I can go ahead and add another one as well. So I'll use the exact same command, and I'll give myself 195. I'll have to bounce the NICs again. And now I also have 195 instead of 190. If I wanted to do both, I would use a comma. So 192.168.51.190/24, comma, bounce the interface again. And I now have all three. .190, .195, .185. Let's check and make sure we can ping 190 again. We can. And we'll try 195 as well. And we can. And if we try 196, we get nothing. So in conclusion, we can assign multiple IPs to the same network interface. We can create additional connections and consume those IPs. And we looked at an example of adding additional IPs to existing network connections. This lesson is now complete. Thanks for watching. Hi and welcome. In this lesson, we're going to cover NIC teaming and bonding. We've seen how we can add multiple IP addresses to a single interface, so now let's examine how we can have multiple interfaces for a single IP. The most common use case in my experience for NIC teaming and bonding has been fault tolerance. So take this example. We have a single host with two NICs, and we want it configured so that if either NIC fails, we can still answer to traffic for our IP. This means we want to have a redundant connection, and we can use either teaming or bonding to do this. We could also be doing this for additional throughput, load balancing, link aggregation, broadcasting, etc. But in this example, we're using it for redundancy. And so teaming and bonding are terms that are often used interchangeably, but there are some differences and some advantages. Let's look at the advantages of using one over the other. First of all, teaming supports IPv6 link monitoring. It's able to work with the dbus and Unix domain sockets. It also permits load balancing for LACP support, so that's 802.3AD link aggregation control protocol for increased bandwidth. This would permit you to make use of, say, two 1 gigabit connections instead of a single 2 gigabit connection for the same amount of overall bandwidth in a more cost-effective manner. And teaming leverages Network Manager and associated tools. This one's probably the most compelling for me. So being able to use an MCLI, basically Network Manager, as a single toolkit for all things network related is very efficient in my experience. But let's look at some bonding advantages. It doesn't require a TeamD. This isn't much of a benefit, and bonding still requires its own kernel module to function, so it's in there anyway. It does, however, work in a virtual environment in my experience. So if you're noodling around with VMs and you just want to play around with it, it works. I've not had much luck getting teaming to work in a virtual environment, but it might be something that if I have some extra time, I'll come back to it and work on it and update this lesson with my findings. Let's look at an example. So I'm back in my Ubuntu VM environment. Let's say that we want to add multiple NICs and have them respond to the same IP. So maybe we want this for fault tolerance is a live backup. Maybe we want some additional throughput. Being in a VM environment, it doesn't make a whole lot of sense, but we can assume that this is a physical environment with multiple network cards, and maybe we just want some fault tolerance. So it's the same setup. I have my Ubuntu VM here, and in the other tab, I have my CentOS. So the first thing I'll do is look at an MCLI. And you can see we still have our three IP addresses, 192.168.51.190, 195, and 185. But we also have this new card down here. So we have ENS38, that's the device, connected to wired connection 2. And it has picked up the IP address of 192.168.51.188 over DHCP. So the first way to do this would be through bonding. And to do that, I'm going to use NMCLI connection add. The type is going to be bond. The connection name will be bond 0. The interface name will also be bond 0. And I want the mode to be active backup. So again, if we wanted to see what some available modes would be, we've got these at the bottom: active backup, balance ALB, balance round robin, balance TLB, balance XOR broadcast. In this case, I want to use active backup. We have to give it an IPv4 address, and we'll go 192.168.51.170 in the same subnet. So it's created it. Let's take a look at it. And here it is. We have our 3 connections: wired 1, wired connection 2, and bond 0. Incidentally, we can already start receiving traffic on that IP. So there we go. We received a ping. But we don't have any kind of fault tolerance built in with it whatsoever. We've basically just created a connection. So the next thing we need to do is add the bond slaves to the master bond 0. And so we have these 2 wired connections, these 2 interface devices that we're going to add as slaves. To do that, we'll use NMCLI connection add. Type is going to be bond tac slave. The interface name is ENS33. So this one here. And the master for it will be bond 0. We'll do the same thing for ENS38, which is here. So now if we look at our devices, we see that we have bond 0, as well as our wired connection 2 and wired connection 1. So let's bring these interfaces up. NMCLI con up, and we'll do bond slave ENS33 first and 38 second. And my VM's going to say, hey, you've got some weirdness going on with your MAC addresses. We can ignore that. So if we look at our connections now, we have both slaves are up, bond 0 is up. So let's look in an MCLI. Device show, and we'll look at bond 0. So we can see we have an address, but this piece of information here is missing, this gateway. So we're not going to have any connectivity. So if I try to ping 1111, the network is unreachable. We have to add that gateway. NMCLI con mod bond 0 IPv4 dot gateway is going to be 192.168.51.2. It's the same gateway we've always used. Remember, it's not going to take effect. I'm going to have to bring it down and back up. So now if we look at NMCLI device show bond 0, we should see that we have a gateway. We still don't have any DNS, but we should be able to ping something. And the DNS is probably picked up from our DHCP and left over in etcresolve.conf. All right, so that's bonding. Let's take a look at teaming. The configuration itself is very similar in terms of the creation of the team and addition of the slave interfaces, but there is some nuance. Let's review the default behavior. When you start a team, and I'll use Team 0 as the example, it does not automatically start the slave interfaces. Starting a slave interface, however, will start the team interface. Sometimes I start the team interface anyway, it's just habit. Stopping the team interface will stop the slave interface. Again, sometimes I'll stop a slave interface and then stop the team interface as well. It's just habit. A master without ports, that is slave interfaces, will start static IP connections. The team interface will wait for slave interfaces when using DHCP. It couldn't not, right, because it doesn't have an active connection. The team interface using DHCP completes when the connected slave interface is added, and a team interface will keep waiting if a disconnected slave interface is added. Moving on to team runners. Runners are the modes. If you remember a minute or two ago in the bonding example, I used the mode active backup. It's the same thing. The broadcast runner does just that. It will broadcast everything to all ports, the ports being the slave interfaces. Round robin is the default runner. If you do not specify, you get round robin. This means that it transmits the data over each slave interface in sequence. So for example, if you had 3 ports connected, it would sequentially work through all of them. 1, 2, 3, 1, 2, 3, 1, 2, 3. Active backup, one port is used while the other is reserved. Disconnecting the active port forces the inactive port online. This is the one I've used the most for just general systems. Load balance, active load balancing and port selection. So this can be used for active and passive load balancing. In active mode, rebalancing is done using stats or statistics of the recent traffic to try and keep the traffic load as balanced as possible. In passive mode, the traffic is spread out randomly across all the active links, and this is a little bit faster due to less processing overhead. And lastly, we have LACP. This implements the 802.3AD link aggregation protocol that I was talking about earlier, where you could double your bandwidth if you had, say, 2 1 gigabit connections. Active load balancing is possible using this runner, similar to how the load balancing runner functions. Link watchers monitor the state of the links, and there are 3 different types available. Just as with the runners, the configuration is in JSON format, and I'll show you where to pull some examples for syntax when we get to the hands-on demo here in a minute. The first type of link watcher is ethtool. This is the default, and it just watches for link state changes. The second type is ARP ping. This works just like the utility ARP ping, but it doesn't use the utility, and monitors the available of neighboring MAC addresses using ARP. The last type is NSNA ping. This stands for Neighborhood Advertisement and Neighborhood Solicitation, and it uses the IPv6 neighbor discovery to monitor the neighboring interfaces. If you're using the LACP runner, only ethtool is supported. I do not believe there's anything programmatically stopping you from using any runner with any link watcher, but if you're using LACP, use ethtool. So now that we understand the runners and the watchers, let's create a teamed interface. So for this teaming example, I've logged into a Linux Academy cloud server. This is actually a learning activity server that's going to be coming up as part of this course. And I've sudoed up as root just so I don't have to keep typing sudo. And if I use an MCLI, you see we have eth0, which has its DHCP IP of 10.0.1.11. That is static, by the way. It won't change. And then we have eth1 and eth2, which also have picked up IPs of 13 and 12. So I'm going to create a team using these 2. And the reason I've done that is because if I screw it up, I don't want to lose my SSH connection. So we'll leave eth0 alone, and we'll just be working with eth1 and eth2. One other note, this is an AWS environment. There's asymmetrical routing. There is just all kinds of stuff going on here. And you can see all the superfluous entries in the routing table. If I wanted to get these interfaces to work, I would have to go through and clean up this routing table. However, I would never be able to get the teaming interface to work. Or there may be a way to do it, but since we're in a cloud environment, it doesn't really make any sense to try to do it, so I didn't want to spend too much time going down that rabbit hole. However, if you figure it out, please drop me a comment and let me know. I'd love to see it. So the first thing I need to do, since we're going to be working with a team, is install teamd. So I'll use yum install tac-y teamd. I'm going to go ahead and install bash completion at the same time, just to save me a little bit of typing with tab complete. And everything's good. Let me reload my profile. And we should be all set to go ahead and start creating a team. So if you'll remember, we have these extra 2 connections. I'm just going to blow them away. You don't need to do that. You could leave them out there and just kind of disconnect them and make slave interfaces and tie them to the team, and they would just be out there. But for the sake of cleanness, I'm just going to blow them away. So NMCLI connection, delete, and then we're going to delete wired connection 1 and wired connection 2. So now the only network manager connection we should have is our system ETH0. It's good to go. Let's go ahead and create the team connection. So NMCLI connection add, and the type will be team. And we'll give it a con name of team with capital T, 0, and we'll give it an interface name of team 0 with lowercase t. Now, if I don't specify a runner here, it's going to be round robin. But if I want to specify a runner, then I have to put a little bit of JSON in, or I need to create a file and then specify the file. So let's say I want to use active backup. I'm going to have to do team.config, and then I have to do some JSON. So I will use, let's do runner, and then we'll bracket, and we'll go name, and it's going to be an active backup. And let's give it a link watch. And for that, we will use ETH tool. And if you messed your syntax up here, don't worry too much about it. I mean, I can see that I've used a backtick instead of a single quote over here. I'll show you here in just a sec how you can reference some configurations. So what you can do is you can cat out user share doc teamd and then just tab complete to whatever the version is that you're on. Example configs. And if you hit tab a couple times, you'll see a bunch of these. So maybe we want to look at this active backup ETH tool here, put that in, and you can see your JSON right there. So I just did mine inline. You could just as easily copy and paste this into a new file, edit that file, and then import it using team config and then bring in the file. So we have our team interface here. Let's go ahead and add a couple of slave interfaces. Clear my screen. MCLI connection add. Type will be team slave. Connection name, we could just call it slave 1. We'll do a slave 1 and a slave 2. And the interface name on this one will be ETH1. And then we'll do the, well, we actually have to add the master, which will be team 0. And then we'll do the same with slave 2. So now we have our team 0, slave 1, and slave 2. Now we haven't given our team 0 an IP or anything like that, so it would be set for DHCP if I were to bring it up. But let's go ahead and modify that connection and give it an IP address, a gateway, and set the method to manual. So MCLI connection mod team 0. IPv4.addresses will be 10.0.1.15/24. IPv4.gateway will be 10.0.1.1. And IPv4.method will be manual. So to verify everything looks good, we'll use an MCLI connection show team 0 and grep out the IPv4 parts. And we can see our method is manual. We see that our IP address is good. Our gateway looks good. So we should be good to bring it up. Now, the right way to do this would be to bring the slaves up and then bring the team up. You can bring the team up and then the slaves up, but things can be a little bit inconsistent. So I'm going to go ahead and bring the slaves up first. An MCLI connection up, and we'll bring up slave 1, and we'll bring up slave 2, and then we'll bring up team 0. So MCLI now, and we can see everything is there. Here's our ETH0, the one we're not messing with. And here's our team, 10.0.1.15. We can ping it. And it works. So there again, because of asymmetrical routing, if I were to try to ping and force the interface of team 0 and, ping 1.1.1.1, it's not going to work. The ping will go out, but it doesn't come back on the same interface. And that's where things get a little weird, and it doesn't really make any sense to be doing this in AWS. But if this was a physical host, this would make perfect sense, particularly if you had 3 NICs and you had one that you would use as a management interface and then the other 2 for application delivery. So we can also look at team D control, at the state of team 0. And we can see that it's active back up, and we don't have any active ports. So let's blow this one away and do one round robin style real quick. So MCLI connection delete, and we'll delete team 0, and then we'll delete the slaves. A lot of typos today. So now we're just back to system ETH0. I'm going to restart networking just to clear out everything. And we just have our one connected interface ETH0 maintaining our SSH session. So for round robin, I don't need to specify runner. So everything will be more or less the same. MCLI connection, add, type team, con name, team 0, interface name, lowercase team 0. And then we can connection modify. And add our IPv4 address, 10.0.1.15/24, and our IPv4.gateway, 10.0.1.1, and our IPv4.method. Since we want this to be static as manual, now we need to go back in and create a couple slave interfaces. And MCLI connection add, type team slave, con name, slave 1, interface name ETH1. We need to specify the master. And do the same for slave 2. And this time we'll do it backwards. We'll bring up team 0. And then we'll bring up the slaves. We can see everything is there. And we have our IP 10.0.1.15. We'll ping it. So I can talk to itself. We can take a look in Team D control. We can see that we're round robin and we have specified the links. If active backup was working, we would have seen 2 links here as well as the link that was active. But like I said, in a abstracted virtualized environment like this, that just doesn't make any sense whatsoever. Again, this isn't going to work if I were to try to ping and force the team 0 interface and ping something like 1.1.1.1. It'll go out, it just never comes back due to asymmetric routing. That's a teamed interface. So let's wrap up. Teaming and bonding are similar, but teaming does have some advantages. I would say if you're on the fence between using one or the other and it's physical hardware, definitely use teaming. If you are on the fence using one or the other and it's kind of a virtual or AWS environment, first of all, asymmetric routing is going to get you in AWS, and probably bonding is the only thing you're going to get working in a virtual environment. But for real-world production use cases, I would use teaming. We looked at an example of bonding multiple NICs, and we looked at the example of teaming multiple NICs. And I have talked a little bit about there is some nuance to the teaming behavior. Those are the default behaviors. You can go back and rewatch. You really should understand that or just be prepared to do it twice, kind of like I do. So I bring up the team interface and bring up the slave interface. I bring up the slave interface and bring up the team interface. It takes a couple seconds. This lesson is now complete. Thanks for watching. Hi and welcome. In this lesson, we're going to take a deeper look at routing, in particular static routes. So let's jump behind the command line and get started. So I'm logged into a cloud host here, 10.0.1.10. This is a CentOS 7.5 server. And I can use the command route-tac-in to show my routing table. And a quick note, route is a deprecated command, kind of like ifconfig and netstat. The new way of doing this would be to use iproute-show or just IPR. And we can see we have our default gateway at 10.0.1.1. And for the 10.0.1.0/24 subnet, we don't use the gateway. So really just two entries. So aside from using static routes to make something reachable, you can also use static routes to make something unreachable. And the three most common ways of doing that is either through a prohibit, where the kernel generates an ICMP prohibited message, or through black hole, where it just gets discarded, or through an unreachable, where it generates an ICMP unreachable. And so, for instance, if there was a certain site that you did not want accessed from this particular host, you could use the iproute add prohibit IP or even whole subnet command. So let's look at an example of that. Let's say we do not want this host to be able to access Cloudflare 1.1.1.1. And I'm just picking on that because it's such an easy IP to remember. I can use iproute add, and we'll just use prohibit 1.1.1.1. And now if I try to ping 1.1.1.1, you can see it's not going to work. It's suggesting using a ping broadcast. Or if I try to curl the header of 1.1.1.1, because I know it's a website, we get this permission denied. And so these changes aren't going to be persistent. Some of these will persist through a network restart, but they're not going to persist through a system restart. If I wanted these to persist through a system restart in CentOS, I'd have to modify or create the static file in etc sysconfig network scripts, and then create static routing files there for the interfaces I want static routes to exist on. And so right now we just have the one interface. We just have ETH0. There is an ETH1. It's disconnected though. So to get rid of that, I can use iproute flush 1.1.1.1. And then if we go back and try to curl, we get it. And if we go back and try to ping, it's going to start pinging and responding. So again, I could have used prohibit. I could have used black hole if I didn't want any kind of feedback whatsoever. And I could have used unreachable to just have the ICMP unreachable come back. Now let's say that, let's go ahead and bring up the second interface, an MCLI connection up wired. So now if I do my IP route, you'll see we have, an extra entry for the other interface, ETH1 in this case. We can add a static route for a particular interface. So let's say I wanted 1.1.1.1 traffic to go out and come back through ETH0. I can use iproute add 1.1.1.1 via, and I'll just use an IP I know won't work, dev ETH0. So rather than sending it all out through ETH1, it's all going to go out and come back through ETH0. So if I run ping again, it's only trying to do it through ETH0. And if I run the curl again, it's only trying to do it through ETH0. And using 10.0.1.10 as the gateway. So let's look at the routing table again. And you can see why it's broken. I'm sending it out via 10.0.1.10, so that's myself on ETH0, so of course that wouldn't work. But if 10.0.1.10, we'll just say it's not my IP, let's say we used .20. If 10.0.1.20 was a gateway, then all traffic to 1.1.1.1 would go out through that gateway over ETH0. So let's flush that out again, and we'll just use IP route flush 1.1.1.1, clear our screen, And let's look at a couple of other examples. So let's go back to the example I was working on here. And instead of our own IP and that NIC, let's use ETH1. So we're saying add the route to traffic to 1.1.1.1 via our actual default gateway, which in this case is 10.0.1.1, over device ETH1. And so if I use an MCLI, you'll see that that route now shows up under ETH1. So let me clear my screen. If I try to ping again, 1.1.1.1, and we'll just do a count of 1. It's trying to go out. It's not going out. And if I try to curl that header again, it's not going to work because clearly there is some asymmetrical issues, routing issues going on with ETH1 that I would have to resolve in order to get that to work. Or rather, there is some manner of connectivity issue going on with ETH1 that needs to be resolved before we could use this. So let's flush that again. And interestingly enough, I bet that if we ping and force the ping to use interface ETH1, the ping's not going to work. There it is. And that just confirms that we do have some kind of issue going on that we need to resolve before we could send all traffic through that. Let's go ahead and just take that interface back down. And so now we just have our regular interface up, ETH0. And if I look at the IP routing table, we're back to just having our default and then our local. So let me clear my screen one more time, and let's go back and run our curl. And we're functional, and we'll run our ping. And we need to run it without specifying ETH0, or ETH1 rather. And so we're back to connectivity to 1.1.1.1. So let's break it a different way. Let's say that we want to add the route so that traffic for 1.1.1.1 just goes through 10.0.1.20. And so then we would have to move over to 10.0.1.20. We'd have to set it up to NAT. We'd have to set up to masquerade and IP forward. And since this is an AWS environment, we would have to do a lot of that configuration actually in the AWS console, not on the Linux host itself. So in this case, we're just going to break it as an example, and I'll use IP route add 1.1.1.1 via 10.0.1.20. And so what's going to happen now, let's clear the screen, is if I go back to ping, it's not going to work. And if I go back to my curl, it's not going to work. And so what I'm hoping I'm demonstrating here is how you break things with static routing so that maybe you'll understand better how to resolve things through static routing. An example of that is if we look back at our routing table, if you're on a system and you are unable to access it and you only have your two routing entries, right? Your default through the gateway and then your local subnet, and this entry or this IP happens, maybe it's a class B or a class C or it's some kind of a private IP, then you probably need to go through a different gateway other than your default gateway to get to that IP. And so you'll have to contact somebody who is more familiar with your network architecture, or at least you yourself look at your network architecture and say, okay, where's the router for this? And then you could add the entry, let's say it's 10.0.8.0 or something like that. You would add the entry 10.0.8, or rather you would just go IP route add 10.0.8.0/24. And that gateway would have to be multi-homed as well on your network. So maybe it's 10.0.1.55. And of course, I'm going to get back garbage because that's not legit. Or rather, I forgot to put the via to say that it's the gateway. And so now I'm saying for all my traffic to the subnet 10.0.8.0 in that subnet /24 subnet, send that to the host 10.0.1.55 because I'm identifying 10.0.1.55 as the gateway or the router for the 10.0.8.0/24 subnet. And again, if I wanted to make this route persistent, I would have to create or edit the etc sysconfig network scripts, and this is CentOS. And then it would be route tech eth0, and I'd drop my route in there to make it persist. That wraps up this lesson on static routing. Thanks for watching. Hi and welcome. In this lesson, we're going to take a little closer look at troubleshooting routing issues in Linux. Routing issues typically show up when you're setting up a new component in the network or when something's failed like a NIC. Otherwise, routing issues are normally caused by some manner of configuration or design error, and troubleshooting can be tricky as the normal tools like traceroute and ping don't really give you the information you need. I tend to lean on curl when I know that the IP resolves to a website, as ICMP is commonly blocked. If you're using IP tables for complex natting or masquerading, troubleshooting is something we're going to cover in that section, as there's a specific order of operations to keep in mind when untangling that kind of mess. So for the scope of this lesson, we're going to keep it at the routing table level on the local host. Let's get started. So as a bit of an extension of the last lesson and a little bit of a refresher, it's important to keep in mind that you can set your routing table entries to go through specific NICs. So I'm on 10.0.1.10. The only other host in this subnet is 10.0.1.20. And .10 here, the host I'm logged into currently, has two NICs. It's got .10 and then it's got .11 on eth1. And they're both on the same subnet. So let's say I want to set all of my traffic to .20, the other host on this subnet, to all go through that second NIC. So since the first NIC is natted to my public IP, maybe I want to use this for all private traffic. It would be as simple as using IP route add, and then we're going to specify 10.0.1.20. So all traffic to 10.0.1.20, just send it through device eth1. And, I could have tested this first, but, I would want to ping and then force the interface eth1 and make sure that it worked. It does. So now if I just do it without specifying the interface, I'll be able to have some connectivity. And so now if I take a look at my routing table, and I'll use IP route show or just IPRS, we'll see that we have at the very top default via 10.0.1.1 device eth0. So that is our primary route. That is our gateway. So everything goes to 10.0.1.1. And then there are exceptions beneath that. So we have a default gateway for both interfaces, both NICs, and then we have the local subnet for both NICs. So 10.0.1.0/24 device eth0. We just use our own NIC for that, or our own IP, 10.0.1.11 or 10.0.1.10. We do not need to send that to any kind of a gateway because it's on our local subnet. Beneath those two entries, we have 10.0.1.20 device eth1. So that is all traffic to 10.0.1.20 go through eth1. And like I mentioned earlier, maybe it's because eth0 is natted to our public IP and we just want to balance traffic a little bit better by sending that internal traffic over eth1. So if that NIC, if eth1, the NIC went down, I would no longer be able to get to 10.0.1.20. And we can simulate this by using IP link set eth1 down. And now if I try to ping 10.0.1.20, it's going to fall over to eth0. So if I look at my routing table again, we see all of those extra eth1 entries are gone. However, if they exist in etc sysconfig network scripts static config files there, then those entries would be put back in place when eth1 came back online. And so I'll bring this up because if eth1 was connected to the network, the only network that was reachable through eth1, then eth1 going down obviously is going to break connectivity to all destinations that were using eth1. And in my example here, eth0 happens to be on the exact same subnet as eth1. So connectivity didn't break, but it would break in your example if, say, you had two different subnets, each connected to a different NIC, and you had established routing to go through one or the other. So let's say that instead of 10.0.1.20, it was 10.0.8.20. And ETH1 had the IP of 10.0.8.10. Now ETH0 here at 10.0.1.10 is not in that .8 subnet, so it would not be able to reach it. The ping would have failed. So let's look at a couple of other examples. Let me clear my screen again. So as a few more examples, I have populated the routing table with some extra entries, and you can see at the very top you have your default via gateway. And then we have our local subnet, and we've got there's a superfluous entry there that's an artifact from having removed that first NIC and not bouncing networking. And then we have some static routes to specific IPs, and these could be subnets, but in this case, they're specific IPs. And so one of the tools that you can use to assist with resolving these IPs, and you should remember this from our DNS lesson that's coming up, is install bind utils. And that will give you access to the host command, which we can then use to see what some of these IPs are. So I happen to know what they are. And so let's say we want to curl the header of example.com. And it just locks up. And we try to ping example.com. And it just locks up. Well, we can use host example.com and see that example.com has the address 93.184.216.34. And if I look at my routing table again, I see an entry 93.184.216.34 via 10.0.1.20 over device ETH0. And yes, I know the ping command gave back the IP, but NSLOOKUP was what I was thinking of in terms of resolving IPs to host names. Now, since this is a publicly accessible website, and I know that device ETH0 is able to reach through its default gateway the internet in general, there's no reason for it to be going through 10.0.1.20. And whatever reason did exist doesn't matter now since it's unreachable anyway. And so I can use IP route flush 93.184.216.34. And I should now, let me clear my screen, and I should now be able to go back and curl example.com, and I can, and we'll ping it as well. And we'll just do a count of 1. So that's an example of a entry in a routing table that is just going to cause problems. It was, first of all, it was dependent on 10.0.1.20, which isn't even set up as a gateway. It's also dependent on the ETH0, which is fine because if ETH1 were to come up, it would fall over. But on most hosts, you're probably only going to have one NIC, or if you have multiple NICs, it's for redundancy, unless you've set it up as a gateway of some sort, which is beyond the scope of this lesson. And unfortunately, not something that I can do in an AWS EC2 environment, or at least I could do it, but the vast majority of the configuration would be in the AWS console and not at the Linux level itself. And so I'm trying to stay focused on Linux networking in particular. I will mention you'll want to be careful with that flush command. You do not want to blow away your entire routing table because that's going to break connectivity to your host. So in terms of troubleshooting static routing and your routing table, make sure you're using it in a manner consistent with with good design. That is, routing entries should be there because they're absolutely necessary. Other things that you can run into that are bigger than the scope of this lesson would be like policy-based routing and in Cisco routers in your environment and that sort of thing. Unless you can log into the switches or the routers themselves, you're probably not going to have any kind of visibility or transparency into what's going on there. VPNs can also throw a little bit of a monkey wrench in there, especially if they're like split tunnel VPNs and that kind of thing. But normally they're not too hard to work with or figure out. Where they'll mainly get you is when you can't resolve an organization's, say, an external IP from the internal network and things like that. That's where that starts to come up. So I hope by this point you have a pretty good grasp of the local routing table, what the routing table is used for, how to use static routes, how to use or how to define all traffic going through individual NICs, that kind of thing. This lesson is now complete. Thanks for watching. Hi and welcome. In this lesson, we're going to talk a little bit about local domain resolution and how we can make use of it. So let's get started. I'm logged into my Linux Academy Learning Activities server here, which is a CentOS 7 installation. And since we're going to be working with DNS, I'm going to install some tools. I'm going to install the bind utilities. So bind utils. And so bind utils is going to make use of the libresolve backend, which means it's going to use DNS for everything. Things like ping and a lot of everything else uses get host by name or the newer get address info. So that's something to be aware of. So I've got the bind utils installed. Let's talk about the use case for a minute. And we're going to be using the domain LA Toys. And so let's say we have some developers and this is an application host and they don't want to bother with not hard coding in domain names and things like that, and they want to be able to test and then put in production without having any kind of modifications. So it's not something I would recommend, but it comes up, it happens, and it's probably one of the least nefarious things I can think of in terms of why we would do this. So the first thing we'll do is we'll look at LA Toys, and I'll just use the host command, and we'll see what exists out there. So latoys.com resolves to 50.116.32.190, and I'll also use getint. Since host is definitely using libresolve and getint, we'll use get address info or get host by name. I can't remember which, but it's the other one. It doesn't use DNS for anything. And we'll look up against ahosts, latoys.com. And we can see it's the same information, 50.116.32.190. And then lastly, let's curl the headers for this site, latoys.com. And we can see that the server is Apache 2217, and the E tag starts with an 8 and ends in a 0. So let's change local resolution. Let me clear my screen. And I'm going to cat out etsy nsswitch.conf, and let's grep for host. And you can see here in the host line, we have files, DNS, and my host name. So what this means is it's first going to look in files for hosts when it does resolution. It's going to look in Etsy hosts. Then it's going to query DNS if it doesn't exist in Etsy hosts. So let's modify Etsy hosts. And let's add the entry 10.0.1.10, and we'll call it latoys.com and save. So now if I clear my screen and we perform the getint against ahosts for latoys.com, we are our local IP 10.0.1.10. However, if I use host latoys.com, it's still going to come back with the real one because we're actually using DNS. This came with the bind utils, so it's going to use DNS. And then lastly, let's curl the header. And we get a connection refused because we don't have HTTP running. We can install it real quick. So we'll install it and then we'll start it. And then if we rerun that curl, we can see that we are now using Apache 246 instead of 222 or whatever it was on the legitimate one. So if we wanted to do a name server lookup, or if we want to do a DNS lookup, we could use dig latoys.com, and we see that it comes back at 51.16.32.190. And the host that answered that was 10.0.0.2, which should be somewhat familiar if we use nmclid and then grep for DNS. We will see, well, we'll have to add show, and we will see our IP4 DNS entry is 10.0.0.2. So let me clear that out and go back. Let's redo curl, and we can see that we're on 246. Let's redo host. And we can see that it's legitimate. And let's redo getint. And we can see that it's 10.0.1.10. So let's go in and reverse the order in nsswitch. So I'll just copy and paste there, and then I'm going to go in here and we're going to move DNS in front of files. So now if I retry host, it's going to be the same thing. And if I retry get int, it's going to be the correct one because we're now looking in DNS instead of files. And if I retry curl, it's going to be back to the original because we are again looking through DNS instead of files first. So that wraps up how you can go in and modify local name resolution. In the next lesson, we'll set up a name server and actually go in and do this in a more legitimate manner. But for now, this is just a quick and easy way to get your own host to resolve itself internally to whatever domain you like. We could have changed it to Google, LinuxAcademy.com, whatever. So one other thing you could do with this would be to mirror a web page. So if I go to cd var html, and I don't think I have wget, so I'll have to install it. And we will just wget example.com. And we have www.example.com. Let's move the index up a level so that it's at the root level now. And so if I yum install a text browser like Lynx, I now should be able to use Lynx. Well, first, let's go in and curl taci example.com, and we can see that it is, the E tag starts with a 1 and ends in plus gzip. So definitely not our local host. We're still set to use DNS before hosts, so let's fix that. Now we're back to files, and now let's edit etc hosts. And let's add the entry 10.0.1.10 example.com. So now if I curl taci example.com without a typo, we see it's totally different, right? We've got a completely different E tag. And if I use the link browser, then we can see that a little bit of the script broke. And it's the first time we've loaded it, but it's the example.com website, right? This domain is established to be used for illustrative examples and documents. So that is one other use case that you could have, is to mirror a website locally. You'll just have to make sure that when you use wget, you pull in all the requisite site assets and cross-site assets and things like that. And you can still expect some things, JavaScript and stuff like that. Certain things will still break, but it's just one more thing you could do. This lesson is now complete. Thanks for watching. Hi and welcome. In this lesson, we're going to look at setting up DNS hosts as name servers. Let's get started. Before we get too far, let me break down a sample architecture. I'll be working with 3 hosts: Server 1, Server 2, and Client 1. Server 1 is connected onto ETH0 with IP 10.0.1.10, and this is going to be our primary DNS server. Server 2 will have 10.0.1.11, and this will be our secondary DNS server. And finally, Client 1 will have 10.0.1.12, and this is just a client for testing. These are all on the same subnet connected to a switch, and in this case, I'm using AWS EC2 instances, so the switch is just implied. We'll connect to our default gateway, so this is our default route, and then off to the internet. And somewhere outside of the local subnet is the DNS host assigned by DHCP. The domain we'll be using is example.com, and this is a domain reserved for use in example use cases like this. And let's assume for a moment that example.com is our domain and we own it. We would need to update the settings in the registrar control panel to point it to our own name servers. Now we could go into the registrar's DNS settings and add an A record for our site or whatever, and we can modify the records there while keeping the registrar's name servers associated with the domain. But if we want to take full control of the DNS of our domain, we need to use our own name servers. And to do so, we'll need to create a minimum of 2 name servers. Now, this example isn't best practice, as both name servers are on the same network in the same location, and ideally you would want to have some degree of separation between them. And so for this example, you would want your name servers to be publicly accessible, so ns1.example.com would need to be reachable from the internet. Likewise, ns2.example.com. In this example, my internal IPs are mapped to public IPs. However, I have blocked external DNS traffic, as this won't be a secure implementation, and it's merely for illustrative purposes. All right, so just like in the sample architecture, we're going to use 10.0.1.10 for our primary DNS server, 10.0.1.11 for our secondary, and 10.0.1.12 for our client. The first thing we need to do is set up our server. There are a couple ways we can do this. The 2 primary applications for providing DNS service are Bind, which is kind of your old school classic name server or DNS server application, and then a newer one called Unbound. Whichever you use is up to you. You have to really be diligent about securing either one, particularly Bind. And some find Unbound to be a little easier to configure, but in this example, I'm going to use Bind. So in order to do that, I'm going to have to install it. I'm going to use yum install, and we'll install bind utils. Let's go ahead and grab network manager and bash completion. I love bash completion. So while this is installing, let me touch on security a little bit. The manner in which I'm going to configure this named or bind server is not secure whatsoever. In fact, it's the bare minimum of security. And I wouldn't do this on my home network. I certainly wouldn't do this on a corporate network to provide production name services. At a bare minimum, I would be using a jailed environment. So I'd install the bind root package, and I would be creating some keys, and I would do a whole lot more than the bare minimum, which is what I'm doing here, just to illustrate the whole NS1, NS2 client sort of relationship. So we're installed. Let me go ahead and source Etsy profile. I don't know if I need to source Etsy profile or Etsy bash RC or .bash RC, but I've always just used Etsy. And that immediately applies the bash completion to my session. So the configuration document we're going to be working with is under Etsy named.conf. You can see it here. And there are examples of this. And the syntax is a little funny, and this isn't something you normally go in and you change an awful lot, so it's not syntax you're probably going to remember. So let me show you where you can see it. And for that, we're going to cat user share doc bind tac9 or whatever version of bind you have installed. Sample Etsy named.conf. And so the part that we're going to look at is right here where we're adding zones. So it's zone, the zone in parentheses, and then the type is going to be master or slave. The file where that zone information will be found, and then you can determine whether you want to allow update or not. And if we go up here to the top of the file, you can see the options, as well as the port that you're listening on, the interfaces, or the IPs rather, that you're going to permit connections on. So that's where you can find that. So let's go ahead and edit our actual one. And so the first thing I want to change is right here. We're listening on the loopback, and that's okay, but that doesn't really fit our purposes. We have to listen on our primary IP. And I want to limit queries to just our local subnet, so 10.0.1.0/24. I do want to allow transfer to the secondary DNS, which in this case will be 10.0.1.11. And then I'm going to turn off recursion. Like I said, this isn't even, I'm taking the softest, lightest pass at any manner of security on this. Do not do it like this. This is purely academic. So then we want to go to the bottom of the file here and add our zone information. So right after zone dot, in this case, we're going to use zone example.com. It will be internet, and we want our type to be Baster. And then we'll reference our file. And so our file name will be forward.example.com. And you can call this whatever you want. You just have to remember what you called it. And I want to set allow update to none. And then close bracket. And then we're going to do the same for our reverse record. So in that case, our zone will be 1.0.10 intechadder.arpa internet. Type is master again. Our file in this case will be reverse.example.com. And we want to set allow update none. And close our brackets. So that should do it for configuring this file. And there are a couple ways we can look at the syntax or do some syntax validation. One is to just try to start named. It will spit back at you what line is acting up. But we can also use named check conf and run it against the file. And we can see that we have something missing on line 19. So if we go here to line 19, we can see that we forgot our semicolon here at the end of the /24. So that file is good to go. Let's clear our screen and go ahead and add our zone files. If you remember, we used forward.example.com and reverse.example.com. So let me show you where you can see the syntax for these files as well. And it's in the same place, user share doc bind tech 9 examples, or rather sample, and then in this case we want var named. And let's just use named.empty. And so here we have a TTL declaration of 3H. That's 3 hours. This is the time to live. It's the length of time, typically in seconds, but in this case it's specified as hours, that this resource record is valid. And then each resource record could have its own TTL value that would override whatever's up here. So why would you increase this? It would allow remote name servers or DNS hosts to cache the zoned information for a longer period of time. This would reduce the network traffic back and forth in terms of making those DNS lookups for queries. It would also lengthen the amount of time for propagation. And so that's the exact same reason or the converse reason as to why you would decrease it. You want faster propagation, or you want the queries to be more fresh. So then this @ symbol here stands for origin. So in this case, it's the zone. And so if this was example.com, this would stand for example.com. So it's internet start of authority. The start of authority is this proclaims the important authoritative information about a namespace to the name server. And so it will refer to the name server's server record, which announces the authoritative name server for the particular zone. In this case, it's going to be @. And then of course you have your loopback. This is not an actual thing. Just use it for syntax. So you'll have a serial number. This is something you want to increment every time you make a modification to the file. So you add new A record, you drop a CNAME, things like that. And then likewise, you can set refresh time, retry time, your expiration, and then your minimum TTL, which is typically set to the TTL up here. So let's create this file, vim var named, and we use the file forward.example.com. And I'm just going to drop some copy and paste in here. So in this case, our TTL is 86,400 seconds. That's the same as 1 day. Our SOA is ns1.example.com, server1.example.com. So that is this host that we're on right now. Serial number typically follows a date, then refresh, retry, expire, minimum TTL are set. We've declared our name servers here, ns1.example.com and ns2.example.com. Real quick, do not forget to add the period at the end of here, because that will cause you all kinds of problems. It's basically going to append that to whatever. So without that period, it's a subdomain. So this would be seen as ns1.example.com.example.com. And I've got some A records in here. These could be, well, NS1 could be a C name, NS2 could be a C name, but I'm just using A records for simplicity. So server 1 is going to map to 10.0.1.10. That's this host right here, just like NS1. Server 2 will map to 11, NS2 the same, and then client 1 will be 10.0.1.12 right here. So we'll save this file, and we're going to do the same for that reverse.example.com, which is the PTR record. And this file is going to look the exact same up till about right here. So 10.0.1.10 is going to map to server1.example.com. So this does the reverse of DNS, right? It says, all right, give me the IP, or give me the host name for the IP, and maps it back. And so .10 will be server 1 and NS1. .11 will be server 2 and NS2, and then 10.0.1.12 will be client1.example.com. And so just like we did with the other named config check, we can config check these as well. So named check zone, and we're checking the example.com zone. And those files are var named forward.example, which looks okay, and reverse.example, which looks okay. So at this point, we are good to enable named and go ahead and start it. And if there's anything wrong with our configuration, even despite the fact they passed this syntax check, it'll still break on you if you're not careful. So if I've typed a directive incorrectly, the syntax wouldn't pick that up. So let's go ahead and system control enable named and system control start named. And we're good. So right now, bind is running, and we can do some verification. So let me clear my screen again, and let's just do a dig example.com. Remember, we're not using ourselves for our own DNS. And so we see that here is our question, give us example.com. Here's the answer, example.com has an A record for this right here. So now if I do a dig at localhost. So now we're asking our own DNS host ourselves for example.com. And we see, hey, give us example.com. And it comes back and says example.com, the start of authority is ns1.example.com, server1.example.com. So it is functional. And since we did not have anything in there for the root example.com, we would have to have gone in and put in an @ for origin down where we were adding the A records. And we could have had example.com resolve here as well. So the last thing I want to do before we move on to the secondary DNS or the client is we want to check and see if we have a firewall running. And let's check IP tables and firewall D. And yes, firewall D is running. So I'm going to use firewall command, permanent, add service, and we're going to add the service DNS. Now we have to reload our firewall. And we should be good to go. Let's move on to the client and configure the client to use this for its DNS. All right, so I'm logged into the client now, and I want to use the new host as DNS. So bind utils already comes installed on this host. So I'm going to do a dig at 10.0.1.10 and look up server1.example.com. And we can see that here's our question, server1.example.com. Give it to me. Here it is, 10.0.1.10. So we should be good to go. And if I cat out etc resolve.conf, you can see that we have the DNS lookup domain or search domain for ec2.internal, and our name server is 10.0.0.2. This is what we picked up via DHCP. We need to set our IP for static before we can go ahead and change DNS. So let's see if Network Manager is running. And it is not, so let's start it. And let's also enable. And let's also install bash completion. Okay, so we're good to go. We can use msli. We have 10.0.1.12, that's fine. Here's our DNS information here. 10.0.0.2 and EC2 internal, that's what we want to change. NMCLI connection mod, system ETH 0, we've got to pull it from right here. And we're going to set IPv4.method to manual, IPv4.address to 10.0.1.12/24, IPv4.gateway to 10.0.1.1. And we're not going to set DNS yet. We're just going to set it like this. And we need to restart networking because we can't bounce the NIC. We're connected to it. So now if I do an MCLID show, we should see no DNS is provided whatsoever. So if we cat out etcresolve.conf again, we just have the search domain, so we'll blow that away. All right, now we're good to go. We have a nice clean slate. We have a static IP. We don't have any DNS set. If I were to try to ping server 1.example.com, it's going to come back with name or service not known. It's not. So let's get some DNS. An MCLI connection modify, system ETH 0, IPv4.DNS will be 10.0.1.10. And we can go ahead and do IPv4.DNS search and add example.com. We have to bounce networking again to pick up this change. And so now if we ping server1.example.com, it at least resolves. ICMP is blocked here, but it does resolve it to 10.0.1.10. And if we were to try to ping just server1, we can see that it also resolves because we have our search domain. So we've configured our server, we've configured our client. Now all we have to do is configure the secondary server. All right, so now I'm logged into 10.0.1.11. This will be our secondary DNS host, and it's the same drill. We're going to have to install bind utilities, etc. So yum install tech-y bind utils. Let's go ahead and grab network manager, bash completion, and I think that should be enough. And so again, you know, I know I'm harping on it. This is just not a secure way to set up a DNS host. This is purely academic, and you're probably getting tired of me bringing that up. But just trust me, this is something you're going to want to spend a whole lot more time familiarizing yourself with and getting up to speed on how to have a secure DNS server installation. And it's installed, so same old drill, source etc profile. And we'll clear the screen. Okay, so we have bind utils installed. We know what we have to do. We know what files we have to modify. So let's go ahead and modify etc named.conf. And again, we need to change the IP here to 10.0.1.11. That's our IP. Let's not forget the semicolon this time. We'll allow queries to the local subnet. We're going to turn off recursion. And then we're going to go down here to the bottom, and we're going to add our zone information. So this is going to be very similar to when we set up the master or the primary DNS host. We're going to use zone example.com internet open bracket. And in this case, we're not going to do type master, we're going to do type slave, and our file is going to be in slaves. So this is the var named is kind of implied. So our file is going to be var named and now slaves example.com.forward. And then we're going to specify our masters. And with this case, it'll be 10.0.1.10. and close our brackets. And then we're going to do the same thing for the PTR. So zone 1.0.10.intechadder.arpa. Same drill, type slave. Masters will be the same thing. And then close our bracket. So we know we can use named check config, and everything looks good. We don't need to do anything else at this point in terms of configuration. So we have set this up to basically pull the zone information from our master and then store that information under var named slaves example.com.forward and .rev. And since this host is using the same CloudFormation script, I'm going to have to make that firewall exception. So firewall command, permanent, add service, DNS, and then firewall command, reload. So at this point, we ought to be able to go back to the client and then point it at this secondary DNS and have it resolve for us. But we can check local resolution as well. So dig at localhost, and we'll just pick on server1.example.com. Oh, we haven't started bind yet. So let's enable named, start named. Try our dig again, and we're good to go. So let me get out of here and jump back into the client real quick. Before I jump off the secondary DNS server here, you can cat out the files in var named slaves, and you can see there's some data here. So that's one way you can make sure that you're getting the zone data. So onto the client. All right, so I'm back in the client. Now we can update the DNS to point to the secondary name server. But we can also verify it with a dig at 0.1.11 because primary is 10, this one's 11, and then the one we're on now, the client, is 12. And we'll do server1.example.com, and we're good to go. So if we wanted to, we could update our DNS to use this one. Again, it's insecure. However, if we were to put the primary name server, somewhere not accessible to the internet, only able to be queried by a particular subnet, apply the firewall rules, make sure it's in a jailed environment, make sure we're using keys to move things back and forth. Go in and make sure that we're not providing a bunch of extra information. We're just providing the minimum information. And then interact with our clients, interact only with the non-master host. It would be a little more secure. We followed the sample architecture exactly. This lesson is now complete. Thanks for watching. Hi and welcome. In this lesson, we're going to jump into troubleshooting DNS issues. So a quick review. We've looked at the DNS query itself in some detail. We know what it takes to achieve local resolution, and we've even set up our own name servers, and I'm not going to say another word about security around those. So I think we have a pretty good foundation for troubleshooting DNS issues like the one in this intro. Let's go back and look at it. All right, so I am logged into one of my Linux Academy cloud hosts, and this is just one of the 6. And so the first thing we need to do is a little bit of local troubleshooting, and then we'll go into some server troubleshooting, and then we'll go into some verification. So in terms of local troubleshooting, I know that I have network connectivity because my SSH session is working. So let's try to curl a couple of host names. So we'll curl the website for linuxacademy.com. All right, that's no good. Could not resolve host linuxacademy.com. So that tells me something's up with DNS. Let's try example.com. Failed to connect on port 80. Connection refused. All right, something is definitely up. The first thing I'm going to do, and you can usually skip this step, but I like to do it anyway, is I'm going to cat out etc ns switch and grep for hosts. And so I see that we're looking in files first and DNS second. So let's cat out our etc hosts. So there's example.com. So that explains why example.com resolved and gave me connection refused, because I'm clearly not running a web server on this host here, or at least 172.31.141 is not, and that happens to be my IP. but it doesn't explain why linuxacademy.com didn't resolve. Now, obviously, I could put linuxacademy.com in here to some IP and it would resolve, but that's not going to fix our issue. So let's get rid of that extraneous example.com. Okay, the next step I'm going to do is I'm going to look in etcresolve.conf and see. So we do have a name server specified, 172.31.0.1. So we have our name server in there. However, resolution's not working. So if I try to dig linuxacademy.com, we're going to get this connection timed out. No servers could be reached. So there is clearly an issue with our DNS server, 172.31.0.1. So we know from setting up our own DNS hosts, those name servers that we set up, that they listen on TCP port 53 and UDP 53. So let's verify that it's listening on TCP 53. And for that, I'll use telnet 172.31.0.1, and I'll specify port 53. And it doesn't look like it's working. It would have connected by now if it was. So clearly that DNS host is non-functional. It's not on our same subnet, so we can take a look in the routing table and see if we have a special route for it, and we don't, so we're going through our default gateway. So it may be on a route that we just haven't entered and we're not aware of, or the server itself could be down. Either way, without any additional documentation, we're not getting to this host. Now, another thing I'll mention that can happen is that if you have cluster DNS and it's in round robin and one node fails, the other node isn't aware that it's working by itself. And so you can get into some issues like this, but that's kind of an edge case. So from this point, what we need to do is try public DNS. So we could use Google's DNS 8888 or Cloudflare 1111. So let's just ping 1111. I know that it permits SCMP, and we can reach it. So then we can dig at 1111 linuxacademy.com. All right, great. So we're getting an answer right here. Here's the question, give us linuxacademy.com, and then here are the 3 IPs. And if you remember from when we looked at them in Wireshark, the whole DNS query, that looks right. So at this point, we can edit etcresolve.conf. We can swap to public DNS until our existing DNS is restored. However, public DNS isn't going to have any internal records that we may need for internal resources like database hosts, our ERP, things like that. For that, we would need to get the internal DNS host back up to a sane state, and this is also why we typically have multiple DNS hosts, primary and secondary and so forth. So in my documentation, I see that I can use 172.31.0.2 as my secondary DNS host, so I'm going to swap over to that. And I'm just going to change this 1 to a 2. And so now let's see if linuxacademy.com resolves for us. Great, perfect. So we did a little local troubleshooting, and then we did a little bit of DNS server troubleshooting. We verified that it was definitely our DNS server that was the problem. Now, I'll mention sometimes forwarding can be broken, and so that's something to watch out for, where your DNS server is working and it's responding to queries, but it won't forward. So you're able to get the internal stuff, but none of the external stuff. So something internal would work, but Google or Linux Academy wouldn't. So in this case, we narrowed the issue down to the one local DNS host. We swapped over to another. Now, some other troubleshooting you can do is in terms of getting authoritative information. So if you look here at the diglinuxacademy.com that I just did, you'll see that the authority is 0. So this is not an authoritative response. So let's dig, and we want to get the NS, the name server records, for linuxacademy.com. And so here we have the 4 name server records, and they are AWS DNS. So we're just going to pick one of them here. We'll get this guy. And I'm going to dig at that name server, linuxacademy.com. And so now you see we have some authority right here. And this hey AA here means that this is an authoritative answer. So the QR is a query request, authoritative answer, recursion desired. We asked it one question. We got the 3 IPs back with an authority of all 4 name servers. So according to the host's name servers themselves, these are the right IPs. So what about DNS caching? So we talked a little bit about TTLs, and in this case, we can see the TTLs here are 60 seconds for the IPs, and then of course the name servers are much longer. So how can we look at that cache? We can dig linuxacademy.com, and we're going to use knowall and answer. And so we see here 60 seconds. And if we run it again, we'll see we're down to 56 seconds, 54. And so that's how old the cache is. We refreshed it when we asked it just a second ago because it had been a minute since we last asked. Now we're down to 44 seconds. But what if we want to verify zone synchronization across all the name servers? So we saw we had 4 in the authority answer section. How can we make sure that all of them are on the same serial number? And so for that, we can use dig linuxacademy.com, and we'll use plus name server search. And you can see these are all on the same serial 1 in this case. So another thing we could do is we can verify this zone. So let's go back to that name server right here. So dig at name server. And in this case, we want to look at the SOA, the start of authority. So you see, once again, we have authority of 4 here for the 4 name servers. And this is an authoritative answer. And we see here that we got no error. So we're good to go. Let's try something that our name server shouldn't be the authoritative answer for. So we'll just try Amazon.com. And in this case, we see that the status is refused. This will be refused because of policy reasons. So obviously our zone information, or rather our name servers, does not have the Amazon.com zone. But let's look for a subdomain. Let's try Linux networking.linuxacademy.com. And in this case, we see an X domain. That means this just doesn't exist. So we're asking the authority right here, getting an authoritative answer for the name server for the zone, linuxacademy.com, and it is saying that subdomain does not exist. That wraps up this lesson on troubleshooting DNS. I hope you found this helpful. Thanks for watching. Hi and welcome. In this lesson, we're going to talk about firewalls. Nothing seems to cause more grief to junior and mid-level engineers than firewalls, so I'm going to break it down right to the bits. And in the next couple of lessons, we'll look at a couple of different ways to leverage firewalls on the host. Let's begin. What is a firewall? Let's say we have a host, and on this host, we're running SSHD, we've got HTTPD, so we've got a website, and we are running bind. So we are accepting connections on port 22, port 80, and port 53. And this makes up our application listeners on this host, and we'll just call it an application host. And as it stands, connections can come and go, and there's no problem until we enable a firewall. With the firewall enabled, no connections are coming in or out unless we set up specific rules to permit that traffic in or out. Now, most firewalls come default with port 22 in and things like that. But if you have a fresh host and it's running IP tables or Firewall D or some other firewall and you start up Apache and no one can connect, chances are you're going to need to permit that port 80 traffic. So let's talk about what makes a firewall work, and that is NetFilter. NetFilter is a framework provided by the Linux kernel. Essentially, NetFilter is the software inside of the kernel that permits things like packet filtering. And so we're talking about stateless as well as stateful through the use of connection tracking. So we could have configurations to accept packets from this host or accept established connection packets from this host. NetFilter also permits network address translation. I touched on this a little bit when we were talking about IPs in general. NATing permits translating traffic from one IP to another. And additionally, NetFilter permits port translation, which, just like it sounds, permits translating traffic from one port to another. There's a little more nuance provided by NetFilter. However, NetFilter, IP tables, and connection tracking make up the bulk of it. It's used to build firewalls, NAT for address masquerading, transparent proxies, and performing packet manipulation, often called mangling, as well as building policy routers. And per NetFilter's own definition, NetFilter is a set of hooks inside of the Linux kernel that allows kernel modules to register callback functions within the network stack. A registered callback is then called back for every packet that traverses the respective hook within the network stack. We're going to talk a lot about this in the next lesson. So if NetFilter is the engine that runs all things firewall, what are the services we typically use for implementation? System Config Firewall is one you might be familiar with. It's a GUI or a TUI front end that interacts with the IP table's service, which in turn is merely a handler for the IP table's command. IP tables, in turn, interacts with the hooks provided by NetFilter. You may have in the past used dbus, firewall config, or firewall command, and you may already know that these leverage the firewall D service. But despite often being touted as a replacement for IP tables, it still uses IP tables for all of the functional configuration. So I don't want to take away from what Firewall D has done in terms of abstracting firewall configuration from IP tables. I've used both a good bit, and I vastly prefer Firewall D for the majority of firewall adjustments and configurations needed on a typical host. However, there are some cases where IP tables is just a better fit, such as setting a host up as a router, for instance. So having said all that, let's look at an example of a firewall in action. All right, so let's take a look at an example. Here I have host 10.0.1.10. This is a server and it is running Apache. And we can verify that by looking at the listening ports and grepping for port 80. And we see that we are listening on port 80 for web traffic. And we can curl the local host and get back the web page, which in this case is just header 1, server 1. Now we also have a client here that can do the same thing, and we can curl 10.0.1.10, and we get back server 1 from 10.0.1.10. So right now we don't have any firewalls running. Let's go ahead and start IP tables. And this is just default out of the box. And of course, we can still curl. However, if we try to curl it here, we're going to get a failed to connect. Now let's go back to server 1 for a second. And I'm going to use TCP dump on the interface ETH0. And we're going to watch port 80 traffic. So right now, we're not getting anything. And if I curl it again, let's see what we got. We got a send request, but nothing else. So let's go ahead and stop that. And let's stop IP tables, see how this looks different. And as you can see, we got the send request, we got the send ACK, we got the ACK, we got it all. And we even sent and looked at the H1, server 1, H1. So let's take a peek at this in Wireshark. And so here we can see all of it. Here's the send ACK, the ACK, get the HTML, more ACKs, and then we're kind of done. And so this is when it worked, and this is when it didn't. So here's that original send request, and we didn't get anything. And the giveaway to firewall for me is this host administratively prohibited. That almost always means firewall. So now we're back on the server. We'll go ahead and disable that firewall so that we can receive connections again. That wraps up this lesson. I hope you found this a useful explanation of what a firewall is and what it does. In the next lesson or two, we're going to dive a little deeper into firewall configuration and using IP tables and Firewall D. Thanks for watching. Hi and welcome. In this lesson, we're going to jump into IP tables, break down how it works, and look at some examples. Let's get started. IP tables does indeed use some tables that contain the policies for how to handle different network scenarios. So think of these tables as the categories for the rules. The first table is the most common, filter table. This is what most people think of when they think of a firewall. This table is used to determine if a packet should continue or not. It also happens to be the default table when using the IP tables command to enter a rule. The next table, and I'm really only going in order of popularity as it pertains to my own experience, so take it with a grain of salt, is the NAT table. The NAT table is used for network address translation or sending traffic bound from one IP to another. It determines how to modify the packet's source or destination address to affect the routing. We also have the mangle table. This table is used for altering the headers of packets in order to modify the TTL or hops. You would add rules to this table in pre-routing, say if you wanted to create some logic around maybe dropping SYN requests or even modifying the MTU. There's also the raw table. This table is used for opting out of connection tracking. Connection tracking is how the disposition of a connection is determined, for instance, if it is new, related, or established. And lastly, there's the security table. This is used for applying SE Linux contexts on packets or connections. We know that NetFilter is the engine powering the firewall, and that IP tables is the mechanism whereby we implement the firewall. And we know that NetFilter provides a set of hooks for actions on network activities, so let's examine how these two interface. The NetFilter IP pre-routing hook is leveraged by the pre-routing chain. This is triggered by incoming traffic shortly after it hits the network stack and is processed before routing decisions. The NetFilter IP local in hook is leveraged by the input chain. This is triggered after the incoming packet is routed if the destination is internal. The NetFilter IP forward hook is leveraged by the forward chain, and this is triggered after the incoming packet is routed if the destination is external. The IP local out hook is leveraged by the output chain, and this is triggered by local outbound traffic once it enters the network stack. And then the NetFilter IP post routing hook is leveraged by the post routing chain, and this is triggered by any outbound traffic prior to being transmitted. There are 5 hooks. It's no coincidence that there are 5 IP tables chains. If you've been working with Linux long enough, you may even remember the firewall used to be called IP chains. And as you can probably tell, there's a fair bit of logic in terms of the chains present in each of the tables. And this is what that looks like. This is a slightly misleading chart, as there aren't, for example, 2 different raw tables, one for pre-routing and one for output, but rather this chart shows the flow of the chains and what tables can contain what chains. So to walk back through the processing I mentioned a couple slides ago, pre-routing rules apply to packets just as they arrive on the network interface, and that chain is present in the NAT, mangle, and raw tables. Input rules apply to packets just before they're given to a local process, and the input chain is present in the mangle and filter tables. Output rules apply to packets just as they've been produced by a process. That chain is present in the raw, mangle, NAT, and filter tables. Forward rules apply to any packets that are routed through the current host. The forward chain is only present in the mangle and filter tables. And post-routing rules apply to packets just as they leave the network interface. The post-routing chain is present in the NAT and mangle tables. That's a lot of information. Luckily, for the most part, you do not need to understand it to this level to be able to effectively use it for your typical firewalling tasks, but it is handy to understand when you're getting into really complex configurations. So let's talk about the rules for a minute. Rules are added to a chain in a table, and a rule has 2 parts. As a matching part, that is determining what criteria must be met, and a target, or what kind of action to take when the match occurs. Targets are typically divided into terminating and non-terminating. Terminating targets perform an action that terminates evaluation within the chain and then returns control to the NetFilter hook. Non-terminating targets perform an action and continue evaluation within the chain. An example of a non-terminating target would be a log target. You want to log that specific traffic, but not interfere with it otherwise. And then jump targets are a special class of non-terminating target. The most commonly used targets are accept, which causes IP tables to accept the packet, reject, which causes IP tables to reject it, and it does so by sending a connection reset if it's TCP, or a destination host unavailable in the event of ICMP or UDP. And then drop does that. It just quietly drops the packet. So let's look at a couple of simple examples. In this example, we're using the IP tables command with a TAC-T filter to indicate that we're adding this rule to the filter table, TAC-A for append, or add if there isn't anything there already, to the input chain, TAC-P for protocol, which in this case is TCP, TAC-D port for the destination port, and we're specifying port 22, so that's SSH traffic. And then the target is jump to accept. Here's another example similar to above. We are inserting into the input chain at line 5 with a TAC-S for source, and we're specifying a subnet. We could specify a single IP here or a range. And then we're jumping to reject. So in the first example, we're permitting port 22 traffic, that TCP port 22 traffic, incoming to the host from wherever, while in the second example, we are rejecting all connections from the specified subnet. Now you have to be careful with your IP tables rules because they are processed in order. And I'll get to that here once we jump behind the command line. Before we do that, let's talk about states. States are connection dispositions that can be used in matching. I've mentioned connection tracking a couple times, and we're going to look at it on the host here in a moment. But for now, it's important to realize how connection tracking facilitates the use of some of these states. So you have new, and this state represents the very first packet of a connection. You have established, which is used for packets that are part of an existing connection. For a connection to be in this state, it should have received a reply from the receiving host. You have related, so that state is used for connections that are related to another established connection. So an example of that would be like an FTP data connection. It's related to the established control connection. There's invalid. That state means the packet doesn't have a proper state. This could be due to any number of reasons, such as environmental issues on the host or network errors, really anything. And most firewalls are configured to just drop invalid. Untracked are packets that are exempt from connection tracking in the raw table with a no track target, and they will end up in the untracked state. And then source NAT is a virtual state used to represent packets whose source address was changed by the rules in the NAT table. Likewise with destination NAT, the rules in the NAT table have changed the destination address. So if you imagine for a moment that you have a brand new fresh host and you create a rule to block all incoming external traffic except port 22, that way you can log in and do your thing. That way you can log in and administrate the host. You would find that your host wouldn't be able to effectively connect to anything else, say to run updates, for instance. And that is why you generally have a line at the beginning of every default IP tables implementation permitting related and established connections. That way, if your host reaches out and initiates the connection, it becomes established or related in some cases, and you're able to have that two-way connection. So let's jump into the command line and look at some examples. I'm going to start with connection tracking. You can look at your existing connection tracking information by catting out proc net netfilter underscore contract. So cat out proc net netfilter underscore contract, and that is your raw connection tracking information. I should add, you need to have IP tables as a service running for this to work. And if you're using CentOS 7, like this installation here, this is just a Linux Academy cloud server. You can see that I've installed the IP tables tax services package, which then allowed me to system control enable IP tables, system control start IP tables, and run it instead of firewall D. If you want to interact or poll the connection tracking information a little more meaningfully, you can install the contract tac tools. So if I yum list installed contract tac tools, you'll see that package right here, Contract Tech Tools x86. And so what that does is that allows me to, instead of catting out procnet, I can contract tech L and see everything. And you'll find that the syntax used with contract is very similar to that used with IP tables. So I could even contract tech L, protocol TCP, and D port 80, and see that traffic there. If I wanted to kind of tail this or watch it in real time, I could swap that L, which stands for list or dump, to an E, which stands for event log, but really it's just like tailing it. And I could watch it real time. So if connections were happening right now, I would be seeing them. So that's connection tracking. Let's go back to IP tables for a minute. You can look at each one of the individual IP tables. So we use IP tables table, and we'll just use filter, and then tech L for list. And we can see that I've misspelled filter. So here we see the filter rules. So we've got an input chain, a forward chain, and an output chain in the filter table. And we can look at all of the tables. We could swap filter for NAT, for instance. And you see we have a pre-routing, an input and output, and a post-routing. Or we could even look at raw, which has a pre-routing and an output. Or we could do mangle or security and look at those. So mangle has pre-routing, input, forward, output, post-routing. So we can view each one of the tables like that. We could also view the individual chains. So I'll use IP tables, tag L, because I want to list everything, but I want to see the input chain. And now since I didn't specify a table, we're looking at the filter table. That is the default. And so let's walk through these chains real quick. We have an accept all protocols from anywhere to anywhere that has the state related and established. This is what I was mentioning a couple minutes ago. We want connections that our own host initiates to be able to take place, or already related or established. On the next line, we have an accept of protocol ICMP from anywhere to anywhere. Likewise, an accept of all protocols from anywhere to anywhere. And then we have an accept of the TCP protocol from anywhere to anywhere. That is the state new, right? Because if it was related or established, it would have already been caught. State is new, TCP, destination port 22, or SSH in this case. So each rule is evaluated in order, and then it's done, because remember, accept is a special non-terminating target. And then lastly, we have a reject. So reject all protocols from anywhere to anywhere. If you're a little confused about how we can have that third line there, the accept all anywhere to anywhere, and then still proceed down the list to the reject, it is because I did not use TAC V to list a more verbose output. And if you look here, you see that it's just for the loop back only. And so all traffic anywhere to anywhere over the loop back, naturally, you do not want to block that. But IP tables still treats it like a normal interface, and so we have that in there. So since this is our input chain in our filter table, we would not want to append to this. It would put whatever we appended after the reject line. Luckily, we can add rules at any line we want. We can also use the IP tables TAC L and use line numbers to see the line numbers. So in this case, if I wanted to permit HTTP traffic, I would put it at line 5 and bump line 5 down 1. So let's do that. We'll use IP tables, and we'll insert in the input, and we're going to insert on line 5. Protocol will be TCP. Destination port will be port 80, because we want this web traffic to happen. And then we'll jump to accept. And so now if we look at it, we see right after the SSH line, we have the HTTP line on line 5, accept protocol TCP from any source to anywhere that is TCP port 80. So admittedly, we have stayed towards the shallow end of IP tables. We're going to get more into the deep end when we start talking about advanced use cases, but this should give you a more fundamental understanding of NetFilter, IP tables, firewalling in general, In the next lesson, we're going to take a look at Firewall D, and then towards the end of the course, we're going to start using IP tables in Firewall D for some more advanced use cases. This lesson is now complete. Thanks for watching. Hi and welcome. In this lesson, we're going to get into Firewall D and talk about why you might use it over plain old IP tables. One of the things that sets Firewall D apart from IP tables is the concept of zones. Now, you might have remembered in the past when an operating system would ask you if your connection was trusted, public, office, that kind of thing. This is sort of along those lines, but it allows us to do some pretty cool stuff in terms of firewalling. Each network interface has a default zone. Firewall D comes packaged with 9 zones, and I'm talking about the CentOS version here. I have not looked to see if Ubuntu's is different. But the default zone is the public zone. Now, let me run through these zones real quick. The drop zone is the lowest level of trust. All incoming connections are dropped without a reply. Only outgoing connections are possible. Block is similar to drop, but instead of dropping it, the incoming requests are rejected with an ICMP host prohibited. Public represents a public untrusted network, so a couple of services are already included. External networks in the event that you're using the firewall is your gateway. It's configured for NAT masquerading so that your internal network remains private but reachable. Internal is the other side of that external zone used for the internal portion of the gateway. The computers are fairly trustworthy and some additional services are available. DMZ is used for computers located in a DMZ, so they're isolated with no access to the rest of the network. Only certain incoming connections are permitted. Work used for work machines, home used for home machines. And trusted trusts all of the machines in the network. It's the most open of the available options and generally not used or used very sparingly. But all of these default zones exist as XML files in userlib Firewall D under zones and can be parsed like any normal XML file. So if we walk through the file, there's the short name, public, there's a description, and then there's a list of services permitted by the zone, in this case SSH and the DHCP-v6 client. You can do some pretty cool things with zones, as we'll see once I get behind the command line here in a few minutes, but let's look at services for a minute. So we see that in this zone, we have the service SSH and the service DHCP-v6-client permitted in the zone. So services are the other big thing that separates Firewall D from IP tables. Services are a list of ports and destinations and can include firewall helper modules automatically loaded for the service. For instance, the NetFilter connection tracking module for that service. And just like zones, they exist as XML files in userlib Firewall D under services. And I should mention, you wouldn't want to modify these files. User-defined zones and services can be placed in etc Firewall D. And you can manage all of that through firewall command. So walking through this HTTP XML services file, we have a short name and a description, but then at the bottom we see that it's port 80 over TCP. So what this means is that if a zone calls this service and permits this service in the zone, then this port will be open in the firewall. So if I wanted to set up a Linux Academy Cloud server as a name server, I could create a new zone and then add bind to that list of services permitted, or I could just simply add bind to the public zone, which is more likely what I would do. So then how do we leverage zones for a single NIC system? To do that, let's talk about IP sets for a bit. IP sets are a group of IP or MAC addresses. They're a list. They're all user created, and they exist as XML files under etc Firewall D IP sets. In this example, I've created a whitelist with 3 IPs in it, but it could just as easily be a blacklist or a list of IPs that you want to limit connectivity to or deny from. And by using IP sets as a source for a zone, that's where we can do some pretty cool things, such as having a programmatically main list of, say, kiosk IPs that get dropped when they try to access our host. So let's fire up a cloud server and jump behind the command line and set up Firewall D. So I've just logged into a Linux Academy Cloud server, and I installed Firewall D in bash completion, and then I started Firewall D. So to start interacting with it, I'm going to use the firewall command, and all Firewall D commands pretty much start with this. Now there is a firewall offline command as well if Firewall D wasn't running. But since it is, I'm going to use firewall tac command, and I'm going to use list all to show me kind of what's going on now. And so I see that the public zone is the active zone. The target's default. We're not doing any ICP-MP block conversion. Our interfaces are ETH0. We don't have any discrete sources set up. The services permitted are, just like in the slide, DHCPv6, client, and SSH. We haven't specified any open ports, protocols. We're not masquerading. We're not doing any port forwarding or anything with source ports or ICP-MP blocks, and we haven't done anything with rich rules. So if I want to see what zones are out there, I'll use firewall command get active zones. And we see that we've got public. Public's the active zone, and the interface is ETH0. I can also get the default zone. And if I wanted to look at all the zones, I could use get zones. And so we've got block, DMZ, drop, external home, internal, public, trusted, work. And so before we get into services, if I wanted to just add a port, I could use firewall command, add port. And that's going to be, we'll just say port 100 over TCP. And that's successful. So if I do firewall command again with the list all, we'll see that right here we've got ports 100 TCP listed. So let's talk about services for a minute. If I wanted to take a look at the services, I can do firewall command, list services, and it's automatically going to look in the public zone since that's the default active zone, and it's going to tell me DHCPv6 client and SSH are there. And those are the services that are enabled. I could do the same with list ports, and I will see that 100 TCP is enabled. If I want to add a service to the default public zone, I could use firewall command, add service, and we'll just add squid. So now squid is added. So if I go back up here to list services, we got DHCPv6 client, SSH, and squid. And if I were to look at the list all again, we would see that squid now shows up here. If you wanted to see all of the services that were available, you could just look in user lib firewall D services, and there's plenty of them already there. If you had a custom service, you could always just create it. We'll do that here in just a moment. You could also use firewall command list services. So right now, just like with IP tables, I have only been making changes to the running config. So if I firewall command reload and then do that list all again, you're going to see everything has gone back just to the way it was before I started doing anything. So the changes were not persistent. To make changes persist while you're entering the command, you need to use the permanent flag, just like that. So let's say I want to create a new service. And let's say for the sake of the hypothetical that this host that I'm on right now, I've got, we'll say 10 Tomcat instances. And so each Tomcat instance has a couple of JMX ports that I want to be able to interface with some sort of monitoring application. And so I've got these 20 ports, and my monitoring application needs to be able to reach into these ports on this host, so I need to expose them. So maybe I'll just call this new service JMX. So I've created a new service called JMX. Now right now, I do need to do a reload for it to pick it up. And if we take a look in Etsy Firewall D services, we'll see that there is a JMX file. And right now there's nothing in it. It's just the service JMX. There's service thing closed tag service. So it's not required, but we can just give it a description. So I'll use firewall command permanent, and we'll have to use service equals JMX, so it knows which one we're talking about. And we will set description to, we'll just call it JMX service. And let's go ahead and add those ports to it. So the same thing, permanent service JMX, and I want to add port And we'll say it's 20 ports open, so maybe 1400 to 1420 over TCP. And so if I reload again, and then we cat that file again, you should see now that we have a description and we have those ports right there listed. So we created that service. We're not going to add it just yet. We're going to do something with IP sets here before we add it. So let's see if we have any IP sets out there. We will get IP sets, and we don't have any out there now. So let's go ahead and add one. So again, firewall command, permanent. This is something you're going to be typing an awful lot if you're working with Firewall D. And we'll do new IP set, and we'll set it, let's just call it kiosk. And now we have to give it a type here. And so we could go MAC address or IP. I'm going to go IP, so I'm going to use #IP. And we have created it. Now, just like when we created the service, we need to reload. We've created the XML file. The firewall command took care of that, but we need to reload it to be able to start adding IPs to it. So I will firewall command, reload. And if I cat out etc firewall D, IP sets, kiosk, you'll see that there is just the IP set type, which is #IP. So let's add an entry. We'll use firewall command, permanent, and we have to specify the IP set we're working with. Even though there's just one, we still have to do it. So IP set equals kiosk. And we're going to add entry, and let's give it 10.0.1.11. And so now we can use firewall command IP set equals kiosk, and we can get the entries. And we see that we don't have anything because we need to reload. So if we run get entries again, we have our one entry. So that's great if you have to add entries onesie twosie, or you want to programmatically have a hook that adds an entry somewhere. But what if you have a big long list of IPs that you want to add? So let's create a list. We'll just cat, and we'll call it kiosk ips.text. And we'll just do till we get to the EOL. And so let's add 10.0.1.12. We'll add 10.0.1.15. We'll add 192.168.1.0. We can put a whole subnet in there. And that's probably enough to make this example. And so we've created this file, kiosk_ips.text. So now we can use firewall command, permanent, IP set equals kiosk. And we can add entries from file, and that file will be kiosk_ips.text here in the local path. And it did it. So let's reload again. And then let's get the entries again. And we can see all the IPs are in there. So let's tie it all together. Let's create a new zone, and we'll say that the kiosk is consuming the data from those JMX ports that we exposed. So let's create a new zone. We'll firewall command, permanent new zone, and we'll just call the zone kiosk. This is not a great name, but we'll just say this is the zone of the firewall, and we've zoned off the kiosk machines. So just like earlier, that created the XML file. We'll have to firewall command reload before we can start doing anything with it. And let's go ahead and add firewall command permanent, and we'll specify the zone equals kiosk. And let's add this service JMX. So now we've added the service we created, the JMX service, to the new zone that we've created, the kiosk zone. So now everything hitting the kiosk zone is going to be able to hit those JMX ports. and nothing else because we didn't add any other services. It's a new zone that we created, so no services will be included. And so here's where a little bit of the magic's going to happen. We're going to use firewall command permanent zone equals kiosk, and we're going to add source equals IP set kiosk. So we created an IP set that we called kiosk, and we also created a zone that we called kiosk. We probably could have called it something else. But the IP set, if you'll remember, are these IPs here, right? We added the onesie twosie and then we added them from a file. And now we're saying that all of these IPs that we have here are going to be bumped to the kiosk zone. And the only service we have exposed in the kiosk zone is the JMX service. And so now the only connectivity that a kiosk IP has to this host here that we're working with is through the kiosk zone, meaning only those JMX ports that we described will be open to it. So that's zones, services, and IP sets. Let's talk a minute about rich rules. Rich rules are a really big topic, and there is a lot to the rich language. And there is some excellent documentation here if you look at the man pages. And there's just all kinds of really good stuff. There's examples here. And I'm going to tell you, if you're ever in an exam situation, being able to just kind of copy and paste to get the syntax right on these examples is pretty critical. And what rich rules allow us to do is to get really granular with source and destination formatting and that sort of thing. So let's look at an example of that. I'll use firewall command. I'm not going to use permanent because I'm not worried about this persisting. But I will add rich rule, and now that's going to be equals, and I have to have a single tick. And if you remember the man page I was looking at, that's where the syntax sort of comes in. And that will always start with rule family equals, and then I'm going to use IPv4 because that's the IPvert schema that I'm using. And let's say we have a source address of 10.0.1.0/24. It's picking up the whole subnet, and the destination address equals 10.0.1.10. So we'll just assume this is .10 here that we're working with, but maybe it's got a bunch of IPs and we've got a service listening on .10. And so we want to take all of the source of our local subnet that's coming to us on that IP, and I'm going to specify the port is 8080 to 8090, and we'll say the protocol is TCP, and I want to accept this traffic. Now, if you botch it up, it will tell you that you've made a mistake. And in this case, I have misspelled rich rule, which I'm sure was incredibly painful for you guys to watch while I kept typing and typing and typing. So let me go up here and just fix that. Okay, so it succeeded. So now if I use firewall command list all, we see down at the bottom we have that rich rule. And it's handy that it preserves the format, because to remove that rich rule, you're basically going to copy and paste. You're going to firewall command, remove rich rule equals, and then you're going to put a tick, you're going to paste, and you're going to close the tick, and that's how it works. So there's a whole lot you can do with rich rules. That's a really big topic. You can get super deep into that. I would encourage you to get familiar with them. If I had to pick one, IP tables or Firewall D to work with every day, I do prefer Firewall D. Now, I recognize if you're getting way in the weeds with transparent gateways and things like that, then you're kind of stuck doing IP tables. But for the bulk of what a Linux administrator is going to be working with firewalling, Firewall D is way more than capable of handling that, and then some. Now, there's one last thing I want to bring up before I wrap up this lesson on Firewall D, and I kind of hesitate to do it because it can make things really messy. But let's just say this is a dual NIC device, right? We'll assume for a minute that it's a physical device and I've got two NICs. I've got ETH0 that's connected to this local network, and I've got ETH1 that's connected to a private network with some other private IPs. And let's say I want to allow those IPs to communicate with the external network, and we have to configure the firewall for some IP masquerading. You can use firewall command to add direct IP tables rules. And the way you would do this is with firewall command. And you would use permanent, but you're going to use direct and then add rule. We'll use IPv4. We'll specify the table that we're adding it to, in this case, the NAT table, the post routing chain. We'll put it at the top. Our output interface is going to be ETH1. And we're going to jump to masquerade. So I have now added an IP tables flavored rule through firewall command. If I wanted to get a list of these, I can use firewall command and then direct and get all rules. And that's going to show me what I've got. This can be useful in certain edge cases. I would caution you about doing this because it can make for some really convoluted and messy firewall configurations. And as a guy who has inherited systems that was a mix of this and Firewall D, it was just, these things were all over the place and it wasn't any fun trying to sort it out. So if you do go down this route, I would encourage you to be very sparingly with it and make sure it's well documented. So that wraps up this lesson on Firewall D. Thanks for watching. Hi and welcome. In this lesson, we're going to look at firewall troubleshooting, the order in which you can go about it, and where to begin. I'll be using the following reference architecture, with 10.0.1.10 being designated as Server 1. It is the firewalled host running some services. Client 1 will be 10.0.1.11. Client 2 will be .12. The services on Server 1 will be Apache and SSH, and will primarily be testing with Apache. So before we start troubleshooting a firewall, you need to perform some sanity checks. You want to make sure that the service you're attempting to connect to is listening, it's listening on the right interface, and you want to make sure it's not a connectivity issue in between the client and the target of the server. And so I'll usually use SS and LNTP to see what services are listening on what ports on my local host. And so I see here that HTTPD is listening on port 80. So we're running a web server. And I should be able to see that that web server is behaving normally, and I can curl localhost, no problem. Now we would want to make sure there weren't any routing issues in between, and we're just going to make the assumption that all of that is copacetic and we're merely troubleshooting the firewall. So let's start with IP tables. I verified we have a service running, and I verified that I can curl the localhost. So let's attempt this from client 1, since I want client 1 to be able to hit server 1 over port 80. So from client 1 here, I'm going to curl tech. I just want to pull the headers of 10.0.1.10. And I can see that we've got this connection failed, no route to host. So clearly there's something preventing me from curling those headers. So let's head back over to 10.0.1.10. And so the first thing I'm going to do, since I know that I'm running IP tables, is I'm going to look at the running config. The command I'll use is IP tables, and I'm going to use TAC V for verbose, N because I want to see port numbers and IP numbers, and L because I want to list out the config. And so we see we have a config here, and I'm seeing a lot of accepts. It looks like the vast majority of this, if not all of it, is around different service ports. And towards the bottom of the accepts, I see a reject. So I see this reject here. And it comes before the state new TCP destination port 80. So that is what's going on here. So remember, with IP tables, you have to verify the order and determine if a new rule needs to be added or if an existing rule should be changed. Now, before I get too far here, it is tempting to just disable the firewall and see if it works. This is never something you're going to want to do with a production system, particularly one on a public network. Now, if you were in the middle of a change window, you could possibly just flush all of the rules once you had made a backup and then explicitly permit the traffic that you were troubleshooting just to rule out network issues, but this is rarely needed. So remember that with IP tables, order is everything, and the chains can look pretty complex at first, especially if you're looking at a routing system. So don't be afraid to grab the config, write everything out on the whiteboard, especially if it's a system or an environment that you're unfamiliar with. Rule out the easy stuff, the ports being open block, little rules, and then follow the chain. Also, be mindful of the order of operation. If you remember the chart from the IP tables slide deck a couple of lessons ago, you're going to want to follow this chart, particularly if you have some complex chains that you're trying to untangle. So back to this problem at hand. The easiest way to resolve this would be to just remove this last accept and then insert it somewhere before the reject. We can do this inline, or we can modify the etc sysconfig IP tables file. And in this case, if we look here, we've got the port 80 accept occurring after our reject. So I'm going to yank that and paste it up here, and then we're going to delete it from the bottom. And we'll save the file. We will restart IP tables. And now we'll verify from our client. So back at the client, curl, and I can curl the local host. So again, with IP tables, order is everything. Follow the chains, break it out on a whiteboard. Now, the vast majority of systems aren't going to have super convoluted firewall rules and chains in there, unless you're using it as a router of some sort or NATing or gatewaying. And honestly, you're going to save yourself a world of trouble when working with systems like that if you make extensive use of comments and documentation. So now let's look at troubleshooting with Firewall D. So I'm back on the same system. We're no longer running IP tables. We are now running Firewall D. We're still running Apache. We're still running SSH. So the first thing you're going to want to do is use firewall command list all and get your running config. So we're in the public zone. I don't see any weirdness. Our target's default. ICMP block conversion is no. Interfaces is blank. We don't have any discrete sources for this zone. We've got a few services running, no specific ports open, protocols. We're not masquerading. We're not port forwarding. We're not source porting, any of that stuff. No rich rules. So unlike IP tables, our service right now is running, and we're going to break it because I want you to see the manner in which it breaks. So if I hop over to the client here, you'll see that I can curl 10.0.1.10 with no problems. And I should have curled the headers because that's an awful lot. There we go. So we're good to go here. Let's break it. And so the way I'm going to break it is I'm going to add a rich rule to block all traffic from the local subnet. So I'll use firewall command, and we'll use permanent. I'm going to add a rich rule, and the rule family will be IPv4. I want our source address to be the 10.0.1.10/24 subnet. Our port is port 80. Protocol is going to be TCP. And I want to reject all of this traffic. But before we check it from the client, we need to reload the firewall. Since we didn't change the running config, we're changing the permanent config. We can see that we've broken it, so connection refused. This is what we would expect since we blocked the entire subnet. So back on the server here, let's add another rich rule to permit that subnet traffic. And we'll do it much the same way. We'll use firewall command, permanent, add rich rule. Our rule family is IPv4. Our source address, in this case, is going to be 10.0.1.11. Port is going to be port 80. Protocol TCP. And we want to accept. We'll reload the firewall to pick it up. So what do you think is going to happen when I test it now? Intuitively, we would think that it's going to succeed. But if I try to curl the header again, we'll see that it fails again. So the ritual ordering in process can be a little unintuitive. Let's go back and look at our running config. So we're looking at these rich rules down here at the bottom, and we see we've got the first rule is blocking the subnet, and the second rule is permitting our client 1. So we might assume that this is an ordering problem. Kind of like IP tables, it's all about the order of the chain. So let's test that hypothesis. I'm going to copy the reject rule here so that I can remove it. And I'll use remove rich rule. So I've pasted it in there, and I'll hit enter, and then we will reload the firewall again. We can test from the client, and we will see that it's working. So let's now add that rule after our rule explicitly permitting the 10.0.1.11 port 80 accept traffic. So I will firewall command, permanent, add rich rule, reload, and let's look at the running config just to verify. So now the ordering looks intuitive, right? It's correct. We're accepting before we're rejecting. So what's going to happen when I try it again? It's going to fail. So rich rule ordering and processing can be a little unintuitive. A workaround for this particular example would be to leave the subnet blocking rule in place and then add .11 as a source to a different zone and manage it from there. So as you can tell, firewalls are a pretty deep subject, and I've only been able to cover a portion of the topic under the larger context of Linux networking and troubleshooting. I hope this has provided you with a solid understanding of what firewalls are, how they function, how they can be used and managed, and how you can begin troubleshooting them. This lesson and this section is now complete. Thanks for watching. Hi and welcome. In this lesson, we're going to talk about connection testing, one of the most important troubleshooting skills you can have. When integrated systems break, or really when anything breaks or doesn't function as desired, being able to find and resolve connectivity issues quickly is an essential tool. Let's begin. Let's start off by discussing the order in which we'll address testing and then the tools that we can use. So if you remember the OSI layers from the beginning of this course, those are going to frame how we go about our testing process. If you remember layer 2, the data link layer, this is the layer in which we'll want to verify our VLAN configs, MAC addressing, and IP conflicts. Layer 3 was our networking layer. We'd want to verify addressing and routing, bandwidth constraints, network authentication issues, and things of that nature. Layer 4 was our transport layer. This is where we'd investigate blocked ports and firewall configs. In my experience, this is where a lot of the problems occur. And then layers 5 through 7 were primarily application-centric. So let's talk about what tools we would use at each layer. ARP ping is very useful for verifying MAC level reachability at layer 2. You can also use IP neighbor to look at the ARP table. Ping, traceroute, tracepath are all useful for verifying layer 3 IP connectivity. SS, Telnet, TCP dump, and Netcat are useful tools for layer 4 testing and validation. And then for layers 5 through 7, you can use DIG for DNS testing, as well as any application-centric tools like configuration checkers for syntax validation. Now, how you go about testing is really up to you. I've always tended to start with the application layer and work down, the premise being that the network isn't as likely to change as the application environment. However, if your circumstances have you in an organization that's making frequent network topology changes, you could start at layer 1 by simply making sure the cables are plugged in and SFPs are seated, getting link lights, and that sort of thing. Lastly, in an all-hands outage situation, it would make sense to divide and conquer, with 1 or 2 engineers validating each layer so that they're not working on top of one another. As for our example architecture, this should look pretty familiar. you'll notice that server 1 now has 2 NICs, and Apache is bound to the second NIC at IP 10.0.1.20. So maybe this is the IP that is NATed to an external IP in our example. And in this example I'm going to walk through, the host is way more broken than what you'll typically encounter, but it should be a good exercise to walk through. It's time to get behind the command line and sort out why our client at 10.0.1.11 cannot access the web server. So I'm logged into the client, and like all good administrators, I'm going to verify that the issue exists. So let's just curl the header of 10.0.1.20. And nothing's coming back, so that tells me there's probably an issue. So let's hop on server 1 and see what's going on. So I'm logged into the server here, 10.0.1.10. And first, I'm going to make sure that all the NICs are up, and they're all connected. I see the ETH0 is 10.0.1.10. And ETH1 is 10.0.1.20. That's the IP that our Apache server is available on. The next thing I'm going to do is make sure that Apache is actually running. And I'm going to use SS with a TAC L for listening, N because I want the numbers, T for TCP, and P to give me the ports. And I don't see anything listening on port 80. In fact, let me run that again without the grep. And you'll see that we've got SSH running, we have port 25 open, so some mail, but that's it. So this could simply be that the service isn't running. So let's go ahead and start Apache. And then we'll verify that it's running and listening. All right, so now it's listening on 10.0.1.20, port 80. Let's try from our client again. Yeah, it's still not working, so back to the server. So the next thing I'm going to check is the firewall. So I know that we're running firewall D. And incidentally, if I didn't know which firewall we were running, I could use system control status, and it's going to be, since this is CentOS, it's going to be firewall D or IP tables. And if it wasn't, then I could PSAUX and look at the running services and see if it was UFW or pfSense or something like that. But I'll try firewall D and IP tables. And I can see that it is firewall D right here, running active. And so let's get the running config for firewall D, firewall command, list all. And I can see that the HTTP service isn't in there. So let's go ahead and add that through firewall command. And I'm going to make it permanent. Add service equals HTTP. Yeah, that's interesting. We get enabled. We'll check it again. So something weird's going on with the firewall. So to clear all that out, I'm going to use firewall command, reload, check it again, and I can see that HTTP is there. So maybe there was just a little hiccup with firewall D. Let's check our client. And still nothing. So back to the server we go. So a quick recap of what we've done. We verified that the service is running. We verified it's not the firewall. Let's go ahead and try it from the local host. We can try curling the headers of 10.0.1.20. And it is there, so it is running. Apache is functional. So we're ruling out layers 5 through 7. We've ruled out layer 4. It's not firewall. We're down to layer 3. So now we need to start looking at routing information. So let's look at the routing table. And I see a couple of extra entries that aren't making a whole lot of sense that are probably left over from the CloudFormation script that created this instance. And since I know that I'm on an AWS EC2 instance and I have that insight to the system, then I know that I'm probably running into some asymmetric routing issues. So in other words, requests will come in and out through ETH0 here as the default gateway. And the interface that I need to be interacting with from 10.0.1.11 is ETH1. So let's add a little bit of policy-based routing and see if we can't get that sorted out. I'm going to IP route add 10.0.1.0/24. So everything to this subnet through the device ETH0, I want to put through table 1. And I'm going to do the same thing for the device ETH1 through table 2. So I've created 2 routing tables now, and I can look at those through IP route show table 1, and I can see 10.0.1.0/24 dev ETH0 scope link, and I can verify table 2 as well. Now I need to add a rule. So I'm going to IP rule add from 10.0.1.0/24. So everything that comes in through that, go through table 1, and then I'm going to do the same thing through table 2. So this should resolve our asymmetrical routing. And now I should be able to ping from ETH1 10.0.1.11. And I can, and I should be able to do likewise from here. I should be able to ping 10.0.1.20, and I can. So now if I curl the headers, I should get something back. And there it is. It's resolved. So in this case, it was a layer 3 issue. That's not a very common issue, but I wanted to make sure that I brought it in here just to show through the validation checks that I would do. Now, the one thing I did skip is I skipped pinging it before I resolved the routing issue. But these days, ICMP is blocked on a lot of different networks, and ping is not a super reliable test. Now, I could ARP ping 10.0.1.20, and see we get back the MAC address comes back. But since this is AWS, I know that it's not likely to be a layer 2 issue, at least not on a running system like this. So that's a real quick walkthrough on a fairly broken system and then resolving it. And I had the insight, like I said, of knowing that it was asymmetrical routing. Now let's talk about using those tools. Let me go back to the server for a moment. One of the most useful tools on any system is Telnet, because it will let you test against any port. So let's see if Telnet is installed. And it would help if I didn't typo. Okay, so now Telnet's installed, and let me throw it on the client as well. So now I have Telnet on both. And so from the client, I can run Telnet to 10.0.1.20 over port 80. So it's IP then port. And I see that I get this connected to 10.0.1.20. That to me is as good as curling the header. That means there is nothing in between this host and that port 80 connection causing a problem. Now I can get out of that and we can try a different port. So let's try port 443. We know that one's not open. We didn't add HTTPS, and we get this connection to address 10.0.1.20, no route to host. So Telnet is an extremely useful tool for using like that. It is one of the tools I have used probably more than just about any other. Maybe Netstat or SS. But let's say you have a host and for whatever reason, you're building it and you want to make sure that that connection is there and you don't have the service started up yet. So this is maybe you're instantiating some new queuing hosts or something like that, and you're building them out, and before you apply all of the application configuration to it, you just want to make sure your ducks in a row. That is where Netcat comes in. Netcat is extremely useful. So let me install that. And for a CentOS-based system, it's going to be nmap-ncap. So yum install nmap ncat. And so now we have it. And so what I can do now is let's add a port to the firewall. We'll just add port 100. So now we've changed the running config. We didn't use permanent, so if we bounce it, it goes away, but that's fine. This is just for our test. So port 100 is now available. I can use ncat listen on port 100. And so now it is just listening. And so let me jump back over to the client, and I can telnet 10.0.1.10. So we'll just use the regular IP over port 100, and there it is. And so I can send some garbage and then just quit. And if I go back to the server, we will see the garbage that I sent right here. So that is extremely useful in being able to listen server side to make sure that there's nothing network related in between. So if you're in an organization that makes heavy use of network contexting and things like that, this is a great validation tool. So useful in a different way is TCP dump, and we can run TCP dump just like we did, and we'll need to make sure it's installed. So now we have TCP dump. We can run it in a similar way. We'll just listen over port 100, and my syntax is off, so we'll use TCP dump, port 100. And so now it's listening back to the client, and we'll telnet again, connection refused. And we can see that we got this connection refused because it's not actually listening on port 100 the way Netcat was. It is merely observing port 100 traffic in a packet capture manner. And so we can get into source and destination. We can say, let's watch this port 100 traffic and let's specify the source as 10.0.1.11. So let's try that for a second. We'll use TCP dump, and I want my source to be 10.0.1.11. And we're just going to capture everything. And let's go back to the client. And let's try to curl that header again, 10.0.1.20. And if we go back to the server, we'll see that we didn't specify the interface, and so we'll need to specify an interface. So we'll do eth1, go back to the client, rerun the curl, go back to the server, and we see all that data there. And you can send this into a PCAP file to then consume it with Wireshark, which is something we're getting into in the next lesson. So to take it back from the top, we had a broken system. The service wasn't running. It was listening on a specific IP. The firewall was blocking the port. The routing was broken. We fixed all that. We looked at a little bit of usage of the ARP ping tool. Ping, we talked about how ping isn't always reliable. We looked at using Telnet. We looked at using Netcat. Telnet and Netcat are really critical tools for your toolbox in any kind of connection troubleshooting. TCP dump's right behind there. It doesn't actually listen on anything. It just captures the packets, captures the data that comes through transparently. You can use Wireshark for the same thing, which is something we're getting into in the next lesson. And that should give you everything you need to be able to reliably connection troubleshoot just about any scenario you're going to come up on outside of a actually physically broken network or a misconfigured at the switch or router level network. This lesson is now complete. Thanks for watching. Hi and welcome. In this lesson, we're going to talk about packet captures. Packet caps are a great way to gather evidence when you're troubleshooting or working through any kind of networking issue. They're also handy for getting a better understanding of the traffic on your network. Let's begin. Packet captures intercept data between a source and a destination, and likewise, once it's in the network stack. So picture for a moment a source and a destination, client and a server, if you will. The packet capture is going to occur on an interface. In this example, it's the source or the client interface, but it could just as easily be on the destination interface or even a router interface. The packet capture is going to observe all connection data flowing through that interface. An important component of packet captures is the capture filter. These are used to reduce the size of the raw packet cap and allow us to only capture the data that's relevant or what we want to look for. Display filters, on the other hand, merely reduce the amount of the packet capture file that we're observing. So consider for a moment a valid use case for a capture filter. The most common one that comes to my mind is filtering out the SSH traffic, especially my own SSH traffic when I'm logged into a device. Just by being logged in, my session is going to create a whole lot of noise, and I don't necessarily want to inflate my file size with that noise. So with a capture filter, we prevent that traffic that we're not interested in from ever making it into the file. Then we can use a display filter to refine how we look at the file. For instance, we can follow DNS queries, HTTP requests, etc., and look at them in the context of each other. Let's look at a couple of capture filter examples. On the left, we have a couple of TCP dump commands. We're invoking TCP dump, we're specifying the interface is eth0, and we're writing to a file called capture.pcap. We're doing the same in the second example. However, we're applying the capture filter port not 22, so no server-side SSH traffic. We have the same examples on the right using Wireshark, or T-Shark as the CLI version is known, and the capture filters are going to be the same syntax due to both using libpcap, the library for network capture. So it's the same capture syntax. Let's get behind the command line and look at some examples. So the server architecture here is something you're familiar with. 10.0.1.10 is our server 1. It's running Apache. 10.0.1.11, what I'm logged into here, is our client. And I've installed both TCP dump, Wireshark, Telnet, bash completion, and some other stuff. So the first thing I'm going to do is just run TCP dump with no switches, and we'll see just a lot of traffic going back and forth. Now that all, if you're sharp-eyed, you'll notice that I am logged into 10.0.1.10, and I'm then subsequently logged into 10.0.1.11. So the SSH session is coming from 10.0.1.10. Now I could use TCP dump, and we'll say that we don't want to see that SSH traffic. And I don't necessarily want name resolution either, so I can just show that to you. So with attack end, it's going to drop the name resolution. We'll specify the interface as ETH0, and we'll say port not 22. And so now if there was any other traffic other than SSH traffic going through ETH0, we would see it here. There's not, so we're going to have to generate some. Now likewise, we could do TCP dump and use NI ETH0. And we could specify a host. So in this case, 10.0.1.10. Now, since I'm logged into that, we're going to see all that SSH traffic again, but we can narrow it down to traffic with that host. So if there was a host in particular that you were troubleshooting and you wanted to watch the traffic between this and that, you could narrow it down like that. So let's generate some artificial traffic. To do that, I'll just create a traffic.sh script. I'll paste a little for loop in there. So for I in 1 to 100, do curl this, send all the output to dev null, wait 5 seconds and do it again, and it'll do that 100. Let's make it executable, and let's run it and get my prompt back. Okay, so now it's running. So we've generated some traffic. We can, probably one of the most common TCP dump commands that you can run, at least in my experience, is just TCP dump tac VV. So very verbose. And then we'll just specify the source. So 10.0.1.10, so this is traffic coming back and not destination port 22. So I don't want to see any of that SSH traffic occurring between me and there. And we can watch, and it's just going to print out every single request. And so I'll control C out of that. So that's all traffic but the SSH. We could narrow that down. Maybe we don't want to see it as verbose. We can use TCP dump, and we'll just do the N because we don't want resolution, I because we're specifying ETH0, and we'll say port not 22. And so now we see those web requests going back. You see some ACKs. So that's pulling that information. Now, maybe we want to see the ASCII output. So we want to see the ASCII data flowing back and forth. We can use TAC A, and we're going to go back and see the raw HTML when it starts going through. So if I scroll up a little bit, you'll see that raw HTML. Now we can do the same thing, and maybe we want to write this to a file. So we can write it to capture.pcap with the TAC W. And if my script is still running, it might have timed out by now, but if it's still running, it's going to send that data into that capture.pcap file. So then if I look at the file, we'll see there is some data in it, and we can use TCP dump with a TAC R to read, and we will read capture.pcap, just like that. So those are some TCP dump examples. TCP dump is super useful for creating packet caps, looking through packet caps. There's a tremendous amount of documentation. It is an absolute scalpel when it comes to looking into network packet capture. And you do well to at least be somewhat familiar with what it's capable of so that you can look up the necessary syntax and switches when you need to. So we can do something similar with Wireshark, and Wireshark is installed, and Wireshark's command line application is tshark. So let's use tshark, and we'll do not port 22, and I want to write to temp, and we'll just call it shark.pcap, and we'll go. And so it's running as user root, group root. This could be dangerous, naturally, promiscuous mode, all that good stuff. We've captured 10 packets, and so this is just going to run, and now I need to generate some traffic. So let me get screen going here and start, well, not that, start a session over here on the right. And so I can do a DNS query against Google. Maybe we'll try to ping google.com, which we won't be able to. I think ICMP is blocked. We'll throw a couple different pings in there. Let's ping 10.0.1.10. I know we can reach that one, so we'll let that run a little bit. Let's run telnet to 10.0.1.10 over port 80 because we know that's there. And I'm just going to do find me. I'm going to send that. It's going to be garbage. It's going to connection closed. And so I think that's probably good enough. Let's stop our PCAP, and now we're going to open it up in Wireshark proper. So I'm going to download this file and open it up in the Wireshark GUI. And so before I can do that, I obviously need to change my file permissions so that I can get in there and download with the cloud user account. All right, so I've opened up the PCAP file, shark.pcap. I've downloaded it to my desktop. I've opened it up in Wireshark's GUI. And you see the time 0.0000. That's when we started the PCAP all the way down to the bottom, which will be when I hit Control-C and knocked out of the PCAP. And so what's going on here should be somewhat familiar. We see a SYN, we see a SYNAC, we see the ACK, we have a GET, and we've got some application data flowing back and forth. Now we can look at, say, any one of these, and if we look down here, we've got the packet details. So if you'll remember, Layer 1, this is your physical layer, bits going across the wire. Layer 2, right here, MAC addresses. Layer 3, we have IPs. Layer 4, we have TCP and ports. And then layer 5 is our application data right here. We have our hypertext transfer protocol, so it's an HTTP GET request. So you've got your packets up here, your captures up here, and you've got the data for each individual packet down here towards the bottom with all of the requisite layer information. Now, we can apply some display filters here. So if we just wanted to see the DNS information, I could use DNS. And here's our query when we tried to look up Google. So you'll probably remember this from our DNS lesson. And then, of course, there's the response. And we can come down here and we can see the response if we dig down. And come down here to the answer section. So there's the query section. There's the answer section, 172.217.1578. Now, we could modify this filter. We could say DNS or ICMP. Remember, we did some pings, and we had the pings that wouldn't work. And so they're represented here. And we also did some web requests. So we can go up here and clear this filter and just set it to HTTP. And then here are all of our web requests that we made. And of course, we can clear the filter to look at everything. And if you remember, we sent that telnet data where it just said, find me. We can come in here and look for that. And here it is down in the raw packet data right here as ASCII. Packet captures are a lot of fun. They're one of those things, they're kind of mysterious until you start working with them a little more, and then everything just starts really coming into place. And so I'd highly encourage you just to run some packet captures on like your home network. You know, obviously you got to be careful doing this in a corporate environment, and you don't want to trigger any security individuals. But I definitely encourage you. And you know what? You can also download tons and tons of packet captures off the internet. And I'm going to make some available for download as well, just to go in there and look at them, play with them, do the sorting through the display filters, search for things, become familiar with the color scheme. Wireshark is a tremendously powerful and useful tool for all things networking. above and beyond just getting a packet capture to send to your network engineer so that he can fix the problem. It's great to be able to look at it and say, hey, here's what's going on. So that wraps up packet captures. This lesson is now complete. Thanks for watching. Hi and welcome. In this lesson, we're going to start talking about some advanced networking use cases, beginning with port forwarding. This is where things start getting really cool, so let's get started. Here is a sample architecture. This is a fairly standard setup in that you have an externally available web host, and then you have an internally available host as well. So maybe the internal host is a database server, an application node, something of that nature. The point being is that it's not directly available to my connection on the far left. So let's walk through it a little more. Server 1 is 10.0.1.10, and that internal IP is NATed to a public IP, and it's running a firewall. Server 2 has internal IP 10.0.1.20 and isn't NATed, so it is only accessible through server 1. If we wanted to SSH to server 2, we would need to SSH to server 1 first, and then SSH to server 2. Server 2 is also running a firewall. Then, within this internal network, between server 1 and server 2, connectivity is limited to ports 22, 80, 3306, and 8080. On top of that, both of these hosts exist in an environment that limits incoming connectivity from the outside. It could be the rules of the VPC as it is in this case or something else, but either way, there's policy or configuration limiting access from the outside. And in this case, ports 22, 80, and 8080 are available for ingress. So prep work. Whenever I'm working with something like port forwarding or any kind of somewhat complex networking implementation, I'm going to try to minimize complexity. And I'm going to do that by limiting or eliminating configuration variables. Now, you can't always do this, especially in a production environment, but there's generally some strategy you can leverage to keep the complexity reduced. Additionally, in part of eliminating variables, I verify connectivity prior to changing the config. And what I mean by this is that if I wanted some kind of traffic happening over, say, port 8080, I'm not going to jump straight into setting that up. I'm going to use a netcat to listen over 8080 and verify I have that connectivity first. It's easy to jump into the configuration prior to performing those basic sanity checks. Next, I'm only going to change one thing at a time. Unless what I'm working on is pretty trivial or I'm just very familiar with it, then I'm going to iterate over my configuration with each change. Again, the point is to eliminate variables, so that if I break something, it will always be the last thing that I did and not something 5 steps or 2 weeks ago. Lastly, and this one can be tough, don't get frustrated. This is especially oriented towards IP tables, which can really get you irritated and pounding away at something you think should work but just doesn't. Especially when you start getting into complex rule chains. Remember, order is everything with IP tables. So let's talk about a use case. We have these 2 web servers in the architecture noted earlier. One is publicly facing, one is internally accessible only. The use case is for illustrative purposes, so don't get hung up on the fact that they're both just running Apache. One could be running a web tier, the other some middleware or a database. We're just working with ports 80. So for our purposes, maybe we have an externally available public site and then some kind of internal site for organizational documentation. And we can see the ports we have to work with. So internal to the network of the servers, we have 2280, 3306, and 8080. And then external from the world, we have 2280 and 8080. And we're not going to want to clobber port 22 with anything because we need that SSH connectivity. And we're probably not going to want to clobber port 80 with anything because these are web servers after all. So we really just have port 8080 from the outside to work with. So here's their layout. If I make a request over port 80 to server 1's public IP, I will get the website there. But I want to set it up so that if I make a request to server 1's public IP over port 8080, that request will be forwarded to server 2 and I'll be able to view that content. So let's look at the prep work needed to set that up. I'm logged into server 1, 10.0.1.10, and the first thing I'm going to do is verify that Apache is running both on server 1 and on server 2. So I'll curl the local host so that we can verify server 1, and there it is. And then I'm going to curl 10.0.1.20. That's server 2, and I can see I get back server 2, so both Apache's running on both. Next, I'm going to need to verify that port 80 is externally available on server 1, so I'll need to do that from my desktop. And so from my desktop, I'll put in the public IP, I'll curl it, and I get back server 1, so we're good to go there. There's no way I can hit server 2 from my desktop, so I'm not even going to try. The next thing I want to do is verify that port 8080 is accessible to me to server 1. And so if we were to try to run telnet now, 54.144.41.70 over port 8080, that's going to fail because there's nothing listening over port 8080 and it's probably blocked at the firewall. So I'm going to need to jump over to server 1 and resolve that. So back on server 1, the first thing I'm going to do is firewall command, and then I'm going to add port equals 8080 TCP. So now I can at least receive that traffic coming in. The next thing I need to do is install netcat and then listen on that port and make sure and verify that I have that connectivity from the outside. So I'll nctac L over port 8080. I'm listening. So I'll jump back to my desktop now and see if I can make that connection. And so back on my desktop, I'll try telnet again and I can connect. And so now I'm good to set up that port forwarding. It's really important to get these sort of pre-checks out of the way. You don't want to have spent 15, 20 minutes or even an hour troubleshooting some firewall rules only to find out that the whole reason it didn't work was because you don't have that basic connectivity. So for instance, if I was trying to do this over port 443, that just would never work. It's a privileged port. It's blocked at the VPC. And despite all of my efforts on server 1, I would never be able to get that port forwarding working. This lesson is now complete. Thanks for watching. Hi and welcome. In this lesson, we're going to take a look at a couple of port forwarding examples using both IP tables and Firewall D. This is going to be a somewhat lengthy video, so let's get right into it. A quick review of the architecture. Just like in the previous lesson, we have an externally available server 1 whose internal IP is NATed to an external IP. We have an internally available server 2 with no external IP. Both are running Apache, and the internal network ports available are 2280, 3306, and 8080. The external ingress ports available are 2280 and 8080. Each host is also running a firewall that may need to be managed to permit incoming web traffic. We're not going to be interacting a lot with server 2 outside of just viewing its web content. So let's get behind the command line and see what we can do. All right, so we'll start with IP tables. I have masked off Firewall D and I've installed and started IP tables. So for this first example, I've modified Apache to be listening over port 8080 instead of port 80. So if I SSLNTP, you'll see that Apache is listening over port 8080 there. And since IP tables has just started, I don't have any rules permitting incoming traffic over port 80 or 8080. And we've already gone over how to add a port, so I won't do that. But let's say we want to take those port 80 incoming requests and we want to forward them to port 8080. So I'm server 1. I want to take traffic incoming to me over port 80, those requests over port 80, and I want to redirect them to my own port 8080, where Apache is actually listening. So let's take a quick look at the running configuration for IP tables. And so this is just vanilla CentOS 7 IP tables. We have our input chain there ending with a reject. We have our forward chain ending with a reject. And then we have an output chain. And we're not doing anything with the NAT table or anything else. This is a fresh install. So if I want to take that incoming request, and let me just show you the NAT table real quick. It is perfectly empty. So if I want to take that incoming request, that traffic coming into me over port 80, and send it to port 8080, I need to add to the pre-routing chain of the NAT table. So the moment it hits the network stack, I need to do something with it. And so to do that, I'm going to use IP tables tnat because we're adding to the NAT table. I'm going to append, which is safe because you see there's nothing in the pre-routing table, to the pre-routing table. The protocol is going to be TCP. The destination port is port 80. So coming in, destined for port 80. And I want to jump to redirect. and I want to redirect it to port 8080. So take what's coming in on port 80 and send it to port 8080. Now, I could test it, but it's not going to work because we still don't have port 8080 or port 80 open. So I need to add an input to permit that incoming port 8080 traffic. So the pre-routing's being handled before the filter. And so port 8080 is the port that I need accessible, not port 80. And so I'll use IP tables, TAC L, and I'm going to use line number. And so I see that I'm going to need to add something above line 5. So I'll add it at line 4. And to do that, I'll use IP tables, insert at the input chain on line 4, protocol TCP, and I want to match the state, a state of new, because remember, related and established already picked up there on line 1, and TCP, and then that destination port is 8080. And of course, we want to jump to accept. This is traffic we want. So now I should be able to check it from my desktop. So when I hit server 1's public IP, when I make that curl request over port 80, I should get the Apache content when Apache is listening on port 8080. And it works. So curl 54.144.41.70 comes back server 1. We're good to go. Even though Apache is listening on 8080, we're forwarding it from 80. So if I were to try to pull that 8080 traffic, I'm also going to get it because that's where Apache is listening. So that's one use case. That's kind of fun, you know, moving ports around and stuff. What if we wanted to do something a little more interesting? Let's say we want to make those port 8080 requests to server 1, and we want that port 80 traffic from server 2 to come back. So just like in the last lesson when we were talking about the use case, when I hit port 80 to server 1, I want server 1's web content. When I hit server 1 over port 8080, I want server 2's content. Let's do that. And to do that, I'm going to hop back over to server 1, and I'm just going to restart IP tables since we're only working with the running config here. Clear my screen, and let's talk this through for a minute. We need to take incoming requests. So our destination port will be 8080, and we're going to have to do something with them so that our destination, final destination, will be 10.0.1.20 over port 80. So again, we're going to use the NAT table. I'm going to use IP tables, TNAT, and I'm going to add a pre-routing. So just like when we were doing the regular port forwarding, protocol will be TCP. Destination port is 8080, so traffic coming in over port 8080. I now want to jump to the destination NAT, and my to destination is going to be 10.0.1.20 port 80. So we have added that rule. That is now going to take everything coming in bound for port 8080 and shoot it over to 10.0.1.20 port 80. Now, in order for this to work, we're going to have to enable masquerading. So we need to be able to replace that source IP address with server 1's own address for this to work. And so to do that, I will use IP tables, TNAT again. We're going to add to the post routing chain, and we're going to jump to masquerade. Now, lastly, if we look at the IP tables again, we're doing some forwarding, and the only rule we have in the forward chain here of the filter table is that reject. So we need to add a forward rule or two. So I'm going to use IP tables, insert to the forward chain, and since we're not specifying a table, it's the filter table. Protocol is TCP. Our destination is 10.0.1.20. That's where it's being forwarded to. And our destination port is 80. That's where it's being forwarded to. We want to match the state where state is new. And then we want to jump to accept. And we'll have to make sure that we put the S on the end of IP tables. So that's new. That's okay. But we also need related and established. So I'm going to use IP tables, insert. Now remember, this is inserting, So it's going to be at the very top. So this line's going to come before everything else in this forward chain. And we're going to add it to the forward chain. We'll match the state where the state is related, established. And we want to jump to accept. So now if I look at my IP tables chain here for forward, and we can do it with the ports, we see in that forward chain, the very first line is accept. So if state's related or established, go ahead and accept it. Right after that, if it's TCP destination port 80 and the destination is 10.0.1.20, then we're accepted. And before we test it, we're going to have to open up port 80 because right now only port 22 is added and we've added this forwarding. So I'm going to use IP tables, insert at the input level, and we'll do it at line 4. Our protocol will be TCP. We want to match the state of new. The destination port is 80, and we want to jump to accept. And I'm pretty bad about not getting the S on there. So now we have that rule. We should be able to pull the regular server 1 web content. Now I'm going to need to make sure that Apache is listening over port 80 again. So we're going to update 8080 to just 80. We'll restart Apache. And we should be good. Let's hop over to the desktop. So when I curl the public IP of server 1, I expect server 1's web content to come back. And when I curl the public IP of server 1 over port 8080, I want to see server 2's web content come back. Let's try it. So back on my desktop, let's try just the IP. We get back server 1. Let's try it with 8080, and we get back nothing. I have a feeling we need to enable IP forwarding. So let me hop back over to server 1. And to see if IP forwarding is enabled, I'm going to cat proc sys net IPv4 and then IP underscore forward. It is turned off. So I need to echo a 1 into that same file, proc sys net IPv4 and then IP underscore forward. You can do this with syscontrol if you want it in a more persistent state. So now we've enabled IP forward. Let's try it again from my desktop. We curl it, we get server 2. So now if I just pull the IP of server 1, I get server 1's web content. If I curl the IP plus port 8080, I get server 2's content. And that is how you do it with IP tables. Let's take a quick look at how we can do this with Firewall D. It's a little more streamlined, it's a little more intuitive, and you don't have to worry about echoing an integer into proc sys. So let me head back over to server 1, and I am going to system control stop IP tables. And I'm also just going to mask it off so I don't have to worry about it starting back up. So now I'm going to use system control, unmask, I'm not sure if it's masked or not, Firewall D, okay? And now I can start it up. So now we're running Firewall D, I'll clear my screen, and we can do this as a Firewall D example. So if I want to go back in and modify Apache again, we'll just do the exact same thing. I know this video is getting kind of long, but hang in there. Let me modify this to listen back on 8080. And I'll restart Apache. And so now to use Firewall D, we'll just pull the running config real quick with list all. And we can see it's vanilla. HTTP is open. But otherwise, we're not doing any masquerading, we're not forwarding any ports. So HTTP is open, but 8080 is not added. And 8080 is what Apache is listening on right now. So let me go ahead and add 8080. So now 8080 is open. Now let's forward all requests coming in over port 80 to 8080. And with Firewall D, that's really easy. It's just firewall command, and we're going to add forward port. And then here's where the syntax gets a little interesting. We're going to do equals port, And of course, port equals 80 because that's what's coming in. And we're going to use a colon. Protocol is going to be TCP in a colon. So we're using colons instead of spaces, and it'll make sense why here in just a moment. Our 2 port, because, and keep in mind, this isn't a rich rule, is going to be 8080. So add forward port equals 80, protocol's TCP, send it to port 8080. So we've done that. So now if I go back to my desktop and curl it, 8080 is not open, so we're just going to curl it regular. And even though Apache's listening on port 8080 and we're requesting over port 80, we're seeing the content, just like with IP tables. So let's go back and look at the rule. If I go up here and I look at the list all again, you'll see down here under forward ports, we've got port equals 80, protocol equals TCP, 2 port equals 8080. Then we have this 2 address. So we can do the same thing we were doing with IP tables. We can do that with this. So let me fix Apache to listen again on port 80. And we'll do the same thing we did with IP tables in that we will send those port 8080 requests to server 2. So Apache's listening on port 80, it's bounced, it's good to go. Let's add the rule. We're going to use firewall command, and just like above, add forward port, and port equals 8080. So if it's coming in on port 8080, protocol is TCP. Our 2 port is going to be port 80 because we're taking requests coming in on 8080 and we're sending them to port 80, but not of the local host. We're sending them to the address 10.0.1.20. So now if I look at the running config, we'll see that we need to get rid of this extraneous rule here for this to work. So I'm just going to copy it and use firewall command, remove forward port, and then just paste that. So now if we look, we should just have the 1. Goes back to that whole changing one thing at a time. Now if we were to try this, we would think it would work, but it's not, and I'll prove it real quick. I can curl that normally, but when I request over 8080, I get nothing. And the reason for that is because we have not enabled masquerading. So just like with IP tables, we have to enable the masquerading. Now what we don't have to do is echo 1 into proxys, net, IPv4, IP forwarding. It is as simple as firewall command, add masquerade. And so we've added masquerading. Let's try it again. And now we're getting server 2 from port 8080. That is so much simpler than doing it with IP tables. I really hope you appreciate how much simpler that is. A couple final words. Keep in mind, we were just looking at web traffic, but you could just as easily do this to interact with, say, database traffic or something else. Keep in mind, though, there is probably a very good reason your database servers are not publicly accessible. And so you would probably want to take this to another level and add a source IP so that only certain IPs were forwarded through the chain like that. It's a very powerful tool. It's a whole lot of fun to use. It gives you a whole lot of options in terms of working with limited network ports and things like that. And sometimes it is just the right tool for the job. This lesson is now complete. Thanks for watching. Hi and welcome. My name is Michael, and in this lesson we're going to take a look at SSH tunnels, what they are, and why you might use them. Let's get started. Here's the basic architecture. This is the same from the other lessons, most notably the port forwarding lesson. So this should be pretty familiar to you. We have 2 hosts in a VPC. Each host has a firewall, and the internal and external network have constraints applied in terms of what ports are available for traffic. Then, of course, if those ports are used, the host firewalls themselves need to permit the connections. There are 3 types of SSH tunnel that you can create. The first is local. This is where you're hitting your local host over a port to access some kind of remote content. So let's say that the connection icon there on the left is you with your laptop, and you don't have direct access to server 2. Maybe there's a firewall between your local client and server 2, or maybe it's just network topography, but you cannot directly access server 2. However, server 1 is accessible, and server 1 can access server 2. Now, you could facilitate connectivity to server 2 using port forwarding. We went over that. But that would assume that you had root level access to server 1 in order to modify those firewall rules. So let's assume you don't have that access, nor do you want to make this available globally. This is just for you. The most common use case that comes to mind is a publicly available web server and an internally available database server. You want to interact with the database in some manner, maybe to make changes for development. You could use a local SSH tunnel and make the database port available on your local host so that you can log into it there. So for consistency, our demonstrated use case will be an externally available web server and an internally available web server, and we want to view the internal content. So server 1 has a public IP that we can access from our connected client. Server 2, however, is not accessible, but we want to view that content. We're going to create an SSH connection over port 22 to the publicly accessible host, which then has port 80 connectivity available to the remote host that has the content we want to see. We're going to build the tunnel so that we can view this remote content from our own device over port 8080. And so this is what that command would look like. We're SSHing using TAC-L for local. Our local host port, this is the port on our laptop, on our desktop, is 8080. Server 2 has the content we want to see. Keep in mind that this address is going to be from the SSH target host's perspective. So we could have 10.0.1.20 in there, as that's the IP that server 1 could connect to server 2 over. So server 2 has the content we want to see, and that content is served on server 2 over port 80. And then, of course, we have our username at the intermediate host, the SSH target. So using this command, we would be able to curl our local host on our laptop over port 8080 to see the port 80 served content from server 2 by using server 1 to build that SSH tunnel. It may take a few iterations for you to kind of get your head wrapped around what's going on here. Basically think of the host that you're SSHing to as kind of the intermediate host. It's the one facilitating the work that you want to have done. The second type of tunnel is a remote tunnel. So keeping the same architecture, let's say that server 2 cannot access our laptop, right? Because it's on the far left there. It's the connection. It's outside of the VPC. Server 2 doesn't have access to it. So let's say that that's my laptop and I'm performing some kind of local development on it, and I want to show my local service content to server 2. So maybe server 2 is my boss's computer and he wants to see what I've done. Both server 2 and myself can access server 1. So I'm going to create an SSH connection to server 1 over port 22, and I'm going to make my local content available there over port 8080, which then tunnels the traffic back to my laptop and makes the port 80 content there available to server 2. So the resulting command is similar to a local tunnel, only we're using TAC-R and saying that port 8080 on the intermediate host will tunnel to port 80 on my local host, on my laptop. Therefore, any connections to server 1 over 8080 receive the content that my local laptop is serving over port 80. The last type of SSH tunnel is a dynamic tunnel. This permits us to use an SSH intermediate host as kind of a proxy. So we'll create the SSH connection. We designate a port on that target host as our SOCKS proxy port. We could then configure our browser like Firefox to use that address and port as our proxy. And then all of our web traffic would pipe through there. This could function as a sort of pseudo VPN, for instance, if we had some internal web content not publicly accessible. We could SSH TAC-D to a corporate resource, configure our browser using that destination and port, and then browse whatever content was accessible to the SSH target. So that's kind of what's going on with an SSH tunnel, architecturally speaking. So keep this architecture in mind as we move to the next lesson. The next lesson, I'm going to actually go through some examples of each. This lesson is now complete. Thanks for watching. Hi, welcome. In this lesson, we're going to get into some SSH tunnel examples. If you remember in the last lesson, there are three types of SSH tunnels. There's the local, there's the remote, and then there's the dynamic. And so we're going to look at each one of those. A quick review of the architecture. Client 1 is within the same subnet as server 1 and server 2, but I'll firewall it off to sort of simulate being outside of the subnet and how you can get around firewalls. But otherwise, this is the exact same architecture that we've been using more or less the entire course. with server 1 having 10.0.1.10 and server 2 being 10.0.1.20. Client 1 will still retain the 10.0.1.11 IP. Server 2 is not publicly available. So let's jump into it. All right, so I am logged into server 2 here, and I have added a firewall rule, a rich rule, to block any traffic coming in from 10.0.1.11. That is client 1. So if you remember the architecture diagram from the previous lesson, imagine that client 1 is that connection icon on the far left. Then we have server 1 and server 2. So I'm simulating that separation by adding a firewall, preventing client 1 from being able to directly access server 2 at all. So from here on out, I'm going to be on client 1 and server 1 pretty much only. And if I curl localhost, you should see a somewhat familiar output. It's server 2. So I'm going to hop over now to client 1. So I'm now logged into client 1, 10.0.1.11. And if I try to curl 10.0.1.10, I'm going to get back server 1. And if I try to curl .20, I'm going to get a failed because of the firewall rule that exists. And so I'm going to install screen real quick just to make this a little easier to follow. And split my screen. So now when I make that SSH tunnel, I won't have to switch to another window. It'll be right here. And so what I want to be able to do is curl my localhost. I'm client 1. I want to be able to curl myself over port 8080 and get that port 80 server 2 web content. And so the way I'm going to do this is with SSH TAC L. And my local port is going to be port 80. I want the content from 10.0.1.20, which is available over port 80 on that server. And then I'm going to use the user cloud user at 10.0.1.10. And so now I have that SSH tunnel connected. Now on the right, I have SSH'd into server 1. So on the left, I'm still on client 1. And if I SSLNTP, we'll see that we are listening over the loopback address at 8080. So now if I curl localhost 8080, I'm getting server 2's content despite being firewalled. Now let me jump back over to the right here and we'll exit this. I'm not limited to just a single tunnel. So let's say I want both server 1 and server 2's content. I can do a TAC L. I will listen to myself on port 80. We will use server 1's IP. It's serving over 80. Put our password in. And if I SSLNTP now, I'm listening on port 80 and 8080. So if I curl localhost 8080, I'm getting server 2. And if I curl localhost over port 80, I'm getting server 1. Now, obviously, there are security implications with this, right? You don't want to start SSH sessions over port 2222 and things like that. So you definitely want to be mindful that you're using legitimate use cases with this. So let's log out of this and look at a remote example. Let me clean up my screen here. All right, my screen's cleaned up and I am on client 1 still. Let's add a firewall rule so that server 2 cannot connect to client 1. So to do that, I will use firewall command. I'm going to add a rich rule, and my rule family is going to be IPv4. My source address is going to be 10.0.1.20, so that's server 2. And I want to reject that traffic. So I do not want server 2 to be able to directly access me. So if you remember from the lesson where we were going through the slides on a remote forward, maybe this is a local development box, and I want my boss, who happens to use server 2 as his desktop, to be able to access my content. And so typically this would be something that wasn't on the same network or subnet, and so that's why I firewalled it off to kind of artificially create that environment. So if I curl my own local host, I see that I get back client 1. Cool. And if I curl 10.0.1.10, I get back server 1. And I can't connect to server 2, so I'm not even going to try. So in order for me to make my port 80 content available to server 2 using server 1, I'm going to have to create that port forward. So I'm going to use SSH TAC R because it's a remote forward. And my remote port is going to be 8080. So we're using port 8080 on server 1. And I'm directing that or tunneling that back to localhost, my, client 1 here, 10.0.1.11, port 80. And we'll log in as cloud user at 10.0.1.10. And so now that is created. Now, before this is going to work, and I can show you kind of, this is one of those things that will cause you to pull your hair out. Let me log into server 2 real quick. Now, I can't go straight from there. I'm on client 1 here on the right half of my screen. I can't log directly into server 2 because we have that firewall rule. So let me log in as cloud user to server 1. And let me log in again to 10.0.1.2 to server 2 as the cloud user. Now I can curl localhost. I can curl 10.0.1.10. No problem. If I try to curl 10.0.1.10 over port 8080, we're going to see we have a problem. Connection refused. Now, let me jump back over here to the left half. We have SSH'd into server 1, into 10.0.1.10. And if I curl localhost here, everything's fine. And if I curl localhost over 8080, I get it. And the reason you're seeing this behavior is because you need to modify your SSHD config. So vim SSH, SSHD config, and this gateway ports here has to be uncommented and yes. Can't be no, it has to be uncommented and yes. So I make the change, I'll restart SSHD. But more importantly, I'm going to close that connection and start the tunnel back. So I've restarted the tunnel and I've now moved back over here to the right. I'm going to try curling it again and now it works. So that's a remote. So now server 2, despite being firewalled off, can look at client 1's web content. This could be your development laptop. This could be a dev environment, a test environment, something like that. So that is a remote port forward. This video is running kind of long, but I want to squeeze in a SOCKS proxy real quick. And so to do that, I'm going to hop over to an Ubuntu desktop. So real quick, I am logged into my Ubuntu host here. This is my desktop. And I'm going to run SSH tech D 8080 cloud user, and this is server 1's public IP. So now it's connected. I'm going to hop down to Firefox here, and I'm going to go to Preferences here, and I'm going to search for proxy, click on that, and we're going to use a manual proxy, localhost, port 8080, because remember I used TAC D 8080. I'm going to hit OK, and now I should be able to go to 10.0.1.10 and see server 1. I do. I can go to 11. I can see client 1. I can go to .20 and I can see server 2. So that is a quick example of using it as sort of a SOCKS proxy browser. We're going to get into proxy browsers in the next lesson, and I thought this would be a pretty cool segue. This lesson is now complete. Thanks for watching. Hi and welcome. In this lesson, we're going to take a look at proxy servers, what they are, and why you might use them. Let's get started. We looked at using an SSH tunnel as a SOCKS proxy, but if we wanted to set up a permanent proxy for others to use, we'd need to set up a proxy server. So what is a proxy server? It's a host that acts as a proxy on behalf of client requests. So for example, when you make a web request through a proxy, the proxy is actually making the web request on your behalf and returning you the result. So what are some reasons you might want to do this? You could use a proxy to circumvent any kind of monitoring, blocking, or censorship, and you do this by leveraging a proxy in a location less subject to those restrictions. Alternatively, you can leverage a proxy to perform those actions against users. Say if you wanted to prohibit corporate web access to things like Facebook or YouTube. And you can use it for increased web performance by using caching. So if you have a corporate network and you have a lot of sites that are being accessed frequently, you can leverage proxy caching so that the proxy doesn't have to reach out and make that web request for every single request, and it can use the cache. So here's a simple example. A client computer has a TCP connection to a proxy host. In this case, it's over port 3128, which then manages the web requests for that client. Typically, the client needs to be configured to use the proxy server, or the gateway itself could be configured to use the proxy for transparent implementation. Probably the most popular Linux proxy is Squid. As defined by Squid's site, Squid is a caching proxy. It supports HTTP, HTTPS, and FTP, and more. It reduces bandwidth, improves response times by caching, and it has extensive access controls. So you can use these ACLs to create whitelists, blacklists, do a little traffic shaping, things like that. So here's an example use case. Let's say you have a small office of users and you want to leverage a proxy server to permit some kind of caching, content restriction through blacklists or traffic shaping. Maybe you want to deprioritize traffic to certain sites like YouTube or Facebook, or maybe you want to prioritize traffic to sites like travel booking and things like that, sites that are relevant to the office job requirements. And the way you could do this would be to leverage a Squid proxy and configure the user's browsers through GPO or some other mechanism to use the proxy server for that web traffic. So that's a proxy server in a nutshell. There's not too much to talk about with these. In the next lesson, we're going to get into installing and configuring a Squid proxy server. This lesson is now complete. Thanks for watching. Hi and welcome. In this lesson, we're going to install and configure a Squid caching proxy. Let's get started. A quick review of the architecture. We have client 1 at 10.0.1.11 and we have server 1 at 10.0.1.10. This is the same scheme I've been using the entire time. And I have verified that client 1 does have port 3128 TCP connectivity to server 1 in the VPC. So we'll still need to enable it in the firewall. And of course, each host has its own host firewall. And then of course, there's the VPC firewall. So let's log into server 1 and go ahead and install Squid. All right, so I'm logged into server 1, and the first thing I need to do is install Squid. So I'll use yum install tac-y Squid. And this will take a minute. It's not the smallest package, but it's not huge either. It probably takes 30 seconds to install or less. So now that Squid is installed, I need to enable it and start it. So I'll use system control, enable Squid, and I'll just make a one-liner out of it. System control, start Squid. So now it's enabled and running. And I need to enable this service in the firewall. And so Squid is a service recognized by Firewall D. So I can use firewall command, permanent, add service Squid. And then I'm going to have to reload to pick up that change. So now Squid is enabled, Squid is running, and it is permitting port 3128 TCP connections into this host through the firewall. So before we get into too much configuration, let me just show you the configuration file, which is at etsysquid.conf. And I'm going to grep out all of the comments, and they put the comments in line with valid configuration. So I'm just going to use a little pattern matching to filter out the actual non-working parts of the configuration, the actual comments. And so here we have the actual configuration file, and you can see at the top you have a bunch of ACLs, and then towards the bottom you have your denies and allows, and then at the very bottom you've got some refresh patterns. So an important thing to keep in mind is, similar to IP tables, the order matters in your Squid configuration file. So to run down this configuration file real quick, you can see we have the private IP ranges or private IP subnets at the very top, your 10.0, your 172.16s, your 192.168s, and then some IPv6 versions of the same. And then we're identifying the SSL port is port 443, and we're identifying what we consider some safe ports, or rather what Squid's default configuration considers safe ports, port 80, 21, 443, 7210, so forth. And then if you come down past the connect method connect, you'll see that we are denying things that are not safe ports. We're denying connections to non-SSL ports. We're allowing the local host to access the Squid manager. We're denying everyone else. We're allowing the local net to use Squid. We're allowing the local host to use Squid. And then we're deny. That's your deny all right after that. And then we have the port 3128. That's your default Squid connection port. a core dump directory, and then some refresh patterns. So without making any changes to this configuration, let's hop over to the client and set it up to use Squid for its connections. So I'm logged into client 1 now, and the first thing I'll do is I will export HTTP proxy to be 10.0.1.10 over port 3128. And so now if I curl tach linuxacademy.com, we'll get some headers. And you can see there towards the bottom, the via 1.1 IP 10.0.1.10 squid 3520. That just verifies that we connected through Squid and pulled the headers. So now I'm going to hop back over to server 1 and we're going to look in the logs. So back over here on server 1, let me clear my screen and let me tail var log squid access log. And we're going to see that request we made from client 1, IP 10.0.1.11. So I'll point this out to note that if you have a bunch of clients connecting through Squid, you can leverage the logging in any kind of log aggregation to pull some metrics around what sites are being visited, how often sites are being visited, things like that. And that can be useful when it comes time to update your blacklists or add things to your whitelists, and even verifying that your whitelists are being used. So let's make a change to the config. Let's go ahead and create a blacklist. So let me vim etsy squid.conf. And if you see here towards the bottom, you have this insert your own rules here to allow access from your clients. So this is the space we'll work with. And I'm going to create a new access control list. Let's call it blacklist. And we'll use the destination domain. And let's limit or let's prohibit access to apache.org, just for an example, and we'll use linuxacademy.com as well. So we have created the ACL. Now we need to create the access. So HTTP access deny blacklist. So ACL blacklist, anything going to the destination domain of apache.org or linuxacademy.com. And then we have our HTTP access section beneath that, and we're going to deny blacklist. And so I'll save this, and I'll need to restart Squid. And let me hop back over to client 1. So I'm back on client 1. Let's curl the header again, and what we get there at the very top is that 403 forbidden. So we are unable to access that site now. A quick note on SSL. Blocking SSL sites isn't as easy as what I've just done, but it can be done leveraging Squid through SSL bump, which allows Squid to perform or enable some ICAP inspection of SSL traffic. However, SSL bump requires a cert be created for all the SSL sites and then imported to the clients, and this can be somewhat cumbersome. So the next thing I'm going to talk about are delay pools. I had mentioned how you can use Squid to, say, limit some connectivity or prioritize some connectivity by limiting everything else. Let me clear my screen. I've installed a speed test, the CLI version of speed test on here. And I'm just going to run it, and we'll run it with the bytes command. So our download is 53.77 megabytes and our upload is 83.55 megabytes. That's really good. So let's hop over to server 1 and enable some bandwidth limiting on this subnet. So back on server 1, I'm going to go back in and modify squid.conf. And let's borrow a use case from earlier in the course. Let's say that the whole 10.0.1.0/24 subnet is kind of a kiosk subnet, and we don't want our kiosks hogging up a bunch of bandwidth. We want to apply some manner of constraint to the amount of bandwidth those hosts can use. And so I'm going to create a new ACL, and I'm going to call it kiosk, and we'll just use 128K because we're going to limit it to 128 kilobytes. And the source will be 10.0.1.0/24, so the entire subnet. We're going to have one delay pool, so delay pools will be 1. And then we have to specify a class for each pool. So delay class for pool 1 is going to be class 3. The documentation is not super robust around this, but know that if you are blocking a range or multiple IPs, your delay class has to be a 2 or a 3. So when you're aggregating buckets, you have to use 2 or 3 when specifying a group of hosts. So then we're going to add our delay access for pool 1, and we are going to allow kiosk 128K. And then we're going to pick up everything else and deny all. Okay, so for the delay pool, we're going to allow kiosk 128. So now we need to add the delay parameters. So for a class 3 delay pool, the syntax is going to be delay parameters, the pool, the aggregate, the network, and then the individual. So we're going to add delay parameters. The pool is going to be 1. Our aggregate is going to be 64,000, 64,000. And so in this case, the numerator is the volume of the flow buffer or in bytes, and the denominator is the max allowed. And so we want to keep those the same for this. So for the aggregate, we're 64,000 and 64,000. Now for the network, we don't want any limit. And then for the individual IP, and I understand this is in the weeds a little bit, but the documentation is somewhat okay for the delay parameters and the syntax and that sort of thing. And this is just an example of what you can do with it. So for the individual IPs, so we've set the network size to 64,000, which works out to 512K. And we want to get each IP down to 128K. So each IP then is going to be 16,000. You have to do a little math. Over 6,400. Now, if we save this configuration and restart Squid, and then we hop over to client 1 and we'll try the speed test again. So back on client 1, let's rerun that speed test in bytes. And it may take a little bit longer this time to run. And I may have to speed up the video a little bit. And so you can see we have severely limited the download capacity for this subnet going through Squid. And so the last thing I was going to mention is that you can set up Squid as a caching server. To do this the right way, you would want to have a fairly robust disk or partition that you could point Squid to use as its cache. But you could also have it use file caching just under var spool Squid. And this could be useful if you wanted to, say, speed up server updates if you're not using a satellite server or WSUS or something like that. You could speed up software updates by creating a special rule just to permit caching of that content. Likewise, if the VPC permitted port 3128 in, you could set up Firefox or some other browser on your local desktop or laptop to leverage a Squid server for all of your browsing. Kind of like we did with the SOX proxy on the SSH tunnel. Squid's a pretty deep subject. I have kind of skimmed the surface here. Really, my intent was to expose you to it, show you what a proxy server is, kind of how it works, what it does. You can spend days, weeks, months into the documents and the man pages and all of the minutia of Squid configuration. You can really get into the weeds with it and do some cool stuff. It's a Swiss Army knife, but it's not always the right answer for every sort of traffic shaping configuration that you would want to apply to your network. But it's free, it's usable, and it's functional, and it's worked really well. That wraps up this lesson. Thanks for watching. Hi and welcome. In this lesson, we're going to be taking a look at load balancers, what they are, and why you might use them. Let's get started. So let's start with what load balancers are. Load balancers act as a traffic director to distribute and manage traffic across the backend nodes. So for instance, if you have a group of web servers all hosting the same site, you could place a load balancer in front of them to distribute that traffic coming in. Why would you want to do this? Well, it grants redundancy and high availability in your application infrastructure. So in typical cluster fashion, if one node fails or is down for maintenance, the others manage the workload. It also permits the horizontal scaling of your application infrastructure. So instead of constantly increasing CPU and memory, you're able to handle the workload with a larger number of less provisioned hosts. And it permits some architectural flexibility. And what I mean by this is that it gives you the ability to manage the back-end nodes independent of application availability. So for instance, if you wanted to take a portion of the infrastructure down for maintenance or some kind of a migration, this is easily done. Likewise, if a node is misbehaving, you can simply remove it from the pool and then reinstantiate it, which is something necessary in a fully automated environment. So here's a simple example. The client sends the request to the load balancer, and then the load balancer passes that request onto a backend node. So for the sake of example, let's say that the application nodes are Apache hosts and the client makes the request for the site over port 80 or 443 to the load balancer. The load balancer then uses an algorithm to determine which backend node should receive the request depending on how it's configured. So let's look at those algorithms or modes that the load balancer might be configured to use. The first, and typically the default, is round robin. The requests are distributed sequentially. So if you had 3 backend nodes named A, B, and C, the first request is going to be sent to node A, the second to node B, the third to node C, the fourth to node A, the fifth to node B, and so on in sequence. Another mode is least connections. So new requests are sent to the node with the least current connections. So the load balancer will need to keep up with the amount of connections to each node and then favor the node or nodes with the least number of those connections. And the last is source or IP hash. So the IP of the client is used to determine the backend destination. One thing to keep in mind with load balancing is, let's say you have a web app that is not stateless and it uses some manner of non-shared session handling. Each request from the browser has the potential to land on a different backend node, and this can cause some really interesting troubleshooting scenarios. So for instance, if you had 2 backend nodes, the app may only work half of the time. And one way to mitigate this is through session persistence, or sometimes called sticky sessions. Session persistence is used for maintaining session integrity by sticking to the same node. Another thing I'll mention is there are hardware and software load balancers. Hardware load balancers are typically a vendor-provided appliance loaded with proprietary software, and software load balancers are simply software, proprietary or otherwise, that run on commodity hardware. Software load balancers are what I'm focusing on in this lesson, but the concepts largely apply to both. So in order to use a load balancer, it needs to be configured. And by and large, all load balancers need the same basic information about the front end as well as the back end. On the front end, the load balancer needs to know what protocol or mode of TCP connections are coming in. The example we'll work with is HTTP, which are web requests. It's also going to need to know what mode it should operate in, so round robin, least connected, source IP hash, etc. And it's going to need to know what port to listen on. So we'll be listening on port 80 in our configuration examples. As for the back end, it's going to need to know where to distribute the incoming requests. The 2 main software load balancing services I'm going to focus on are Nginx and HAProxy. These are 2 extremely common and free software load balancers used for balancing web workloads. They're similar, but they do have their differences, so I'll focus on the differences, and then in the next lesson we'll begin configuration. Nginx can function as a caching web server as well as a load balancer, and this is handy as Nginx is a great high-performance app server. On the load balancing side, the metrics or statistics provided are kind of lean. However, there is a paid and supported version that provides significantly more flexibility in metrics, albeit at a cost. As for HAProxy, HAProxy provides robust metrics right out of the box. It's easy to integrate with third-party monitoring solutions, but it does not provide web server capability. It is limited to just being a load balancer. So this is a basic introduction of load balancing, specifically software load balancing, and I chose Nginx and HAProxy as they're easy to install. They work really well. They're well documented. And in the next lesson, we're going to get back behind the command line and look at some example configurations for both of these. This lesson is now complete. Thanks for watching. Hi and welcome. In this lesson, we're going to install and configure an HA proxy load balancer for a couple of back-end Apache nodes. Let's get started. A quick review of the architecture. I'll be working completely inside of the VPC, testing with client 1 with its usual .11 IP. Our load balancer will run on server 1, and then we'll have two Apache nodes that I'll refer to as node 1 and node 2. They'll have Apaches 10.0.1.20 and 30 respectively. For practical purposes, you can kind of look at it like this, as our clients would normally be external to the VPC. I only have it in there for completeness. Likewise, the firewall of the client is immaterial, but I include it for architectural completeness. So if this were a live example or a live production environment, you would have your environmental ingress firewall as well as the specific host firewalls to negotiate. In my examples, the ingress firewall is configured in the CloudFormation script, so for the purposes of this demonstration, we don't need to focus on that either, leaving us with just what's on the screen now. I'll need to configure the firewalls for the load balancer and the app nodes. Let's get behind the command line and get started with installing HA proxy. Okay, so I'm logged into server 1, 10.0.1.10. The first thing I'm going to want to do is install HA proxy. So I'll use yum install HA proxy, and this is a really small package. It only takes, I don't know, maybe 10 or 15 seconds or less to install. There it is. The next thing I'm going to want to do is go ahead and enable and start HA proxy. And I'll just do it in a one-liner. System control, enable HA proxy, then system control start HA proxy. And I need to open port 80 in the firewall, so I'll use firewall command, permanent add service, and I'm just going to add HTTP. So it's already enabled. That's perfect. The next thing I want to do is I want to hop over to node 1 and node 2. And the reason is I want to set Apache to listen on port 8080 instead of just port 80. So let me log into node 1 and node 2 real quick. And I'm on node 1 here, and I want to modify the etc httpd conf httpd file, and I'm going to search for listen port 80, and I want to change this to 8080. And then I'm going to restart Apache. And I'm going to do the same thing on node 2. So node 2, vim, etc httpd conf httpd.conf. I'm going to search for listen on 80, and then I'm going to modify that to 8080 and then bounce it. And so I can verify that with an SSL-NTP, and we can see we're listening now on port 8080, that third port down. So since we're listening on 8080, I do need to modify the firewall for node 1 and node 2. I'm still logged into node 2 here, so I will use firewall command, permanent, add ports, and we'll do 8080 over TCP. So it's add port, not ports. And I will use firewall command, reload to pick that up. And I'll need to do the same thing on node 1. So on node 1 here, firewall command, permanent, add port equals 8080 TCP, and reload to pick it up. Okay, so now we're done with node 1 and node 2. They're running Apache. Everything's good there. If I curl the local host on each, you'll see it just comes, well, if I curl the local host, you'll see it comes back connection refused over port 80. And if I curl localhost over 8080, you'll see that we get node 1. And likewise on node 2, it'll respond node 2. So we're done with node 1 and node 2. Everything here from here on out is going to be on server 1 and then testing through the client. Although I may come back at the end and go ahead and stop Apache on one of the nodes to show you how the load balancer sends all the traffic to the up node. So let's move back to server 1 now. So on server 1, HA proxy is installed. HTTP as a service is already enabled to the firewall. So I'll clear my screen. And we need to configure HA proxy. And so we'll do that by editing the etc HA proxy, haproxy.cfg file. And this is a fairly well documented and commented file. First of all, it tells you where to go for a lot of documentation around all of the configuration items here at the very top, that web link. And if we come down, it tells you what you need to do to get certain logging features working. And then we come down here and we see a bunch of common defaults. So if we start up at the top, we kind of have our global section with some global options. So maximum connections is going to be 4,000 unless overridden in a block down here. And then we kind of have some defaults set. So the default mode will be HTTP, global logging, things like that, some timeouts. And so you want to keep your timeout for the client and the server the same. In this case, they're both 1 minute. And then towards the bottom, we have basically some example front ends and back ends. And so what I tend to do is when I get to about here, I blow everything else away and I start adding my own configuration. And so in this case, remember we need to provide some front end information and then some back end information. And for HA proxy, usually the front end goes in the top portion and then the back end goes after that. So I'm going to add some front end here, and we'll just call this the demo app. It's a demo application. It's just pointing to node 1 and node 2. And so we'll just say that the root index on node 1 and node 2 is our demo app. We're going to bind it to all interfaces over port 80. So that would be our public and our private if we had this set up as a dual host system. Our mode is going to be HTTP. So we want to listen for those HTTP connections. And so for this front end, our default backend is going to be, we'll just call them Apache nodes. So this tells this front end what backend to use. So we've specified the default backend is going to be Apache nodes. So we need to create the backend Apache nodes. And so these nodes will be listening in the mode of HTTP. They are HTTP nodes. For balancing, we're going to use round robin to start, and then we'll switch it up here in a minute. I like to add the option of X forward 4, so we'll just use forward 4. And what this does is it adds the X forwarded 4 header so that the applications themselves see the client IP and not the load balancer IP as the requester. And there are obviously many more options than what I'm using. I'm basically just giving you a bare bones load balancer setup here using HA proxy. And so after your options, you're going to add your servers. So we're going to have server, and we'll call it node 1 at 10.0.1.20. And we'll have server node 2 at 10.0.1.30. And we want to enable some checks, so we'll just add check after this. And that should be it. We should have a functional config now. So if we system control restart HA proxy, and then we curl localhost, we get back connection refused. So this is a little unexpected. Obviously a layer 7 issue going on here. Let's troubleshoot it real quick. And if this takes too much time, then I'll just cut it from the lesson. Obviously, the first thing I'm going to do is make sure we're listening over port 80, and we're not. So I'll use system control status HA proxy to see if it's running. And we have a failure. So there's something going on in our configuration. So let's take a look at our configuration again. And we have front-end demo app. We're listening over port 80. Mode is HTTP. Our default backend are the Apache nodes. We created the backend Apache nodes. The mode is HTTP. The balance is round robin. Our option is forward 4. And we did not specify ports for our servers. So that is where I have made a mistake. So now that that's been fixed, let's go ahead and restart HA proxy. And now we are listening over port 80. So if we curl localhost, we get back node 1. So now, since we're in round robin, I should be able to do something like a for loop. So for I in 1 to 10, do curl localhost. So basically for 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 times, curl the localhost. Done. And it would help if I put the for I in here. And so we're going to get back as, node A, node B, node A, node B. So 2, 1, 2, 1, 2, 1, 2, 1. And you should be able to see that right there as the response. So let's change that load balancing mode. Let's go back in and we'll say that for balance, we want to use, I could use least connected, but since it's just me hitting it, it's going to do the same thing. It's going to be 1, 2, 1, 2, 1, 2, 1, 2. So let me change it to source. And what source is going to do, let's bounce it real quick. And what source is going to do is it's going to apply some best effort stickiness to the clients, so let's say we had clients that did not permit session cookies or anything like that. This would apply some best effort stickiness to those clients, so long as your total number of servers didn't change. And in that case, we could use something like weighted hosts in our round robin or use cookies to achieve session stickiness. So let's go back to our for loop, and what we see is we are now stuck to node 2. So let's hop over to node 2 and shut it down. So I'm on node 2 now, and I'm going to system control stop HTTPD, and we're going to hop back over to server 1. I'll clear my screen. We were node 2 only. Let's try it again, and now we're node 1. And so it's load balancing effectively. It's sticking us to just one node. And the one we're kind of bound to becomes unavailable, we go to another. So with HA Proxy, there are additional load balancing modes, such as static round robin, if you don't want to adjust the round robin weighting while running. Speaking of which, you can adjust round robin weighting. So if you have an aggregation of servers and some of them are more well provisioned than others, you can kind of apply more traffic to the hosts with the more resources. There is a URI method, which takes a portion of the URI, it hashes it out, it performs some logic based on the weights of the running hosts so that the same backend nodes handle the same endpoints. So for instance, if you wanted to have a more well-provisioned host handle more resource-intensive application loads, like shopping cart checkouts or large calculations, you could do it using that mechanism. And with HA Proxy, there are a few others as well. Again, the HA Proxy documentation is fantastic. That wraps up this lesson and demonstration using HA Proxy. In the next one, we'll get into it with Nginx. This lesson is now complete. Thanks for watching. Hi and welcome. In this lesson, we're going to install and configure an Nginx load balancer for a couple of backend Apache nodes. So let's get started. A quick review of the architecture. This is exactly like the previous lesson, the HA Proxy example. I'm working inside the VPC with client 1 and its usual IP. The load balancers are on server 1. And then we have our two Apache nodes referred to as node 1 and node 2 at IPs .20 and 30. For practical purposes, we're not worried about the VPC firewall, as our clients would normally be external. Likewise, the firewall of the client's immaterial. It's included for architectural completeness. So if this was a live example, you'd have to deal with the ingress firewall as well as your discrete local firewalls of the load balancer and application nodes themselves. And in my example, the ingress firewall is configured at the CloudFormation script level. So for the purposes of what I'm demonstrating, you only have to be concerned with what's on the screen now. In the last example with HA Proxy, we didn't even have to work with the host firewall at the load balancer. So we'll probably have the same situation with this example. So let's hop behind the command line and set up Nginx. Nginx isn't quite as easy to install. It's still pretty trivial, but you do have to install the EPEL releases first. So I will yum install tacY EPEL release. And this only takes a second or two. But then when we install Nginx, it's going to take a little bit longer. So now that EPEL is installed, I can yum install Nginx. And this one takes a bit, so I'm going to fast forward through this install portion. Okay, so it's installed. Now let's use firewall command to see if we need to add the HTTP service. And we don't. We see we have HTTP and SSH are permitted services, so port 80 traffic coming in is good. In the HA proxy example, we configured the web nodes to listen on port 8080. I'm not going to do that here. We'll just leave them on port 80. I think that's fine for this example. But we do have to enable and start Nginx. So I'm going to system control enable Nginx and system control start Nginx. And we have to configure Nginx. So let's vim etc nginx nginx.conf. And just like with the HA proxy, this does come with a kind of a default configuration. And what I tend to do if I'm using Nginx is a load balancer and I don't want any of its web server caching or anything like that going on, I will just blow away everything after this events portion at the top and add my own HTTP section here. And so just like with HA proxy, we have to configure the front end and the back end. And so the Nginx, so just like with HA proxy, we have a front end and a back end. Nginx likes to call the back end the upstream. So I'm going to start with upstream and we're going to call it demo app. I think that's the example we used in the last one. And we're going to give it some servers. So server will be 10.0.1.20, and we're not specifying ports because we haven't changed them. 10.0.1.30, so that's node 1 and node 2. And then we have our front end, which in this case is referred to as the server itself. So the server itself running Nginx. And so for the server, we're going to listen on port 80, just like our HA proxy example. And we're going to set our location to the root level. And we're going to proxy pass to http:// our demo app. Then we have to close these brackets that we have dangling open here. And so assuming I've got the syntax right and I've closed and opened an appropriate amount of brackets, we should be able to save this and system control restart Nginx. And it looks like I have a typo somewhere. So let's just use status Nginx, see if we can figure out where. And we have an unexpected close bracket on line 31. So let's take a look. And I think this one here might just be extraneous. So let's see if that works out. Nginx is now running. I'll use SSLNTP to make sure we're listening over port 80. We are. I will curl the localhost. And we're getting a bad request. So Nginx is working, it's running, it's listening on port 80, but we're not sending anything to the servers themselves. So we still have a problem with our configuration. Let's jump back into that. And I'm going to take a shot in the dark here. I've not used underscores when setting up something like this. So let's just roll that out. Let's take out the underscores, restart Nginx, and see if that doesn't resolve our problem. Yeah, so there it is. Don't use underscores in your upstream specification. So as you can see, I'm node 1. Since we didn't specify anything, we're round robin. So if I go back to that 4i in, and then we do 1 to 10, so 4i in 1, 2, 3, 4, all the way up to 10, do this 10 times. Do curl localhost. Done. It should go 1, 2, 1, 2, 1, 2, and that's what it does here, 2, 1, 2, 1, 2, 1, 2, 1. Now we can change that algorithm to use source, just like we did with HA proxy, only we'll refer to it as IP hash. So let's go back in here, and we're going to put it right here above the server. I'm going to use IP underscore hash right here, and we're going to restart it. And we do need to have a semicolon at the end. And so now if I run my for loop again, let me clear my screen. then we're going to be stuck to node 1. So let's move to client 1 and do this testing. Right now we're all on localhost. So let me jump over to client 1. So I'm on client 1, and if I curl 10.0.1.10, so that's the IP of server 1, I get node 1. So we know that our load balancing method is IP hash, which is analogous to source with HA proxy. So this is kind of the best effort stickiness. And I can use that for loop again for I in 1, 2, we'll just go to 5. And we're going to be stuck to node 1. So let me hop over to node 1 and stop Apache. So I'm on node 1 now. Let's system control stop HTTPD and hop back to our client. Now from the client, I'm going to expect to see it to be node 2, and that's what we've got. Both HA proxy and Nginx are very powerful. If I had to give an opinion on one or the other, I have more experience using HA proxy in a load balancing capacity. There is a lot of documentation. There are a lot of options. It is less of a Swiss Army knife than Nginx. It is a very robust load balancing solution. On the other hand, I also like Nginx. I like Nginx as a lightweight web server. I like Nginx because you can do some load balancing with it. And that's not even getting into the Nginx Plus side of things. So both are very good solutions. Depending on the use case, one may be more appropriate than the other. But honestly, if you're just doing some basic load balancing like what I've demonstrated here, you're fine either way. This lesson is now complete. Thanks for watching. Hi and welcome. In this lesson, we're going to be taking a look at setting up OpenVPN. So let's get started. Before we hop behind the command line, let's examine the architecture. So everything's in the VPC, obviously, but I have client 1 over here in the 10.0.2.0/24 subnet. So that's an important distinction. This is different from everything leading up to this lesson. So client 1 is in a different subnet. Same last octet, same .11, but it's 10.0.2, not 10.0.1. Otherwise, we have server 1 back in the normal 10.0.1.0/24 subnet with a .10 IP. And then we have a web server that we'll just call node 1 with .20 in the same subnet as server 1. And so what we're doing here is we are setting up server 1 as the VPN server. And the web server at node 1.20 is configured or firewalled to only permit incoming web requests from the 10.8.0.0/24 source. So what that means is that if you don't have a 10.8.0.0/24 IP, you're not going to be able to curl the header or access that website. So why 10.8.0.0? 10.8.0.0 is the subnet that we'll use for the VPN client. So this is a somewhat unique circumstance. Typically you would have websites inside of networks, and you wouldn't filter it to specific VPN traffic or anything like that. But you could, and so that's what I'm doing in this lesson, because I really want to drive home that the web server is not accessible unless you are connected via VPN. So remember, the client is in a different subnet from the VPN server and the web server that we are going to actually reach out to. The web server's firewall is already configured. The client firewall doesn't really matter, but we will have to negotiate the VPN server's firewall. And I've ensured that 1194 TCP traffic is open between the client subnet and then the server's subnet as well. So let's hop behind the command line and start installing OpenVPN. So I'm logged into server 1 here, 10.0.1.10, and I need to install OpenVPN. And before I can do that with yum, I need to install the EPEL release package or the repo. So yum install tacy EPEL release. And once that's installed, I'll be able to install OpenVPN from the EPEL repo. So EPEL's installed. Let's clear, and I will yum install tacy OpenVPN. And this will take a second to install. Okay, so OpenVPN is installed. I'll clear my screen again. Now I need to open the firewall. Normally, what you could do is you could just use the firewall command permanent and add the service OpenVPN. And this opens UDP 1194. However, I'm not going to use UDP. I'm going to use TCP. Typically, you would use UDP for VPN traffic. It's going to be higher performance, and TCP is going to be more reliable. I'm not concerned with performance here, and I'm keeping things somewhat locked down, so I'm going to use TCP. And so I will need to add the port. So firewall command, permanent, add port equals 1194 TCP. And I also need to enable masquerading. So I'll use firewall command, permanent, add masquerade. And then to pick up these changes in the running firewall, I'll need to use firewall command, reload. So our firewall is sorted out now. We have installed the EPEL repo. We have installed OpenVPN. We need to generate some keys and credentials. And so for that, I'm going to use EasyRSA. So I'm going to yum install EasyRSA. And this will take a minute or less to install. And there it goes. So I'm going to create a directory. Right now, everything for OpenVPN is in etc OpenVPN. So I'm going to create an EasyRSA directory under etc OpenVPN. So I'll use make directory, etc OpenVPN, and I'll just create an EasyRSA folder there. And then I want to go into that. So now I'm in the etc OpenVPN EasyRSA. EasyRSA installs under user share EasyRSA, and then there's versions, and I'm going to use version 303. And so that I don't have to type that out over and over and over again, I'm actually just going to append it to my existing path, and I'm not putting this in bash RC or anything like that. It's just for right now. So I don't need this to persist. So now I should be able to use EasyRSA directly. And so before I can start building any certs or anything like that, I do have to initialize the PKI. So I'll use EasyRSA init PKI. And so PKI is initialized. We can now create a CA. So I'll use EasyRSA build CA. And we're going to have to give it a passphrase. And I'm just going to pick something really easy because we're going to have to re-enter this every time that we sign a cert. And so I'm just going to leave this as the default right here. So we've initialized our PKI, we've built our CA. Now we need to generate a Diffie-Hellman key, and that's going to provide forward secrecy. And so I'm going to use EasyRSA gen DH. Now this command is going to take a little bit, and it's kind of inconsistent. I've seen it come back really quickly, and I've seen it come back after a few minutes. It probably depends on the amount of entropy on the host and that kind of thing. But we'll let it run for a minute. Okay, and so now we have our dh.pem. We can move on to the server credentials. For my own convenience, I'm not going to password protect these credentials, but you're welcome to do so if you want additional security. And so I'll use EasyRSA, and I'm going to generate a request. So genrec for server and server. I'm going to generate the request server no path. Because I do not want to use a password, and I'm just going to leave this default. Now I need to use EasyRSA, and I need to sign that request. And for that, I'll use server. And here you want to type yes. And if you type anything else, it's just going to abort. And then you're going to need to put in the passphrase you used for your. Now we need to do the same thing for the client. So we're going to go up here and generate a request. And we'll call it client no pass. And I'm going to leave that the default. And then I need to sign it. Again, type just yes, and then whatever easy password. So we've created a server cert, we've signed it, we've created a client cert, we've signed it. Now we need to generate a TLS key, and that again is for forward secrecy in OpenVPN. It will ensure that the old data sessions cannot be decrypted, even if someone were to get a hold of your private key. So I'm going to cd to etc OpenVPN. And I'm going to use OpenVPN gen key secret, and I'm going to use PFS. So now I've created the PFS.key, the TLS key, and we can move on to configuration. There is a lot of configuration, and there are example configurations. If you go to user share, in fact, I will less it. User share doc open VPN sample, and then sample config files, and then there's server and client here. And so if you hop in here, it's a well commented configuration file, and you could copy this into your etc OpenVPN as server.conf. Go in here and make the necessary changes. Make sure that you're pointing to the right keys and that sort of thing, and do it that way. I am actually just going to copy and paste into server.conf here. So I'm creating the server.conf file, and I'm going to paste in here. And so I'll run down it real quick. Like I said, all of this is documented really well in OpenVPN's documentation. A fair amount of it's documented in this sample config files. So I'm listening on port 1194. We're using the protocol TCP. Device ton will create a routed IP tunnel. I could use device tap or for an Ethernet tunnel or something like that. Dev ton is what I've always used. We're referencing our CA. We're referencing our cert. We're referencing our key. We're referencing our Diffie-Hellman. We're using topology subnet, which is what is suggested. We're specifying a cipher and an auth. We're saying that our server is going to be 10.8.0.0. So that's kind of the subnet that your server is going to use for assigning IP. We've got some push options. So we're doing a redirect gateway. I'll get to that when we get to server configuration. You'll see kind of how that fits in. We're pushing DHCP option DNS. So we're pushing Google's DNS 8888 and 8844. We're using an if config pull persist of IPP.txt. And that's going to maintain a record of the client to virtual IP address associations. And the reason you do that is if OpenVPN goes down or is broken, restarted, whatever, reconnecting clients are assigned their same IP. We've got a keep alive setting here. And so that causes a ping-like message to be sent back and forth over the link so that each side knows when the other side has gone down. Ping every 10 seconds, and assume that it's down if no ping is received during the 120 seconds back. Comp LZO is compression, and if you enable it here, you also have to enable it in the client. Persist key and persist ton. The persist options try to avoid accessing certain resources on restart that may no longer be accessible if you've done a privilege downgrade. We're saying where our status log is. We're saying where we're appending to a log. We're applying some verbosity. And so it's a scale of like 0 to 9. So 0 is silent except for fatal errors, and 9 is extremely verbose. So we're somewhere on the low end of verbosity with a 3. And then we've got our TLS at the very bottom. And so this is good. We're good to go ahead and save this file. And now we can start OpenVPN. And so we'll use system control start OpenVPN, and then we'll do an at our config.service. So system control start OpenVPN at server.service, because we're using the server.conf. And so OpenVPN is up and running. It's listening on TCP 1194. So before we hop over to the client, we need to package up the keys that we created because we're going to need those keys as our credentials to be able to connect. Welcome back. This lesson was getting pretty long, so I decided to break it up into two, and we're going to pick up right where we left off. So let me clear my screen. Let's package up those keys. And so I'm going to make a new directory, and we'll call it server 1 because this is server 1. And we'll put a subdirectory under there called keys. And now I want to copy my PFS key to server 1 keys. And I want to copy, we're going to copy a bunch of these. So I'm going to copy the EasyRSA, PKI, Diffie-Hellman, 2 keys, and I want to copy my CA cert, and I'm going to need to copy the CA key, the client key, and the client cert. So CA cert, and let's grab the CA key, and those are private. And we'll grab the client key from the same place. And we'll grab the client cert which isn't under private, it's under issue. Okay, so we've copied all of these keys into Etsy OpenVPN Server 1 keys. And now I'm going to tar them up just to make it easier to copy them over to client 1 when we're ready to configure it. So tar verbose file. I'm going to put it in temp. We'll call it keys.tgz. And we'll just grab server. So now I've created a tarball, zipped tarball over in temp that I'll use to SCP over to client 1. So let's hop over to client 1 now and get it configured. So I'm on client 1. Remember, it's 10.0.2.11, so a completely different subnet. And I'm going to need to install OpenVPN. And I'm going to do that before I pull the keys over. And so the first thing I'll do is install Apple Release. And then once Apple Release is installed, I can install OpenVPN from the Apple repo. So yum install tech-y OpenVPN. So OpenVPN's installing. Once that's done, I can bring the keys over. And I could bring them over early. I want to drop them in Etsy OpenVPN. And that folder, it won't exist until OpenVPN is installed. So I'll clear my screen. So I'm going to CD into Etsy OpenVPN, and I need to copy those keys over. So I'm going to use SCP cloud user at 10.0.1.10. I dropped the keys in temp, and I think I called it keys.tgz. And I want to pull it over to right here, grab the password, put it in, and now I can tar extract verbose zip file keys right here. And if we look, we have client, we have our keys.tgz. I can delete that now. We have our server, and then we have server. Server 1 is where the keys for server 1 reside. So at this point, I can create the client.conf. Now, just like with the server, you can go in and you can pull the sample and look at the comments and make the changes, but I'm going to copy and paste, and I'll walk through it. So I'm going to vim client.conf, and I'm going to paste the configuration in here. So at the very top, we've got client, device, ton, protocol, TCP. This is our remote VPN server, so 10.0.1.10 over port 1194. We've got our keys, our CAS cert, our key, our TLS, the TLS version, the TLS cipher, the cipher, the auth, resolve, retry, infinite, authorization, retry, none, no bind, route, no pull. This one's important because we're not setting up any routing whatsoever with our VPN configuration. And I've done that on purpose because, we've already talked about routing and static routes, but you're going to add a static route once you're connected to be able to make this work. And we'll get to that here in a minute or two. Persist key and tunnel I've covered. NS cert type is server. And again, you have to have comp LZO. If you've got it on the server, you have to have it on the client. Verbosity, TLS client, and the auth server key right there, pfs.key. So this looks good. I'm going to write and start up OpenVPN. And just like with the server, we're going to use @client. So system control start OpenVPN @client. Now, if I do an IPA, you're going to see we have 3 devices now. We have at the very top our loopback. Then we have ETH0 with its IP 10.0.2.11. And then at the bottom we have TUN0. So that is our VPN tunnel with an IP of 10.8.0.2/24. So we were able to get that address from our VPN server. We're connected. Now, we're not necessarily using this VPN connection for anything. And I'll clear my screen. And if I do an IP route show, here's what we have. We have our default gateway. We then have, for everything in the 10.0.2, our local subnet, we use ETH0. And then for everything in the 10.8.0 subnet, we use tunnel0. And then we have some DHCP 169 stuff at the bottom. So if you'll remember, we have the web server set up to only respond to requests from the 10.8.0.0/24 subnet. So if I try to curl 10.0.1.20 now, it's not going to work. It's just going to hang. However, if I add a static route to force connections to 10.0.1.20 over the device tune 0, then it's going to work. So let's add that route. So IP route add 10.0.1.20 device tune 0. Now, if I go back and try to curl it, it's going to come right back. So we have verified that our VPN connection is working. Now, a lot of VPN configuration is handled kind of on the back end, and they add a lot of routing and that kind of things for you. I've kept this this is the skeleton of a VPN, and I've done that on purpose. I want you to kind of understand what all goes into making a VPN work. We created the server. We created a bunch of keys so that we don't have to type a bunch of usernames and passwords. Or you could also do like a one user key. It would be a lot easier. But this way is at least somewhat secure. We've created the client. We've configured the client. And then we created that connection. So we had that TCP handshake over 1194. But we didn't really use it for anything. You know, we received a DHCP, 10.8.0.0/24 IP, and that was good. And now we have specifically said, we've added a route saying, hey, for this connectivity to reach this host, I want to use my VPN interface, or at least the virtual interface created by the VPN client. So we've specified send all that traffic through that interface. So for the last thing, I'm going to hop back over to the server real quick. And I'll clear my screen and we'll just look in here. Now, remember, we have that IPP.txt that we specified. And so we see we have client at 10.8.0.2. We can cat our OpenVPN.log, and there's lots of logging data in there. We can also cat our OpenVPN status log, and that's going to show our OpenVPN client list. And so here you're going to see the common name, client, the real address, 10.0.2.11, bytes received, bytes sent, and connected since, as well as the routing table and some global stats. So obviously you can use this file to determine how many clients you have connected and that sort of thing, pipe it through a bunch of filters. That wraps up this lesson on setting up OpenVPN. Thanks for watching. Hi and welcome. In this lesson, we're going to discuss IDS, what it is, and why you might use it. Let's get started. An IDS is an intrusion detection system. This is a network security component used to detect intrusion attempts for the purpose of vulnerability exploits. And if you've ever managed a publicly accessible Linux host, you're probably familiar with the hundreds or thousands of SSH attempts you get from bots and crawlers. An IDS adds some policy and rules around what should be noted and logged in an alert log. Similar to an IDS is an IPS. This is an intrusion prevention system. This is a component for preventing vulnerability exploits, so an IDS merely observes while the IPS takes action to prevent intrusion. For the scope of this lesson, we'll be discussing and focusing on IDS, or more particularly, a network intrusion detection. So here's a sample architecture. We have a typical private network, a bunch of hosts that use a gateway or router to additional networks or the open internet. We have another host we'll designate as our IDS, and our IDS will normally have an additional NIC configured and implemented in such a way as to have tap or span visibility into the traffic in and out of the router. And so this is common due to IDSs historically not being able to keep up with inline traffic, though that's less of an issue now. So deployed in this manner, the IDS is going to have visibility into all of the traffic coming into and out of the private network. Now, there can be scaling issues when deploying all of the IDS components to a single host. So just because I'm using a single node here doesn't mean that's completely representative of all infrastructures. You could easily break out the IDS components to build out an IDS cluster. And so now that we know what an IDS is and how it fits into the infrastructure, let's talk about Snort. Snort is an open source network intrusion prevention system capable of performing real-time traffic analysis and packet logging on IP networks. So this is taken directly from the Snort FAQ, and it is the de facto open source IPS. So Snort is an open source IPS or IDS maintained by Cisco. There is increasing overlap between proprietary and open source offerings. And what I mean by that is that Cisco is more and more leveraging the Snort engine and rule set in their proprietary offering. It can be used as a packet sniffer like TCP dump or Wireshark, as a packet logger, which is how we'll be using it in our example, or as a full-blown IPS. Leveraging Snort as an IPS does require a paid subscription for access to the rule sets and rule set updates. There are additional open source components to the Snort ecosystem that extend and augment its usability, so let's touch on those. So here we're building our IDS infrastructure, and since we're using Snort, we can break it down into three primary components. The first is Snort. We use Snort for low-level network observation and as a rule engine. The other two components are optional. Snort is the foundation. We'd typically have it set up to run as a service, and then we'd employ some mechanism for rule updates similar to how antivirus definitions are deployed. Secondly, we have Barnyard or Barnyard 2. Snort writes out binary files, and Barnyard 2 is an open source interpreter for those binary files. This permits Snort to continue to write to disk in an efficient manner without missing traffic. Lastly, we need some kind of visual front end for interacting with our IDS, and Snorby is an open source web app front end for Snort and is normally backed by a database. I don't have it listed, but honorable mention between Snort and Barnyard would be pulled pork. So as I mentioned that we'd employ some mechanism for rule updates, that is pulled pork. Pulled pork functions as a rule management application for keeping the rules updated. It permits receiving up-to-date rule definitions when new exploits or vulnerabilities are discovered and disclosed. Lastly, installing Snort isn't terribly complex, as you'll see in the next lesson. However, installing the additional components to the ecosystem like Barnyard and Snorby can require a significant amount of setup and trial and error, and in most cases compiling from source. The documentation is okay, but it's somewhat thin, and you'll probably find yourself combing through multiple setup guides during the install. This lesson is now complete. Thanks for watching. Hi and welcome. In this lesson, we're going to install Snort as an IDS. That is, we'll be using Snort to observe exploit attempts on our host per the rules we define. Before we get started, let's review the architecture I'll be using. So here is our Snort architecture. We're going to put Snort on the host in the middle. That's server 1. It has a public IP. The internal IP is 10.0.1.10. We'll have a client that we'll test with on the 10.0.2 network. And then we're going to have a bad actor host over here on 10.0.4.10. So let's say there's some manner of exploit that is being implemented through the bad actor host. We'll call it server 2. And we want to put some kind of rule in place so that we see if any traffic is taking place with that host. So maybe it's a compromised host on our network. Maybe it's a compromised host on a different network. Either way, we want to know when any interaction occurs with that host. So let's get behind the command line. We're going to install Snort on server 1, 10.0.1.10. We're going to put the rules on that server, and then we'll do some testing from the client. So let's get behind the command line. So I'm logged into server 1, 10.0.1.10. And the first thing I'm going to need to do is install EPEL, because I need EPEL to install libdnet, and I need libdnet for some low-level network functionality. So I'll use yum install techy EPEL release, and then I'll do the same for libdnet. Now to install Snort, I'm first going to have to install DAQ, D-A-Q, and that is the data acquisition library. And then I'm going to need to install Snort, and neither one is available in a repo. It's not available in upstream CentOS or RHEL. It's not available in EPEL. So these we'll have to download from the website. And so for these, I'm going to copy and paste. I'm just going to use yum install and then the site. So we'll install DAQ first, and then I'm going to install Snort, and this is version 2.9.12 TAC1. Now, while this is installing, I'll mention there are some idiosyncrasies to this install. And the first one we're going to encounter, and this may or may not be needed in later versions, but as of 2.9.12, we need to create a symlink for libdnet. So I need to symlink libdnet SO101 to libdnet.1. And so I'll clear my screen. I'm going to create a symbolic link from user lib64 libdnet.so, and you can see we have .so.1 and .so.101, and I'm just going to use 101. And I'm going to link it to user lib64 libdnet.1. Kind of hackish, but it'll get you through the rest of the install. Next, I'm going to install wget, and we're going to use wget to pull down the community edition of the rules. And so now I can wget http snort.org/rules/community. And I'm going to send that out to a file, community.tgz. Now I can tar extract verbose zip file, community.tgz, and we have in there our community.rules. We also have that SID-tech message map. You would need that if you were setting up Barnyard. But in this case, I'm going to copy the community rules, everything into Etsy Snort rules. Now we have to fix the reference for dynamic rules that were not provided by the RPM. This is another one of those idiosyncrasies. So we have to make the directory user local lib snort dynamic rules, and then we'll chown it and chmod it. So make directory tech p, because we need to create subdirectory, local lib snort underscore dynamic rules, and then we need to chown it to snort. And then we're going to need to chmod it. Okay, so now we can jump into the snort.conf and get that sorted out. So I'm going to vim etsy snort.conf. And this is a very robust and well-commented file. We're not going to use whitelists, so I'm going to comment that out. I'm going to look here at this var rule path first and make sure that everything is set up to etsy snort rules. Now, if you observe this text here, it says currently there is a bug with relative paths. They are relative to where snort is not relative to where snort.conf, like the above variables. I found this to be somewhat inconsistent. So I'm going to remove this parent directory and just put etsy snort here. And then, like I mentioned, we're not going to use whitelists and blacklists, so I'm going to go ahead and comment these out. And because I've commented them out here, I need to go down towards the bottom of the file where the preprocessor is and comment that out as well. And that is down near step number 6. And so right here we have this reputation preprocessor. I'm going to comment all of this out. Now we also need to uncomment some logging, and I'm going to use this output log unified 2 file name snort.log limit 128 no stamp. And then we need to do something with the rules. So right now, all of these rules are included in the config. However, none of these rules actually exist in the rule path. So to get these rules, you could use a paid snort account and then download them and extract them into that rule path directory. However, I don't have that, so I'm going to basically just rely on the local rules, local.rules. Those are the rules that I'm going to provide, and then the community rules. So I'm going to yank and paste this, and we're going to make sure that we have our community rules that we downloaded and extracted. And then we're going to take the rest of these and we're just going to comment them out. So in Vim, I'll hit escape, I'll hit Control V, and then I'm just going to come down here to the bottom. I'm using Visual Block. I'm going to come down here to the bottom. You could delete these. I'm just going to comment them out. I'm going to come here to this last line. I'm going to hit Shift I to insert, and I'm going to insert a comment, escape twice, and I've now commented them all out. At this point, we can save and quit the file, and we can test the file. So we can validate it with snort tech uppercase T for test, and the file is going to be etsy snort.conf. Now it's going to fail because we have not added or created the file local.rules. So let's go ahead and create that file. And we may have that pathing issue that we have to contend with as well. So we'll try it again. All right, so now it works. At this point, let me clear my screen, and we can go back into that local.rules. So vim etsy snort rules local.rules, and we can add our rules here. So let's add a rule. Let's say that in this case, an example use case is our IDS is watching a LAN of domain controllers or something of that nature, and we don't want our systems administrators necessarily surfing the internet from those machines, or at least if they do, we want to know about it. So we can create an alert, and we'll say TCP connection from any host, any port, or rather from any host, port 80, and we're going to make it bidirectional here. So not just coming in, but going out as well. From or to our home net. Now this is, home net is a variable set up in snort.conf. And typically you would say home net is going to be bound to a specific interface, that interface that is port tapping or spanning and watching all the traffic. In this case, I left it as any, and we'll say any port. And we want to create a message. So we're going to say message, and we'll just say HTTP request. So that you can set this to whatever you want. And then we have to give it a unique ID, a SID. And so we'll just give it a 1 followed by 6 zeros and a 1. And each of these has to be unique. The community rules, the proprietary rules, the vendor rules will all have SIDs. So we'll start it pretty high up. And then we can give it a revision. And in this case, our revision is just 1. And so now we have this rule. We can save it. We'll need to system control restart snort D. And with that restarted now, let's just curl the header of linuxacademy.com. And we can go in, and if we look under var log snort, we'll see that we have an alert log with some data in there. And if I just tail var log snort alert, we'll see there is our request out to linuxacademy.com. So let's add a couple more rules. Let's vim etc snort rules, local.rules. Let's say we want to create an alert on any incoming port 80 traffic. That would look like alert TCP from any host, any port, coming into home net over port 80. So from any IP or range at any port coming into our home net over port 80, and we'll create the message. We'll call it incoming HTTP request. Now we'll have to give it a larger SID. So 1, we'll say this one is 2. And our revision is 001. And let's also put something in so that any requests going to that bad actor are alerted. So we'll create an alert, and we'll use TCP. And our bad actor host was 10.0.4.10, any port. And we'll say bidirectional. So if we reach out, it has to come back with the ACK. Home_net, any port. And we'll just call that message bad actor. Again, we'll have to give it a SID. And we're about to have a syntax error here. And we'll call this one number 3. Revision is number 1. So I can save and quit the file now and bounce snort. Now, if I ping 10.0.4.10, it's not going to work. However, I could try to curl 10.0.4.10. We're going to get bad server back. Let me hop over to the client and make a web request to server 1. So here on client 1, I'll curl 10.0.1.10, and there's no Apache running, so I'll just Control C out of that. But we still made that port 80 request over. So let's hop back over to server 1 and look at the log. So back on server 1, I'll clear my screen, and we will tail var log snort alert, and we can see the HTTP request that went out. We can see that bad actor request, and you can use these rules not to just alert, but you can actually use them to do things, which makes Snort a really powerful tool in terms of an IPS or an IDS. We're really just scratching the surface of what's going on here. For a full implementation, you would install Barnyard 2, Snorby on top of that, pulled pork if you wanted to automate your kind of rule updates. But this should give you a good idea of what Snort is, what it's capable of, what IDSs are, what an IPS is, and that sort of thing. One final word, since we did bring in the community rules, we are implementing Snort in as a partial IPS. So anything that the community rules pick up, any exploits or anything that are leveraged by them will then drop those requests. So our local rules are purely around IDS, but the community rules do apply some IPS as well. This lesson is now complete. Thanks for watching. Hi and welcome. Congratulations for making it through the entire Linux networking and troubleshooting course. I really hope you enjoyed this course as much as I enjoyed creating it, and you now have a solid understanding of networking with Linux. So what's next? Networking is such a fundamental component of IT that the skills and techniques you've learned are portable to just about any other IT discipline you can think of. Networking is the underpinning of what makes IT work, but there are some suggestions I'll make. In the Linux track, you've got a good head start on the LPIC certifications, including up to at least the 300 level in terms of the networking components. Likewise, with the Red Hat Certified Systems Administrator and Systems Engineer, your familiarity now with FirewallD and Network Manager should put you in a comfortable place for those portions of the training. So if you want to pursue those certifications, they would certainly be a good fit. As for AWS, you're in a good place to knock out some AWS certifications as well, and I'd recommend taking the AWS Certified Advanced Networking course as an extension of what you've learned in this course. Some of the material will be a recap, but it covers BGP in a little more detail as well as MPLS, also the AWS infrastructure components such as VPCs. And while there may be AWS-specific terminology used, the concepts are largely the same and easily transfer to other cloud providers. Again, thanks for taking this course. I hope it met your expectations. Take care.